So dear Alain, dear Estelle, President of Paris-Saclay University, dear speakers, dear all, thank you so much for being here. We are pleased to welcome you at Institut Optique on this very special day. And Alain, I would like to start by simply saying, you've made it. So at Institut Optique, we are delighted to finally celebrate with you this well-deserved Nobel Prize. And it was a real pleasure for all of us to prepare this scientific celebration to honor not only the Nobel Prize, but your outstanding career. As you wished, this event has been designed to be at the same time prestigious and convivial. So we'll do our best to have both at the same time, all along the day. And the scientific program is, as I was saying, not only about the celebrated Bell's inequality, which led Alain to Stockholm, as you all know, but is meant to honor this whole outstanding career of Alain Aspect. So the program reflects what is so important for us at Institut Optique, and what Alain perfectly represents: the deep connection between fundamental science and technological advances, and the link between research and the transmission of knowledge. So the conference today will be divided in 4 sessions let's say, to enhance topics to which Alain contributed a lot, and some of them he even pioneered the topic. And this will take us from quantum optics to cold atoms. And we also have a focus to include the connection between fundamental issues in quantum physics and the development of quantum technologies. So 4 sessions that will be very, very deep and I hope enjoyable day. Please note that we will have a surprise right before lunch. So as it is a surprise, I can't say more than this, but please pay attention to this very important slot in the program. So it's obvious to say that this event could not take place without the involvement of many, many people. So let me first thank the speakers and the chairwomen and chairmen who all readily accepted to contribute and with great enthusiasm. The day would not be possible without the support of many sponsors. So those sponsors include the French Optical Society, the French Physical Society, Paris-Saclay University, the X-Core Foundation, and 3 companies, Excel, Pascal, and Candela. And of course, the organizing committee is at the center of everything. I would like to extend my warmest thanks to Clémentine Bouillet, Marie-Madeleine Greffet, Nicole Czerniawski, Isabelle Leotti, Cédric Lejeune, and Thierry Dussel. This is an amazing organizing committee that has worked with the help of Fabien Siffrit, Christophe Dio, Graça Martins, Lina Benzeroni, and of course, our technical partners and many volunteers. So I will not be longer than this because we need to enjoy this great scientific day. So with that, I hope you will enjoy the day. And I will now hand over to Estelle Iacona, President of Paris-Saclay University. Thank you.
Good morning, everyone. Monsieur le professeur, monsieur le directeur de l'Institut d'Optique, cher Rémi, monsieur le professeur Alain Aspect, cher Alain, dear colleagues, first I would like to thank Institut d'Optique to organize this event. We are all very happy to be all together today and to be with Alain Aspect for this day. So thanks to Institut d'Optique and to all the people who made this day possible. It's a great pleasure for me to be with you today, to introduce this event. To introduce a scientific event, it's always a pleasure for a president of a university. And today, it's not only a scientific event, we are all here to celebrate and to honor an eminent member of our community. To celebrate a scientific distinction, a personal recognition, but I know that Alain is always also saying that it's a collective distinction. and it's a token of a scientific breakthroughs. So I'm very happy to represent Université Paris-Saclay and the whole community of university. And in my name and in the name of this community, I would like to address once again my warmest congratulations to Alain for this prize. And I remember when we were less than 1 year ago in this amphitheater, when we just got the news, and as many of you said, I was just elected, as you to say. I didn't do anything for that, and I was just on the picture, so it was very easy. So this Nobel Prize completes a list of many other prestigious distinctions, national distinctions for Alain, and many international distinctions. May I remind that the Nobel Prizes awarded those who have conferred the greatest benefit to humankind. And when you know all what Alain did for during his career, quantum research and technology will for sure contribute to society, contribute to better society. In a world as complex as ours, made of environmental constraints, economic imbalances, social inequalities, and even democratic fragilities, technical innovation will be a large part of solution. It won't be the only solution, but it will be a large part of solution. So scientific and technological innovations are necessary for transition. And as Alain said last week, I think, at the graduation ceremony of our Master of Physics, so Alain said to all the students in the room, you can't answer the planet problem against science. And I think that you added, you need modern science. Modern science in terms of breakthroughs and deep knowledge in all disciplines, and also disciplines talking together. For all sciences, what we call hard sciences, human and social sciences, health sciences, and so on. And we basically had the same message to give to the students last week, so we are on the same track. And I just want to finish this introduction saying that us, as academic and as institutions, we have a very strong responsibility to contribute with our 3 missions to this modern science and to this modern society. Of course, through research, of course, through innovation, and also through education. And these 3 missions are completely working all together. Of course, I just want to stress that Alain crosses all these 3 missions, and he did great research, innovation, and education all his career. As a mentor of students, and I'm sure that in the room we have many people who remind part-time of their study with Alain. I didn't follow your classes. Maybe it's not too late. And I'm convinced that our students, our graduated students, are also innovators. So innovation through research, but also innovation through education, because all our graduated students, whatever the job they will have in the future, in a company, in a research institution, or whatever, they will be innovator, and we need them to change society. And so as an university, we have this responsibility too. And I just want to finish with one thing, is the importance of fundamental academic freedom in research. If we want to change this society, we need academic freedom. And I want to finish by also emphasizing the fact that Institut d'Optique has always supported Alain Aspect research, for sure, but in general, fundamental research with strong investment, with strong support, financial support, but support in general. And our institutions need to do that. So if we have Alain Aspect with us today, it's because he's an incredible researcher, but it's also because Institut d'Optique has always supported his research and the way of doing research this way and innovation this way for years and years. So we really need to do it again as institutions, but I think we need also to repeat again. Well, I don't have to convince you of that. I'm sure you are. But when we are in different places than academic places, especially when we talk to politician people, we need to repeat this, I think, again and again. Why are you doing great research? For many reasons, but the first one is because we invest in research for years and years and years. So thank you, Institut d'Optique, for that. Once again, congratulations, Alain, and I wish you all a good conference.
Merci. J'ai pas besoin du micro, moi, mais on va le donner. On va le donner à... Okay. It is now time to start the scientific session. First of all, I would like to say a couple of sentences in French to Alain. Alain, je voudrais te remercier pour les 39 années de collaboration scientifique que nous avons eues, et absolument continue, et pour tout ce que tu as eu, j'ai eu le privilège d'apprendre de contact avec toi. So now we have three talks this morning. We start with a double session talk by Philippe, who will tell us, Philippe Grangier, who will tell us about the early years and the Bell inequality test. Philippe is here, and this will be followed by Jean Dalibard, who will speak about the college years. Philippe, the floor is yours.
Thank you very much, Christophe. So I'm very grateful for organizing this day in the honor of Alain. It's a pleasure and an honor to be there. So I will make some kind of history, that is to speak about the experiment we were doing 40 years ago in Institut d'Optique. So my first point is, where is Institut d'Optique? This is an important question because experiment we did 40 years ago were not here in this building. They were in Orsay, in this old building, Bâtiment 503, who is still there, still being rebuilt presently. But everything I will show was done in the underground of this building in Orsay. So as you know, we moved in 2007 to this present building where we are now in Palaiseau. Okay, it's a much nicer building, but remember that historical Institut d'Optique was there. This is our present logo. This is this logo. This was the old one that you will see in all slides, obviously. Okay, so I move to quantum mechanics. I like to tell to my students that quantum mechanics is a good candidate to the title of greatest intellectual adventure of the 20th century, which means greater than relativity or psychoanalysis. You agree? This is a theory which is at the basis of our understanding of the world, the stability and structure of matter. Without quantum mechanics, a classical electron would fall on the nucleus by radiating light, and we would not be there to speak about it. So the stability structure of matter, the nature of light, photons, the interaction between both is all explained by quantum mechanics. The formalism is perfectly coherent, incredible success, transistor, etc., electronics, etc., etc. So everything is nice in the quantum world. But quantum mechanics keeps a mysterious character. It is a very deeply non-deterministic theory. It is non-local in a subtle way. There is no simple correspondence between quantum object and the macroscopic world. This is a famous Schrödinger's cat paradox. So all these things make people think and act also. So the sort of paradigm of this mystery is this Einstein-Bohr debate, which took place in 1935 due to following a paper by Einstein, Podolsky, and Rosen, who, with some argument, I will not detail but come back to that later, told that quantum mechanics is incomplete, in the sense it's hiding us something. So Bohr, the pope of quantum mechanics, disagreed, and there was an instant debate, but basically, it did not trigger a lot of excitation because quantum mechanics was just so successful. It allowed us to understand, as I said, everything about physics, a new concept, transistor, lasers, and also no disagreement on the predictions. So the debate was considered as philosophical. No experiment could decide. And the situation changed completely in 1964 when John Bell proposed a theorem. Then it was slowly acknowledged to be extremely important. And then one could test physically a philosophical idea, which is sort of very surprising, but this is what happened indeed. So Bell's theorem in a nutshell, so you have this famous source which emits photons, particle of lights, and then you make what is called, we call polarization measurement. There is an apparatus with some orientation, A on one side, B on B side, and the photon goes either here or there, so it makes two results, +1 or -1. Then when the things are remote, one can look at the correlation. So correlation are simple ideas. If you have twins, like twins, if both twins have blue eyes, you just say, okay, this is because they have the same parents, they have the same genes. So let's look at two photons and try to correlate the result, whether they have blue eyes or not. So if you want to do that in the classical world, what you do is that you introduce some parameters that Bell called lambda. So these are just like the genes of the twins. And then the result on one side, plus or minus 1, should depend on the orientation of your polarizer. You will see rotating polarizer later on, and the lambda, the gene of the pair of photons. Same thing on the other side, and these genes are random. You get all kinds of population. So it's very, very simple and natural hypothesis. This is just the way you explain classical correlation. But now the genius of Bell was to demonstrate that if you just assume that, you can construct what is called a correlation function. So a correlation function of two random variables, the results are randoms here, is the average product of the sums. This is just statistics. So you can easily construct and measure this quantity. And if you combine 4 different such correlation functions, like that, with two orientation here, A prime, two orientation here, B prime, you show that this quantity should be between +2 and -2. So these quantities themselves are between +1 and -1. So if you just look at S, it should be between +4 and -4. But due to this hypothesis, this is a fundamental point, and due to this very small smart minus here, S is actually between +2 and -2. Now the point is that if you look at real photon, entangled photon, according to quantum mechanics, S can reach 2 square root of 2, which is clearly above 2, if you choose this orientation. And this is absolutely astonishing because this idea, which just look very natural, a little bit philosophical if you want hypothesis, have a very deep physical consequence, and it can be tested experimentally. So what is this correct description of nature? So this was slowly realized. There were fundamental work by CHSH, Clauser, Horn, Shimoni, Holt. First experiments were done by Clauser in 1972. They were conflicting with other experiments by Pipkin, and then, okay, it was a little bit shaky. And then Alain decided to start this experiment at the end of the 70s with new experiments that I will describe now in more detail. So this is the thing which was in the underground of Bâtiment 503. So the idea was to emit a correlated pair of photons, as I said. So this is a pair of photons, a green and a blue one, emitted in a calcium atomic cascade. And we had big lasers, krypton ion and dye laser. So this is a krypton ion laser. This is the argon ion pumping a dye laser here. And everything is tuned so that the atoms emit this pair of photons in the right entangled state. So the source is very original and emitted a very large number of pairs of correlated photons, which allowed to do a series of experiments in 81, 82 that I will briefly describe now. This is where I started as a researcher. I was, at that time, I started working on this laser. I was a student of Deo Brussels, as we were saying at that time. So this was the first experiment done with polarizer, which were pile of plates polarizers. So there are many plates, and all opticians know that here the polarization in the plane of the screen is transmitted, whereas the other one, perpendicular, is reflected somewhere. So this was the same idea as John Clauser, and you can see this thing in the little museum. If you just look behind here, they are still there. So this worked pretty well, but okay, this was a repeating previous experiment with a better signal-to-noise ratio. So then we started thinking, so we thought a lot. You recognize the persons, I guess. We got a lot of coffee to be stimulated. And finally, Alain went to Amsterdam with a big bag weekend in the 80s, a little bit suspect. But actually, he came back from Amsterdam with his big bag, which was filled. He visited his friend Joseph Bratt in Philips, actually, and he got these things which are polarizer cubes. So they are also polarizers, but instead of these big things, they are very compact, and then we can get both photons, the transmitted one and the reflected one. So we get both the plus and minus one. So it was a very useful tool. So we did this experiment. Now we have this cube, and this is really closer to the thought experiment. One photon is here, detected here with the polarization in the plane of the screen, and it's +1, and the other one is reflected. We get everything. So we just measure for some time with some given orientation A and B. We get this correlation function. We rotate the thing. So rotating the thing was not that easy. It was like 50 kilograms with big weights to balance the thing. But OK, we did that. This was my thèse de troisième cycle. And so we get an extremely good agreement with Bell's, with quantum mechanics, violating strongly by 40 standard deviation, Bell's inequalities. OK, so this was one more step. But the real big step, the famous Aspect experiment, was even more subtle. Because if you look at Bell's hypothesis, you assume that the result on one side does not depend on the orientation on the other side, which is natural because there is no instantaneous effect from one side to the other one. So this is an hypothesis in Bell's theorem, but Alain's idea, also discussing with Bell, was that if you were able to choose this orientation before fast enough, that is why when the photon, before the photon be emitted, for instance, or when the photon was still in flight, then the independence of B on this side and the independence of A on this side and the independence of A and B on the source would be a consequence of relativistic causality. So let's choose at the last instant. And if we choose, we are able to choose at the last instant, then this red bar becomes a consequence of relativistic causality. So it was a very important thing to check. So you have seen my big polarizer, no way to turn them very quickly. But Alain's idea in 76 was to use switches. So like a switch. So it sends the photon either to this polarizer with orientation I prime or this one A. So if you can do that very, very quickly, while the photon is flying between the source and the detector, then you sort of make this late pseudo-random choice, which allows you to imply directly locality, relativistic causality in this experiment. So this was really considered as a big challenge at that time, and nobody could actually really predict the result. I was extremely careful with that. So the switches, so you can also see them in the little museum. They were a little tank of waters. And so the idea, it was again an Alain's idea, because we had big beams, so it was not easy to have big crystal, so it was just water. And so it's a tank of water. There are transducers, and then you make a standing wave due to this transducer, which is a lithium niobate. So when there is no standing wave, the light goes straight. And when there is a standing wave, it's a thick grating, and the beam is deflected. And you see you have complementary channel, either one side or the other side, the transmitted or reflected, and it's uncorrelated with what happened on the other side. So the change, okay, to be as quick as possible, it was changing every 10 nanoseconds, while the time of flight between the two ends was 40 nanoseconds, between the source and the switch was 20, so it was faster, not hugely faster, not hugely random also, but still you see the thing. So these are the big polarizers, one side, one output, the other output, and the switch is inside, and you can see the switch in the museum. Okay, so we did this experiment. So it was, this thing was mostly adjusted by Jean Dalibard, who will speak after me. So, okay, it was more difficult than the previous one. It took several hours. So we had a nice occupation while the photons were counting. Okay, click, 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 click. But after some hours, we made a little calculation because the computer was not able to manage to count and calculate at the same time. It was a primitive computer. But we saw very quickly that Bell's inequalities were violated. And so we repeated the experiment again and again. And then everything worked fine. That is, the quantum mechanics was fully confirmed, and Bell's inequalities were clearly violated, so enforcing Einstein causality. So this was really a major experiment at that time, as I said, the first test of quantum non-locality, direct test by ensuring this complete relativistic separation of the measurement events. Okay, and then after that, there were like 40 years, and in many 30 years here, in many places, people tried to improve. The experiment was not perfect. We were losing a lot of photons. We were detecting only a small fraction of the photon. It was not super good, logically. Also, the switching was not fully random. So all these things were called loopholes. And so it took a lot of time in many places to slowly improve this one and that one. But it was very difficult to close whole loopholes at the same time. That is, to have an experiment which would be really an implementation of Bell's hypothesis. But finally, it happens. That is, physicists are very stubborn. When they want to do something, they do it. And then in 2015, which is pretty recently, there were experiments which were able to close simultaneously all reasonable loopholes. So there were 3 of them done simultaneously in 2015. So this one was done in Vienna. So this is a Hofburg, so Imperial Palace, and it's again the basement. There is a bunker, and there is a very, very long corridor. And so this was a source. So it's very similar to the one we did, except that the photons go in fully controlled direction in optical fibers. The switches are fully random, and all photons, more than 80% of the photons are actually detected. So in some sense, it's close all the loopholes. A similar experiment was done in Boulder, in Colorado, at NIST. And another one was done in Delft, which is interesting. So this one was photons, so it's a similar thing. This one is not photons. The entangled objects are spin, actually, little magnets, quantum magnets. They are entangled using photons, but the Bell measurement is done on spins. So in quantum mechanics, you don't care whether it's photons or spins. They can be entangled, and they can violate Bell's inequalities. And this was achieved in this experiment. Actually, there was a 4th one, which was done in Munich also, with atoms, entangled atoms, similar things, not photons, material object. So Alain published this thing in 1915, closing the door on Einstein and Bohr's quantum debate. So this is Alain's word. By closing 2 loopholes at once, 3 experimental tests of Bell's inequalities, these 3, remove the last doubts that we should renounce local realism. They also open the door to new quantum information technology. So this is, the scheme, you know it now. And this is sort of a very nice achievement. So what follows this achievement? Well, okay, so the conclusion first is that Bell's hypotheses are untenable with respect to nature. And following that, nice events happen. End of last year. So Alain, John Clauser, who was really the pioneer, Alain, who introduced all these time-dependent effects, and Anton Zallinger, who realized one of the loophole-free experiment, got the Nobel Prize. So we went to Stockholm. So we are very happy to be there. So it's not the Nobel laureate, it's Alain with his 2 previous PhD students. They look very happy. It was really, really, really nice. So this is a Nobel conference where Alain and the 3 Nobel laureates, physics Nobel laureates, presented their work. It's not an official award ceremony. It's before. But it was really nice and impressive. Okay, so then what else? So as I told before, the quantum mechanics explain nature, but especially quantum entanglement allows us to introduce what is now called, is also Alain's terminology, second quantum revolution. That is when you really are able to manipulate single atoms, single spin, single photons, then you reach this domain where quantum superposition, interference, entanglement are sort of completely evident. And they are not only evident, but they open the way to new methods to process and manipulate information carried by quantum objects. So this is what is called second quantum revolution. I will not tell more now because you will hear more today, especially this afternoon, about source of emitting individual photons, making quantum bits with superconductors, also with atoms. So there is a huge zoo of quantum technologies, quantum objects that are manipulated in this quantum domain. I have still a few minutes. Yes? 8. Oh, okay, plenty. I would like just to conclude, to come back to the basic motivation, I remind you, the basic motivation was a little bit philosophical. That is, what is quantum reality? What does quantum mechanics tell us about physical reality, and how does this differ from classical reality? So this was the motivation of these guys almost 1 century ago. So this is John Bell. So John Bell anticipated that his inequality would be violated. And so he tried to answer that what will happen if quantum mechanics is right, that is, if my inequalities do not hold. So he said, let us anticipate that quantum mechanics works also for aspect. It did. How do we stand? I will list 4 of the attitudes that could be adopted. The inefficiency of the counters and so on are essential. Quantum mechanics will fail in sufficiently critical experiment. So this is excluded by loophole-free experiments. So the experiment is as perfect as one can reasonably hope. So then another way to violate Bell's inequalities is to admit that despite all the precaution, actually there are instantaneous influence. There are influence going faster than light, even if we cannot control them for practical telegraphy. Nobody claims one can send information faster than light, but at the level of this supplementary parameter, there may be a non-locality. And it's not only fast, it's instantaneous. This was shown by Nicolas Gisin, who is here some years ago. Okay, this is an option. Another option is A and B, the orientation. We make a lot of effort to have this random choice on both sides. But one might claim that randomness does not exist. Everything was decided at the beginning of the universe by some big guy. And then we just follow those streams which are written somewhere. So the quantity are not independent variable, then Einstein local causality can survive, but apparently separate parts of the world become deeply entangled, and our apparent free will is entangled with them. In that case, there is basically no more free will. Okay, well, 4th option, the whole analysis can be ignored. The lesson of quantum mechanics is not to look behind the prediction of the formalism as a correlation. Well, that's quantum mechanics. So this is a famous shut up and calculate option. Okay, that's it. Okay, none of this is really nice. Well, so let's try to analyze them a little bit more. Okay, so there are influences going faster than light. So as I said, you don't violate relativistic causality, but you violate what can be called elementary locality. If you would have access to this supplementary parameter, then you would contradict relativistic causality. But since you don't, that's fine. So is it good or not? So this creates, obviously, a strong tension with relativistic causality. So personally, I don't like it. Because in this option, you cannot decide yet. They all violate Bell's inequalities. So sort of personal preference. So this one I don't like, but some people do like it. For instance, all Bohmian theory makes this choice that they have an explicit non-locality at the level of the hidden variable or the lambdas, previous lambdas. Okay, the quantity are not independent variable. Then you violate free choice. There is no free choice at all. Everything is predetermined. No randomness. Okay, nothing. Well, I don't like it either. I want some freedom to move this way or that way. But people think this is not true, and not any people. Gerhard Tuff is a Nobel Prize winner, and he has a whole theory where basically everything is written at the Planck scale, and there is no freedom. That is no freedom of choice, and that is we are just following an history which was written at the origin of the universe. Okay, the last one. So the shut up and calculate. So obviously, shut up and calculate is a caricature. If you dig a little bit in quantum mechanics, you can see that there is another way to violate Bell's inequalities, which is not related to locality, but which is related to predictive completeness. So actually, it amounts to tell that psi is not complete. But psi is not complete, it's just what Einstein was telling. So would that mean that Einstein was right? It's a little bit more subtle. So if you say that psi is not complete, how should you complete psi? So all the effort of Bell, etc., was to look on things which are behind psi, hidden variable. But actually, psi is always defined in a measurement context. You have to tell what you want to measure if you want to make sense of your psi. And this is another way to complete psi that people tend to call now contextuality. It has to be random also, but if you add contextuality, randomness, and tweak a little bit the thing, you can violate Bell's inequalities without appealing to non-locality. I think this is more or less admitted. Anyway, I wrote many papers on that that I will not describe in detail, but then psi has to be completed, indeed, but it has to be completed by specifying the measurement context. Actually, the real quantum stuff, quantum mechanics is not really speaking to you about systems. It's always speaking to you about system within a measurement context. And if you look at Bohr's answer, Bohr was telling what matters are the very conditions which allows you to make future prediction. And if you assume that, if you admit that these very conditions are precisely this measurement context, well, you are maybe not too far from, okay. Anyway, I'm thinking in this direction, but as I said, you cannot decide at that point, and there are many other options. Still, to conclude, there is a nice sentence that I like. Also, it can describe anything. A quantum description cannot include everything. And this is from Perez and Zurek, who are very famous people on quantum physics. Okay, almost last slide. Okay, so this is the truth. Quantum entanglement is experimentally validated by testing Bell's equality, and it is definitely non-classical. So from that, we can get many physical ideas leading to new theory, new experiments. Juin will speak about that also. There are also many applications on quantum technologies. One should remember that there is still behind this sort of philosophical ideas. So if you want to make a career in physics, and if you are not Alain Aspect, I would rather suggest to go here or there. But nobody forbids you to think about that. This is quite a strong simulation. What is nature? What is physics? What does it tell us about what is around us? And these ideas, I think, remain interesting. They are very difficult, so because many people already thought about them. But I still think they are stimulating ingredient to think about physics. Okay, so all these things we, in some sense, owe to Alain. So this is my real last slide. Thank you and bravo, Alain.
So I'm taking over from Philippe as soon as I have my slides. And as Philippe, I would like to start by saying how happy I am and honored I am to speak at this special occasion. I would like to start where Philippe stopped, that is in 1982, and I would like to explain to you that there is a life after violating Bell's inequalities. The life is for Alain the college years, and this is what I would like to discuss here. So we are in 82, July 82. So the data from the last experiment, the third experiment, the one with the commutator, had been taken. We took them, I think, in May and June. And in July, we were both at Les Ouches Summer School, organized by Gilbert Grimbert. And so you see here Alain. I'm not sure what he's doing with the dog here, but I promise that no animal was injured for the shooting of this photograph. So we are going for a hike somewhere. And so, as I said, the data for the paper were in the box. So Alain was writing the paper in Les Ouches, and the paper was finally published in September, so 2 months after this picture. And the question was what to do next. The question for Alain, of course. And I remember quite well a Monday morning, where Claude came back from an assembly of Collège de France, which always takes place on Sunday. And Claude Cohen-Tanucci said that he was offered a position for a sous-directeur de laboratoire. One sous-director from another professor had resigned, or has retired maybe. And so there was a position, and Alain immediately said, what about getting Alain with us? And so this is indeed what happened. And Alain joined actually in 84. It's here. So this is an activity report from our lab for the year 83-84. So you see here the team that was at that time, with Claude here as a professor, leader of the team, and then Alain was here, and a list of people. So to do what? So Alain joined Collège de France, as you understand, And it's good to have this activity report. I mean, we hate the moment when we write them, but it's good when you read them 20 years later to see what we were about to do. So I can translate here for our non-speaking member of the audience. Nous sommes sur le point de démarrer au laboratoire un projet expérimental important. We are about to start in the laboratory an important experimental project. This project, which will be one of a major concern during the future years, will aim at slowing down and cooling a thermal beam of cesium atom. And we explained that cesium has been chosen because it has a heavy mass, and therefore once we will be able to trap the cesium atom, then it will be less sensitive to collision with background gas. And also we mentioned that there were some laser diodes at the wavelengths, for resonance wavelength. Remember, at that time there was no trapped atom anywhere in the world, so it was a challenge. Unfortunately, or actually fortunately, we were not obliged to write SWOT analysis at that time, but it would be interesting 40 years later, to see what we considered as a weakness of our approach at that time. But anyway, this SWOT analysis does not exist. One last word about this slide is that actually the group of Claude was quite remarkable at that time. As you can see, there are 4 name circles which all went to Stockholm. Roy Glauber was a visitor at that time. So for the people like me, it's really like standing on the shoulders of giants when you see that the activity report of that time. Okay, so we want to start an important experimental project, in quotes. So how do you manage and how do you finance such a project in the year 1984? So first you need a manpower, and fortunately Christophe, our chairman, joined us 1 year later. But in order to get the money, Christophe didn't bring any money. In order to get the money, we had no ANR, which is Agence Nationale pour la Recherche, no ERC, European Research Council, no DIM, that domaine d'intérêt majeur from the Région Île-de-France. And so the only way we found to get money was DRET. DRET was associated with the Ministry of Defense, and we got money from the French Army. We got 1 million francs, which is typically from today 300 kilo euro. And it paid for an argon laser, dye laser, vacuum pumps. And what we promised to the army was that we would improve cesium clocks, which were important, of course, for the army. And actually, it was not wrong. It was not a false promise. We did it. For the rest, we had to do bricolage. I don't know what is the English word for bricolage, but I'm sure you will understand it. We had to do really to invent things and do them. Do it yourself, exactly. Do it yourself. And we had 2 engineers who played an important role, Gerard Trenek and André Klucker. So we bought pipe from the petrol industry. We cut them in pieces of 1 meter, and we soldered some flanges, and then we could make a 5 meter long atomic beam. We had laser diodes, which we powered with car batteries that we were filling every week at the electricity department. And we had to build really everything ourselves. Here you see a copy of the lab book. So for those of you who know it, it's Alain's writing. This is how to deal with electricity issue in secondary pumps. I'm not sure, Alain, you remember this page, but I still have it. And Alain explains how to connect vacuum pumps and in order not to have short circuits and detect any problems. So Alain really did experiments, as you can see. Okay, so we got results relatively fast after this start. Here you have a copy of our 2 first PRL. One in 86 was cooling atoms with stimulated emission, and the second one in 87 was channeling atoms in a laser standing wave. These 2 papers are quite nice, actually. This one is really the ancestor of the Sisyphus effect. I'm not sure I like the title. Reading it now, I think it's really misleading. We needed also spontaneous emission to get cooling, but still, it's true that we were working at large intensity, so this was the ancestor of Sisyphus effect, but at large intensity, and stimulated emission was playing an important role. But in order to cool, we needed spontaneous emission. I may say a bit more words about channeling atom in a laser standing wave, which is really a kind of a precursor of optical lattices and sub-wavelength imaging. So what are we doing in this paper? So we had, as I said, a long atomic beam, which was very well collimated. And so let's say this beam is propagating along this direction, and we were applying a 1D standing wave perpendicular to the atomic beam. And so the kinetic energy of the atom the transverse kinetic energy was quite small. So when the atoms were arriving in this landscape of nodes and antinodes of the standing wave, the dipole force was pushing the atom towards the node where there was no intensity. And so we could have the atom channeled at the node of the standing wave and then emerge later. And in order to see that this effect was really occurring, what we were doing was absorption spectroscopy of the atom inside the standing wave. And because of simply the light shift, the resonance frequency of the atom at the node was not the same as at the antinodes. And we could see a relatively broad spectrum. The atom at the node corresponds to this peak. The atom at the antinodes corresponds to that peak. And indeed, we have more atom at the node than at the antinode. And we could even reconstruct the atomic density. So at the node, we have a large atomic density. This, it's periodic, of course. At the antinode, the density is divided by 4 or 5. So it was really a localization at the wavelength level. And here you have an example of a sub-wavelength imaging. We didn't sell it like that at that time, but it was an interesting example of that with a good resolution. But this was a cesium project, but Alain was not satisfied with one experiment, so he wanted a second one. And this was the start of the metastable helium project. So again, I look at the activity report, so now it's 2 years later, and we explain that we are going to start an experiment with metastable helium. And we explain why metastable helium is interesting. So it is interesting because you can measure the fine structure constant. We never did it, but anyway, this is the claim we had. We said that it was very nice because it was a low mass. We had just used the reverse argument for the cesium. Never mind. Something which is more important and still true now, we said that it could be either a boson or a fermion, whereas cesium was purely fermionic. 133 cesium is a boson, and there are no stable fermionic isotopes. For the helium, for the helium atom, you can have boson and fermion, and this is still true today that it's important to have the two isotopes. So already at that time, we were thinking of quantum statistics, even though we were not claiming that we would go to boson-chain condensation. And also a practical reason for choosing helium was that in the laboratory, in the group of Franck Laloé and Michel Leduc, they were used to work with metastable helium, and they had developed laser sources at 1.08 micrometer, which were very useful. Of course, you don't need just a laser source. You also need an atomic beam. And there, Alain borrowed an atomic beam from Helmut Haberland of Freiburg and used this homemade laser. And then we hired the first 2 PhD students on the experimental project, Nathalie van Senkist and Robin Kaiser. Robin, I've seen him. Maybe Nathalie is also in the audience. This is a picture of the group at that time. So here you see Bill. Here you see Bill, who was a visitor, Alain, of course, Claude. Nathalie and Robin are here. Christophe Salomon, our chairman, is here. Hal Metcalf was also a visitor at that time. Okay, so it's a nice picture taken 87. Now, 87 is the start of what I call the subrecoil cooling adventure. For me, subrecoil cooling is probably the most elegant cooling mechanism that has been invented. It's not the most used by far, but it's probably the most elegant one. And I can say it because I did not participate into this adventure. And metastable helium had not been chosen for this application. It had not been chosen for subrecoil cooling, as you have seen on the previous slide, but it appeared to be an ideal tool for subrecoil cooling. The first thing is that there is no hyperfine structure, at least if you work with a boson, helium-4, there is no hyperfine structure, so it's a simple closed transition. You don't have to worry about optical pumping process to other hyperfine states, which would spoil the effect. Then it has a J=1 ground state, capital G, that is written here, and a J=1 excited state, capital E, which is written here. And so, actually, this gives a perfect realization of a lambda level scheme, which is needed for subrecoil cooling. So G has 3 Zeeman sublevel, -1, 0, +1. Same thing for the excited state. But if you start from one of the 3 states, -1 ground state, +1 ground state, or m=0 excited state, then you will always stay into these 3 states. You will never reach the 3 other levels, excuse me, written with a dashed line. And the reason is that when you reach the excited state here, it cannot decay from m=0 to m=0. The branching ratio is 0. So if you start from here, you will excite the atom here, and then the atom from here will decay by spontaneous emission either in -1 or +1. So perfect lambda scheme. Second good reason that it is well, second and third good reason for having this atom good for subrecoil cooling is that it allows you to have a superb combination of quantum interference, Doppler effect, and Brownian motion. And I can explain this in a few sentences. Let me start with quantum interference. When you have this lambda scheme here, then you can have a dark state. So the reason is that if you have an atom at rest, and if the intensity of this wave here and that wave here, sigma plus and minus, are exactly equal, same detuning, same intensity, then the antisymmetric combination between -1 here and +1 here, G m equal +1 minus G equal -1, is stable, in the sense that there is a destructive interference to excite the m equals 0 state here, because you have opposite amplitude to go from here to excited state and go from here to excited state. So you have a dark state. If the atom is at rest, that's nice. Second ingredient, suppose now that the atom moves, and suppose that your two laser waves are counter-propagating. So if the atom moves, it will not see this wave and that wave with the same frequency because of Doppler effect. So if the atom is moving, then the destructive interference that occurs for an atom at rest is broken. So the atom will eventually absorb a photon, go from G to E, and when it is in m equals 0, what happens? Then you may have a spontaneous emission. The spontaneous emission gives a random kick to the atom in a random direction, and therefore the atom will start again with a different velocity, ask whether am I at v equals 0, in which case I will stay at rest, or am I at non-zero, velocity non-zero, and therefore I will again try. So you have a combination of these three effects, which leads to subrecoil cooling in the sense that the atom will accumulate in the velocity class v equals 0 if you wait long enough. So this was published in 1988, and it's probably the kind of world record in the fastest published paper in PRL. Maybe it's not the fastest, but probably close to the fastest. As you can see, it was sent by surface mail. No internet at that time. It was received by PRL on the 11th of July. Then PRL has to choose referees, send the paper to referees by surface mail. The referees had to answer by surface mail, and then they had to compose the paper, of course, because I mean, it was not a tech file at that time. Okay, it was just a manuscript, and still the paper was published less than 5 weeks later. So that's really remarkable. I think nowadays it's not possible. Okay, so that was the first demonstration of subrecoil cooling, and then Alain and colleagues with François Bardou, Olivier Emile, Alain Aspect, Claude Codanucci, Jean-Philippe Bouchot, they realized that there was involved in this cooling some very subtle statistical physics mechanism. By very subtle, it means that the random walk that I was just describing is dominating by some very rare events when the atom reaches a velocity v, which is very close to v equals 0. V equals 0, strictly speaking, is a zero measure ensemble. So the atom is never at strictly v equals 0. But when it is very close, then it can stay there for very long. So this is a random walk, a Brownian motion, dominated by a very rare event. And this gives rise to some nice statistical aspects called Levy flights. And there was even a book published on that with François Bardou, Jean-Philippe Bouchot, Alain, and Claude. And then this mechanism was even extended from one dimension, as initially in 1988, to 2 dimensions in 1994. But now, as you can see, there is a little cross in front of the name of Alain, and this little cross means that he is back to Institut d'Optique. So this is the end of the college year, this last paper. I think it's the last paper you wrote at Collège de France, back to Institut d'Optique. As we know now, Alain doesn't walk anymore. He has a limousine. So in 40 years, he went from this walk here to this nice limousine. Annie is present. I'm very happy to show this picture of Annie, taken, as you can imagine, a few months ago. So thank you again, Alain. Congratulations, and good luck for all your new adventure. Thank you.
Merci Jean pour l'évocation de ces souvenirs. Mais il y avait beaucoup de travail derrière ça. On n'a pas fait que s'amuser. On s'est beaucoup amusé au labo. Tu n'as pas montré une slide que tu avais montrée dans certaines expériences auparavant. C'est Claude Coentanucci qui tournait la vis pour prendre les données et l'écrivait dans le cahier de labo pour le papier.
J'aurais un commentaire à faire à ce propos, si tu me donnes.
Oui, on va prendre les questions d'abord. Hein. Je te les donne. Merci d'avoir tenu le temps pour les deux orateurs. On va commencer par prendre les questions dans l'autre salle, si ça ne vous ennuie pas. Avez-vous des questions dans la salle 2 ? Ils sont timides ? Non, c'est pas possible. Ah, voilà. Est-ce que vous avez des questions ? Bon, alors ils sont timides. Alors on va prendre les questions dans la salle, dans cette salle ici, sur cette époque historique. Oui, on ne va pas commencer par Bill. Alors. Allez, Bill, une question alors.
So the question has to do with the talk that Philippe gave, but I think I want answers from both of you. So you pointed out that after the EPR paper of 1935, that the general feeling was that the issues being raised were philosophical, and that changed completely with Bell, because Bell presented us with something that was clearly testable. Now, today, in a certain sense, we have a similar situation. We have these various interpretations of quantum mechanics, which, for the most part, predict the same things. So they're almost by definition philosophical, which does not mean unimportant, but just means in this context not testable. But of course, there are some interpretations of quantum mechanics that are testable, and then we might even imagine that some of the interpretations of quantum mechanics that appear to be philosophical today might turn out sometime later to actually be testable. So what I'm wondering is whether, because I'm sure both of you have thought about this far more carefully than I have, I'd like to hear some of your thoughts about that idea.
Yeah, so if you go to quantum foundation in general, the one I have listed are sort of non-testable presently. They have very different philosophical, ontological implications, but there are other approaches like what people call wave collapse. That is, you add a nonlinear term in the Schrödinger equation, for instance, and this is likely to be testable because we have now this entangled massive object. So there are some coupling with gravity, and it's not impossible that one reaches a regime where experiments can be done, where one would exclude or confirm this kind of nonlinear collapse theory. But this is, in this case, these theories are really different from quantum mechanics. They have different predictions, so these different predictions are testable. Difficult to test, but testable.
That's sort of thing that Penrose was.
Yes, Penrose type of thing. But there are, for instance, experiments related to experiment in Vienna. There are many experiments that you try to make interferometers with massive objects, basically. This is your idea. And then this may open a way to test these alternative theories. The one I quoted, presently, it would be a great achievement if there was a way to discriminate them experimentally, but it's not possible. It's more at the conceptual level. So, yes, so maybe, Jean?
No, I don't have much to add. I think indeed, for me, the new frontiers would be including gravity in an intelligent way. I mean, not simply looking at the atoms falling, but testing really something that discriminates between one theory and the other. There is indeed this experiment in Vienna. I'm not sure that it will test, as it is designed, it will test something that will revolutionize physics, as Bell's inequality have. But I think that's probably where the new frontier is, yes, because we have a big gap in our understanding of the physical world anyway. So it's,
There is an ongoing controversy, for instance, about proving the quantum nature of gravity in an interferometer. But probably you know these experiments. Alain, you have your own opinion on that. I'm a little bit mitigated, but many people think that it's a little bit related to this idea that you couple a quantum object and the classical object, then if for consistency, if you are in the quantum regime, both of them have to be quantum. This was all discussion about my PhD about the quantum nature of light. The trouble is that with graviton, we cannot do what we do with photons, and this is still a limitation.
Yes. Thank you. Alain, you wanted to say a couple of words? we take a second and last question because time is passing, flowing. Any question in the room? So we take Alain a comment, and then we move on to the next talk.
Okay. I want to make a comment about Jean presenting the channeling, okay, the atom channeling in a standing wave. We were in the lab at night, and you mentioned Claude Cohen-Tanouji, and he was there. And you say he was turning knobs, but in fact we wanted to avoid him to turn knobs. Okay.
I was turning the knob. He was writing the number.
So we asked him to be on the logbook and to take notes of things. Okay. But Claude took the initiative, in addition to noting the numbers, to make a graph. And on the graph, there was a continuous curve as a function of the velocity, okay? But in the middle, there was a point which was not at zero. And so Claude very carefully showed that the point is not where it was expected. And we began to joke with him, say, look, Claude, you should only do theory, you know? Even for plotting points, you fail. And actually, that point was the point which was showing channeling. So I am happy. Happy to say these few words for this good time we spent with Claude, who unfortunately could not be here today.
Thank you, Alain. Okay. So let's thank the two speakers again.
It's a pleasure to be here to honor Alain. The character of my talk is a little different from what you've heard so far, because I'm not going to talk so much about things that Alain has done, but talk about things that I think will please Alain to hear about, ways in which quantum mechanics are coming into aspects of physics that in the past were purely classical. So I'm talking about the quantum revolution of the Système International d'Unité, or the SI. And I just want to remind people that I'm from the Joint Quantum Institute. We like to remind people that quantum is our middle name, and part of the laser cooling and trapping group. And I'm very pleased to mention that Gretchen Campbell is now the leader of that group, which I started many, many years ago. And I'm so happy because she does a much better job than I ever did as the leader of the group. And Paul Lett, Trey Porto, Ian Spielman, Ida Tiesinger, Charles Clark, Paul Julian, and Nicole Younger-Halpern are also members of the group, some of them emeritus. I also want to remind, especially to the young people who are here, that the International Union of Pure and Applied Physics has been a major force in the development of the SI, and I'm in part representing that group in spreading the word about the quantum reforms to the SI. So we're here to honor Alain in speaking about quantum physics. There was this wonderful event in Stockholm when the Nobel lectures were given. Everyone agreed that Alain's talk was the best of the talks. And at the ceremonies, physics comes first, and the laureates come in led by a student and led by Alain, who the alphabet helps him in being the first of the physicists to come in. But if Alain was the star of the lectures, it was Annie who was the star of that evening, and of course. I've always thought that one of the important features of someone's career is the students that they have produced. Not bad. And, and this represents only a fraction of the students. By the way, I just realized I have to apologize for the way I'm dressed. United Airlines didn't deliver my baggage at the same time it delivered me. I think I'm required by law to say that when I mention a commercial operation, that it does not imply that the United States government approves or endorses. Did I say United lost my bags? And so I'm here in blue jeans and tennis shoes to give this talk, which is not the way I would have hoped to have done it. So not only colleagues and students, family was there for this wonderful occasion. Of course, sometimes students become family, and this is a particularly beautiful feature. And of course, this kind of celebration is so sweet, and here we are continuing that celebration in the way that physicists always celebrate things. We have a symposium. What could be better as a way of celebrating things? So I'm telling you about the quantum revolution of the International System of Units. We're talking about quantum physics from foundations to innovations, but the question comes up so often in these matters, just what is quantum? As we heard from Philippe, in the 20th century, there was a view of what was quantum that had to do with things like wave-particle duality, whether H-bar appears, and the revolution that I'm going to talk to you about is certainly part of this 20th century version, but in the 21st century, we emphasize features that were well known, of course, in the 20th century, superposition and entanglement. But now we put those features to work in ways that have not been true in the 20th century, and that part of the revolution is going to use and enable some of that. Some of that feature of quantum mechanics, that is the quantum revolution to the SI. But for the question of just what is quantum, I'm going to take the attitude that a US Supreme Court justice took toward obscenity. What he said was that I don't know how to define it, but I know it when I see it. I'm particularly happy with this photograph that I think blends the 20th and the 21st century features of quantum mechanics. We have Messier and Alain and John Bell. This already happened in 1984, but I think shows the kinds of connections that we're interested in. Okay, so what is this quantum revolution that I'm speaking about in the International System of Units? Well, as I think many of you know, the metric system came into being with the French Revolution at the end of the 18th century. And on the 20th of May, 2019, which I'm sure you all know is World Metrology Day, because of course we all celebrate the 20th of May because of it being World Metrology Day, that we have experienced on Metrology Day of 2019, we've experienced the greatest revolution in measurement since the French Revolution. And the nature of that revolution is to change the way in which we are defining the base units of the International System of Units. So this illustrates basically our modern metric system is based on the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela. And all other units, things like the joule and the Newton, are based on these. And this wheel here is something I'm wearing on my lapel, and I'm going to give it to Alain as a gift so that you can also promote the new SI. This is a NIST thing. And the point that I'm going to be talking about is that today, every one of these base units of the SI is defined by fixing the value of a constant of nature. Now, in order to illustrate how it is even possible to do that, I want to recall an older instance in which this happened, with apologies to Stephen Hawking, to give you a brief history of time. The second, for a long time, has been a certain fraction of the day, 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute. So that's what a second is. The problem is, what is a day? Well, for one thing, the solar day changes during the year, but you can average that out. So we refer to the mean solar day. But since around the turn of the century, not the last one, but the one before that, we've known that the day changes. The tides slow down the rotation of the Earth. The earthquakes redistribute the mass, changing the moment of inertia. Ocean currents change, changing the distribution of flow of mass. And so we knew this even before we had atomic clocks, which are far better than the Earth. And in order to fix this problem, there was a redefinition of what was meant by a second. So instead of being a certain fraction of a day, the second became a certain number of oscillations of the hyperfine frequency of a cesium atom. So here's a picture of one of the first cesium clocks at the National Physical Laboratory in the UK. And this is a clock which uses the features that we associate with the second quantum revolution. The cesium atoms are state selected. They go into a microwave cavity where they're put into a superposition of states. That superposition, in a sense, is a ticking clock. And the measurement of that ticking clock is the thing that produces the time standard for the country, for the world. Each country has their own cesium clocks. Laser cooling has improved the performance of these clocks. Here is one of the French clocks, in fact, a double rubidium cesium fountain. So this has to do with the promise to make better cesium clocks that Jean mentioned, and indeed you did. And Christophe has had a lot to do with this creation here, and I won't go into why rubidium is so wonderful in addition to cesium, but the key concept here is that we've gone from something that is basically an artifact. The rotation of the Earth is nothing special, nothing tied to the way in which the universe works, to the property, the quantum property of an atom, the cesium atom. The energy levels of that cesium atom are determined by the laws of quantum mechanics, and quantum mechanics also guarantees that all the cesium atoms are the same. So that is something of the spirit of what I'm going to be talking about. Now, there's an even better story, so here's a short history of length. The original standard of length was the human body. And this was wonderful because, you know, a foot was a foot, and you know, a yard was the distance from your nose to the end of your fingers. And the great thing about it was you always had your standards with you. The problem with that is that everyone had a different standard, and you know, if you were buying fabric from a short fabric merchant, you might not get what you expected. So one solution to the problem was to fix it to the body of a particular person, often the monarch. In ancient Egypt, it was the pharaoh, and the royal cubit, that's not quantum bit, but just the distance between your elbow and your fingers, is the standard definition of a cubit. And so the pharaoh's forearm length became the standard, but of course it was still somewhat inconvenient because you didn't always have the pharaoh nearby when you were measuring the pyramids. And so they made an artifact, something very modern. They made a cubit out of stone, and the people in the field were using secondary standards that were made out of wood. They had to recalibrate them every month, and the penalty for not recalibrating was the death penalty. These people were really serious about metrology. So artifacts like that abounded, and all over Europe you had artifact length standards that were essentially set in stone for that town. And here it looks like this would be a good place to buy fabric because the fathom is quite long. But if you were to go to other nearby towns, you would have a different set of length standards. Well, the French Revolution decided they were going to take care of that. They were going to produce a standard of length that would be good for everyone, for all time and for all people. So the meter was defined as 1 over 10 million of the distance between the pole and the equator on a meridian, just to make sure it was completely universal on the meridian that goes through Paris. So they sent out surveyors to achieve this thing. This medal was cast to emphasize the idea that this would be a unit of measure that would be good for all time, for all people. You see, this mythological creature is actually measuring the Earth. That's what they did. They sent out Delambre and Mequin and their teams to survey the distance between Dunkirk and Barcelona, and they were constantly being thrown into jail because there was a war going on. But they got the job done. They brought the measurements back, and of course, this was wonderful. They now had a new meter, but you couldn't go and survey the Earth every time you wanted to measure something. So what did they do? They made an artifact. So here is a picture of the meter of the archives. Deposited in the archives of France in 1799, it became the official length standard for France and for other countries who began to adopt the metric system. And in 1875, the countries of the world gathered together and agreed upon an international treaty, the Convention de Mètres of 1875, and signed it on the 20th of May, which is why the 20th of May is World Metrology Day. I think there were 17 countries around the world who signed this, agreeing to support the International Bureau of Weights and Measures, the BIPM, and to maintain their own standards of measurement metrically. One of those countries was the United States of America. So we have been metric in the United States since the 19th century, in fact, even earlier. So why we still use inches and pounds? I don't know. But legally, we've been metric for well over 100 years. Almost 200 years. Okay, so 1875, they made a new meter to replace the meter of the archives. This was a line standard made to be as close as possible to the meter of the archives, and it became the meter for the entire world, an artifact. But this is 1875, and it's France, and people have realized that light is a wave, and that you can make interferometers. Here's a cartoon version of a Michelson interferometer. Michelson was the first one to compare the wavelength of light to the meter standard at the BIPM using his interferometer. And the point was that you move this mirror by a half of a wavelength, a quarter of a wavelength, and it changes the interference from being light to dark, and that's something like 2/10 of a micron, and the scratch that is on the meter bar is 20 microns wide, and so pretty soon people were using light to measure length and ignoring the meter bar because light was so much better. So you had a situation where there was a better technology, namely interferometry, and then the standard that defined what was meant by a meter, and people were using the wavelength of cadmium as a de facto standard. It took a long time for the very conservative metrology community to change the definition, which clearly needed to be done, and they changed it to the wavelength of krypton. In 1960, the year that the laser was invented, they decided that a lamp would be well, remember, lasers weren't so good in 1960. So they decided that the lamp was the right way to go, and that became the new definition of the meter. But it didn't take long before people made things like iodine-stabilized helium-neon lasers, which became the de facto standard of length. Again, we had technology that was better than the definition of what we meant by length. And everyone used the wavelength of lasers like this as their de facto standard of length. It was clear that you needed to redefine the meter again. And the obvious thing to do would have been to redefine the meter as being a certain number of wavelengths of the light from a a helium neon laser stabilized to a molecular transition in iodine. But fortunately, they did not do the obvious thing. They did something beautiful, and that was to define the speed of light. The definition of the meter now became the distance that light travels in vacuum in a certain length of time. And making the definition that way is essentially defining the speed of light. And the beauty is that if you can measure the frequency, and they had just learned how to do that really well in 1983 when this definition was changed, if you can measure the frequency and you define the speed of light for any light source that you want, you know what its wavelength is, and therefore you have a ruler. And when people made better lasers that had a more pure wavelength, when they developed methods for measuring the frequency of light better, and people like Jan Hall and Ted Hench, who got the Nobel Prize in 2005, did those things, they were automatically already incorporated into the definition. And so this is the real beauty of what's happening, is that we started from an artifact, went to a quantum standard, and finally to a fundamental constant of nature. And the beauty of this is that unless we completely change our ideas about how we're going to measure length, we should never have to change it again. But we might also ask the question of whether it's still quantum. Well, I assure you that, of course, all the ways in which we realize this definition are very quantum, but the definition seems to be a little bit more classical. But now we have this beautiful definition of the meter. And the real message of this talk is that on the 20th of May, 2019, we brought that same beauty of defining a unit using a fixed value of a fundamental constant. We brought that to mass, to the kilogram, and to other features, other aspects of the International System of Units, the ampere, the Kelvin, and the mole. Well, why was it necessary to do this? What motivated it? And how was it done? Well, for that, I'm going to give you a light history of mass. Here's a picture of some Babylonian stones that were used to measure, for example, precious metals. One of these stones is called a shekel. And the problem was the same problem you have with any artifacts, is that they would vary from one place to another. So the French revolutionaries had a solution to this as well, using the meter, which was going to be the measure of all things for all people and for all time. They made the kilogram the mass of 1 liter of water, 1 liter being a cubic decimeter, 1/10 of a meter on a side. But the problem was it wasn't that easy to get a liter of water. All sorts of problems. You know, there's the composition, there's the density, there's the way in which water wets or doesn't wet different materials. And so guess what they did? They made an artifact. And here I am actually handling, well, the case of the meter of the archives. In 1799, they made a platinum cylinder, which was as close as they could measure, equal to the mass of 1 liter of water, and deposited it in the archives, and there it is. That was really quite an amazing experience. 1875, the countries of the world agreed to create another artifact. Here it is, under 3 glass domes. We have the international prototype of the kilogram. This, in fact, was the last artifact. This was the standard of mass for the entire world from sometime in the late 19th century until just a few years ago. Now think about this. We're in the 21st century. Our mass standard is an object that was made in the 19th century, based on an object that was made in the 18th century. This is scandalous. If someone leaves a fingerprint on the international prototype of the kilogram, all of you would lose weight. Not in a way that helps your health. Now, nobody has left fingerprints because they're very careful, but it appears that the mass of the international prototype of the kilogram is changing nevertheless. Here is a plot of the mass of the kilogram relative to similar copies of the kilogram that were made at the same time. They were all made in exactly the same way. They chose the one that was closest to the mass of the kilogram of the archives, calibrated the differences, and this shows how they changed. Every few decades, they would take it out and measure it. Okay? I mean, it gives you some idea of how convenient it is to have an artifact. They only measured it every few decades, and it's pretty clear that something is changing. Doesn't take too much imagination to imagine that if all of the copies are going in one direction, perhaps it's the kilogram itself that is changing. But of course, it cannot change, because by law, it is a kilogram. Well, so this is scandalous, and it had to be fixed. And we wanted to fix it in a way that was similar to this beautiful way in which we fixed the problem with the meter. We want to define a constant of nature. Well, which constant shall we use? Well, I'll remind you of what I'm sure is the most famous equation in history. It tells us the energy of an object at rest is its mass times the square of the speed of light. And one not quite so famous tells us that the energy of a photon is Planck's constant times the frequency of the light. So let's just put these two equations together without thinking about it too much and solve for the mass. And you see that, imagine what we have is a particle like an atomic nucleus, and it emits a gamma ray. And we can measure the frequency of the gamma ray. Because we know the speed of light, we defined that back in 1983, if we are willing to define Planck's constant, then we know the change in mass of that nucleus. And this gives us the change in mass of a nucleus in kilograms if we're willing to redefine the value of Planck's constant. Now, we're not actually going to weigh photons. We could, but not quite well enough. Maybe sometime in the future we will do this better. The beauty of this definition is that it doesn't tell us how we have to realize the kilogram. But what we're using now is something that I think will please Alain very much, although I'm sure he already knows about it. We're going to use an atomic physics way of determining the mass of an atom, of an individual atom, in kilograms. We're going to use atom optics, one of Alain's favorite subjects. Okay, so imagine I've got an atom at rest, and it's in the ground state, an electronic ground state, and I send in an optical photon to excite it to the excited state. Well, the energy of the photon is absorbed, the atom goes to the excited state, and the momentum of the photon is absorbed as well, and the atom recoils with a velocity that's given by the momentum of the photon, h over lambda, where lambda is the wavelength of the light, divided by the mass of the atom. So the mass of the atom is now measured. If we can measure the recoil velocity, it's given by Planck's constant divided by the recoil velocity times the wavelength. Measuring the wavelength is easy to the level that we're interested in. I didn't tell you what the scale was, but we're talking about kilograms that are changing by many parts in 10 to the 8th over time. Okay, so this is, a part in 10 to the 8th is what we want to shoot for, and it's easy to measure the wavelength of these things to a part in 10 to the 8th. You can do it to a part in 10 to the 11th or a part in 10 to the 12th. Now, the way in which this is done is using atom interferometry, and I wish I had time to explain how the atom interferometer works. It's so beautiful, but I don't. So here are some of the things that I'm leaving out, not telling you about what's done. So we actually keep the atoms in the ground state. We make things independent of what the initial velocity is, so the atoms don't have to be at rest, but laser cooling and Bose-Einstein condensation make that velocity width small. Originally, this was done in the lab of Steve Chu, and the best measurements are being made here in France in the lab of Pierre Cladet and Saida Gulati. in fact, depending on how you interpret the results, you can get the fine structure constant out of this. So your promises of making the fine structure constant, well, just a little bit different. But in fact, what I want to do is interpret this as measuring h over m, which of course, if you define h, means you've measured m. And I want to emphasize this, in kilograms. We know what the atomic masses of things are relative to, say, carbon-12 to very high precision. But that's in atomic mass units, not in kilograms. Now we know what the mass of, for example, rubidium atom is in kilograms. Now, how are we going to go from there to a kilogram that we can actually use? And this is the answer. This is the most spherical object that has ever been made. It is a sphere of single crystal, isotopically pure silicon. And the PTB, the German Standards Laboratory, has been the leader in doing this. This thing is so round that it's, the degree to which it's out of round is measured in tens of nanometers. It's the roundest thing that's ever been made. And it's a single crystal, and with X-ray interferometry, you can measure the lattice spacing to the same kind of level that you can measure wavelengths, because you're using optical wavelengths to do this. And so if you know what the spacing of this is, and if you know what the lattice spacing is, and you know what the dimensions are, and you measure the dimensions interferometrically, then you know how many silicon atoms are in there. And because we have all these wonderful historic ways of comparing the mass of silicon to the mass of rubidium, well, it's done in a chain using a lot of carbon compounds, but those can be measured to parts in 10 to the 10 or parts in 10 to the 11. So that means that we now know what the mass of this object is, and it's not an artifact. You could tell anyone what the process is for making this, and they would be able to create a kilogram, as opposed to you couldn't tell your colleagues on Mars how to make a platinum kilogram, but you could tell them how to make a silicon kilogram because of the fact that you've used the fundamental characteristics of these features. Well, this just tells what I've already said, and that's not the end of the story. One of the beautiful features of defining the kilogram in this way is that we are not told how we must do it. And this gentleman, Brian Kibble, figured out a way of determining a kilogram, realizing the definition of the kilogram, that is making a kilogram, using an electromechanical device which is called a Kibble balance or a Watt balance. And now I'm looking at my time, and I've got plenty of time left. So maybe I will show you a little bit about how the Kibble balance works. Okay, so let me run this movie. Okay, great. So first I want to invite you to remember how we measure mass typically. If we have an unknown mass here, we put known masses on the other side of the balance until the balance balances. And that's how you've measured mass since you were in elementary school. By using a standard balance. Now, you could have used a different approach. Let's see if this will now. Okay, right. Now I want you to imagine a different approach. Instead of using standard masses, on the other side of the balance, we have a coil of wire with some current in it, and we have a magnetic field created, in this case, by permanent magnets. And by putting the right amount of current into the coil, we can calculate using the equations of electromagnetism how much force there is, and this will allow us to measure what the unknown mass is. Now there's a problem, and the problem is that we would have to know where all the current goes in the wires, which is really hard to do when you've wound various layers of wire on top of each other, and we would have to know the magnitude and direction of the magnetic field, which is very hard to do. Here's where the genius of Kibble comes in. What Kibble says is, great, we're going to make another kind of measurement. We're going to take that coil of wire, And we're going to take the leads of that coil and connect it to a voltmeter. And now we're going to move the coil in the magnetic field, and that will generate a voltage. This is the way generators work, okay? But if you measure the velocity at which the coil is moving, and you measure the voltage generated, you get all of the information that you need to have about the geometry that is difficult to get if you wanted to measure where the wires are and measure where the what the strength and direction of the magnetic field is. Now you do the other part of the measurement where you weigh, that is, you put a certain amount of current in there and you see how much current is required to balance your other mass. And now you've got these two parts of the experiment. The one where you weighed it and the one where you measured the voltage. We call that the weighing mode and the velocity mode. And you put those ideas together. So you see we got the mass times gravity, that's the force from the weighing mode, times the velocity from the velocity mode. So we put those two things together, that's a mechanical power. We get the current from the weighing mode and the voltage from the velocity mode, again, from two different parts of the experiment. The product of those things is electrical power, and in a proper system of units, mechanical power has got to be the same as electrical power. So you just solve this equation for the mass, and here's where quantum comes in. You measure the voltage and the current using the Josephson effect, which is in Hertz per volt, and the quantum Hall effect, which is in ohms. So you put a certain amount of current through a resistor calibrated according to the quantum Hall effect, measure the voltage using the Josephson effect, and when you do all of those things, the charge of the electron drops out, and you get the mass in units of Planck's constant. So that's the Kibble balance. Let's see. I realize that I've glossed over a lot of things, and I'm going to have to gloss over even more things and get to the final point is, using both this silicon sphere method and the Kibble balance method, laboratories all over the world measured Planck's constant. Because, of course, we had not yet defined Planck's constant, so using the kilogram that we all had been using up until then, they were measuring Planck's constant. The idea, of course, was to eventually turn that around and define Planck's constant and use that to make a kilogram. So when all of these countries all over the world agreed on what Planck's constant was, then they took that value of Planck's constant and made that the defined value of Planck's constant, and that then produced the new definition of the kilogram that we use today. And at a meeting held not very far from here in Versailles in 2018, the countries of the world, 60 countries now, who are signatories of the International Treaty of the Meter, gathered together and agreed unanimously that they would adopt this new definition of the kilogram as well as of other units. And this is the movie they played after that unanimous vote. So I hope it will start. Please start. It worked fine in practice.
It took more than 140 years.
Groundbreaking science.
And the agreement from the world's scientific community.
At times, it seemed
impossible.
Accurate.
Precise measurements.
Anytime.
Anywhere. But
we did it.
Ce l'abbiamo fatta.
Wir haben es geschafft.
Lo logramos.
Lacey Aboli.
我们做到了.
Biz buna nail olduk.
Proud om die.
We zijn жасадық. Het is ons gelukt.
We сделали это.
انتصرنا.
We gjorde det.
Америка дьявол.
我们成功了.
Mi smo to učinili.
Dokázali jsme to.
Angažnáha.
سويناها.
Congratulations. 축하합니다. Felicitaciones.
Mazal tov. Congratulazioni.
Shate relevoricha.
Selamat sukses.
Parabéns.
Ongera. Omedetou.
Kamu kuyuda.
Onneksi olkoon.
Mabruk.
Kapai.
Aiko.
Félicitations. Congratulations.
Well, when I see that, the fact that 60 countries could agree on something unanimously gives me hope that maybe, maybe things can get better in this strange world in which we live. Well, okay, that was just part of the story. Perhaps the most important part was the change to the definition of the kilogram, a very quantum definition since it defines what Planck's constant is. But that's not the end of the story. The old definition of the ampere actually is quite beautiful. It says that the ampere is the current which, when put through two infinitely long straight wires of negligible cross-section 1 meter apart, will produce a force of 2 times 10 to the minus 7 newtons per meter of length. And you all learned that when you were school children, right? And effectively, and this may not have been emphasized to you, effectively this definition of the ampere defines what we mean by the magnetic susceptibility of free space, mu naught, which is 4 pi times 10 to the minus 7, I forget what, newtons per ampere squared. So in a sense, this was already one of the beautiful definitions. The ampere was defined by defining a fundamental constant of nature. It's just that the definition was really, really hard to use because you had to measure these forces. The new definition of the ampere is specifying the charge of the electron. So I contend that this is a very quantum definition because the quantization of charge is one of the most fundamental things that we have, and this is now the number of coulombs in an electron, so the current becomes something really beautiful, a certain number of electrons per second. What could be better than that as a definition of current? But of course, well, I shouldn't say of course, we don't count electrons. I mean, we're working on that, and it may be that one day that we will in fact realize the ampere by counting electrons. But today, you see the beauty of this is that with H defined and E defined, 2E over H and H over E squared are exact in the International System of Units. And so we can use them to make electrical measurements. Now, here's something that very few people know, and I'm going to reveal to all of you, a dirty little secret about electrical metrology. Since a very long time, more than 100 years, we have had two separate kinds of electrical units. We have had the SI, and we have had the legal units, which are maintained in a completely different way because it's so hard to use the SI definition of current. The legal definition for many, many years was that voltage was the average of a bunch of batteries, the voltage of a bunch of batteries that were kept at a constant temperature, and that resistance was the average of a bunch of wire-wound resistors. Now those were chosen, those values, 5 minutes, were chosen, 0 minutes. Wait a minute. No, it says 41 minutes. And no. 41, and then I have questions, right? Both of us know how to measure time. Anyway, so for a long time we had this other way of doing things, and now they're the same. Now we no longer have a legal and an SI way of doing things. And furthermore, we now have a new definition of the mole. We've done that by just defining Avogadro's number. The Kelvin is now defined not by defining the temperature of the triple point of water, but by defining the Boltzmann constant. Again, a really atomic and quantum way of looking at what we mean by temperature. And so we finally have done what the French revolutionaries wanted to do. We've got something that's good for all time, for all people. We're now, liberally leading the people now tells us that we're free of artifact standards of measurement, and we're free of this double standard of electrical measurements. We've defined all of the constants by fixing the value of all of the base units, by fixing the value of the constants of nature, except perhaps for time itself. And The SI second is still based on a particular atom, and we now have better atoms. Optical frequency standards. Christoph is working on this and is part of the discussion, as I am, for what the new definition of the second will be. And so, as for the future of time, only time will tell. Thank you very much. Now, my tradition is that everyone who asks a question gets a prize. I don't want to take up the time to give you the prize, but if you see me afterwards, just tell me about the question you asked, and I'll give you a prize.
Thank you very much.
Yeah. Well, so if the fine structure, yeah, so the question is, what if the fine structure changes, what if the fine structure constant changes in time? And of course, you know, that's already been tested at levels of a part in 10 to the 18 per year. It doesn't change, apparently, at least according to the models that are used to interpret the experiments. So if it did, it's going to be at less than a part in 10 to the 18th per year, and no one will care. But from a philosophical point of view, it's a very good question as to whether we are doing something valid in defining these constants. Now, let me make the following point. We cannot define the fine structure constant. The fine structure constant has no units. So we cannot, by redefining our units, we can't define what the fine structure constant is. Now, you might say, wait a minute, you defined E, H, and C, that's the fine structure constant. No. In the SI, the fine structure constant has a 1/4 pi epsilon naught. And so we have defined all of those things, but we have not defined what epsilon naught is. Before this reform, epsilon naught was defined, and we didn't have E and H defined. Now we've switched that, but there always must be something in the fine structure constant that is open to measurement. So today, if you measure the fine structure constant, you're measuring epsilon naught. Before 2019, if you measured the fine structure constant, you were measuring some combination of E and H. But as to philosophically what that means, I'm not sure.
Thank you. Somehow we are all gathered here because of photons, and you didn't say much about the candela. Can you say a few words about the candela?
Yes. Well, I have to be very careful. So the question is, could I say a few words about the candela? Well, I was...
Guess where the question comes from. Because she has a startup named Candela. It's a Q.
Okay. So my mother taught me that if you don't have something nice to say about someone, you shouldn't say anything at all. But I won't follow her advice. The candela is sometimes referred to as the most hated of the SI units because it has to do with things that don't have to do with physics. It has to do with the way in which human beings perceive brightness. So the candela is a way of measuring how bright a light source is as seen by a person. So there's a definition that says what a lumen is. A lumen is something that is how bright we perceive things to be. Amazingly, all over the world, people have about the same visual curves within a few percent, and that's good enough for the lighting industry, which is really the driver of having the candela and the lumen. But the point is that we've defined what constitutes a lumen in terms of a particular color of light at a particular intensity of watts per square meter of a particular color of light. And then you just ask people what other colors of light appear to be the same brightness, and that's reasonably consistent. But it just doesn't seem, to me at least, that that's the sort of thing you want in your base units of the SI. I mean, you have to have something like that so you can sell light bulbs. But it seems odd to have it as part of the SI, at least to me. Now, on the positive side, I could say that the candela is the most human of all of the base units.
Thank you. We have time for another question. Yes?
Thank you for the great talk. It might be a very naive question, but how do we know if the system is complete, that we'll never have to define some kind of new unit or constant again?
Well, in a sense, we don't know that. That is, for example, since around 1900, we have had a system of units in which we defined the permeability, the magnetic permeability of free space in order to define the ampere. And we decided that was not such a good idea, even though it had the features that I've been describing that are so wonderful, namely that we have a fundamental constant of nature. So it might turn out that we would decide that there's another way of defining a fundamental constant of nature that allows us to do a better job of realizing a particular base unit. Or we might even decide that we want different base units or no base units at all. And that might change things. But for the moment, at least, that's not obvious, except when it comes to time. And in time, it's clear that we will change the definition. Right now, the definition of time is still based on the cesium hyperfine frequency from 1967. And everyone agrees that because of optical frequency standards, that we can do a lot better. I mean, it's amazing already. It's a few parts in 10 to the 16 is the way in which the hyperfine frequency of cesium is realized. But optical frequency standards are parts in 10 to the 18 or even parts in 10 to the 19. So it's clear that we need a new definition. People are already using optical frequencies as de facto standards. So we need a new definition. And even when we do that, it's not clear that will be the end, because there are nuclear transitions where we have even higher frequencies and even less in the way of perturbations. But we don't have the technology yet to use the frequency of gamma rays as the way of establishing our frequency standards. But I have great confidence in the skill of future experimentalists to do that. So probably even the upcoming redefinition of the second will eventually be superseded, not in my lifetime, but will eventually be superseded by something new. Christophe, would you like to make any comments, since you're deeply involved in this?
Well, my main comment is that it's time for coffee break. So I thank you all. I thank all the speakers of this morning. Great honor for me to be asked to speak to you today. And in fact, having listened to the beginning of the session, it is even rather intimidating to think of all these people, and also the future speakers, to think of having to measure up to the standard that's just been set. Although on the other hand, I could say I am now standing on the shoulders of giants, and so I hope you will bear with me while I climb up on their shoulders, and I hope I do not fall down. All right, I'm going to talk about atom optics at YOGS and its birth. Now, of course, we didn't invent atom optics. You could argue that atom optics has the idea of manipulating neutral atom beams using various kinds of electromagnetic fields. That's been going on since at least the 50s, maybe even earlier. So we hardly invented it. But a watershed happened in the late 80s and early 90s because of all the marvelous laser cooling and manipulation technologies that were evolved during the 80s. And it became clear to many people, especially to Alain, that pushing in the direction of manipulating atoms in a way highly analogous to the way we manipulate light, we've been manipulating light for centuries, would be an interesting thing to do. And if you're not already convinced, I hope I will show you that this was a very prescient decision. And a theme in the talk will be that these atom optics experiments, we always had a sort of a guiding idea about what we ought to do, but you will see, as many researchers know, that we frequently got sidetracked and did other things. Our atom optics ambitions often turned in other directions, which I'm going to argue were also very fruitful. And so with that, I will begin with a short a discussion of, does this work? Yes. Of the beginning. Okay, so the beginning of atom optics at the Institut Optique is, I believe, happened around in 1990, when Alain Aspect had two freshly minted PhDs. Actually, I think Robin was still strictly a PhD student in 1990. Nathalie Van Sankist was a postdoc at NIST at the time in Bill Phillips' group. And I wasn't privy to the conversations, but I got wind that, that Alain was proposing to these two people to maybe start a new group at the Institut Optique, and that it would be interested in atom optics. And so it did, a year later, it did begin with the hiring of Nathalie in 1991. Aspect moved, as far as I know, officially from the Collège de France to the Institut Optique also in that year, or maybe I don't know what the official year. And then in early 1992, I believe it was Robin who joined the group, and that was the beginning of the group. And the first order of business when speaking of atom optics was to think about mirrors, because they're simple, they're flat, and they're obviously very important for atom optics and for optics of all kinds. And there's a very elegant way to do this, which involves using evanescent waves. So you have this laser that undergoes total internal reflection at a glass interface, glass vacuum interface, and that gives you an evanescent wave, which has a scale height of lambda over 2 pi, so hundreds of nanometers. And if you tune the laser to the blue, the atoms, when they hit it, will reflect. We're not the only people who were thinking about this, but this seemed like a very appealing, elegant idea in 1990. Appealing, elegant, but not simple. And here you see some pictures, some of the early pictures from the lab. Here you see Roman Kaiser now at the time with a big monster vacuum system that was not yet under vacuum. And there's also a couple of empty optical tables. There was the same kind of bricolage as you see elsewhere. Notice here that here is a Heaney laser that's been taped to some brass posts, right? I wasn't here yet. I would have never done that. But this is the kind of thing that, the kind of bricolage that you have to do when you start a lab. Okay, so, and also, fairly rapidly, it only took a few years before we had a group of students, some of whom you will recognize, or at least the ones in the crowd will recognize themselves. The main point of this, the other main point of this slide is that to show you how young we all were at the time. Okay, and that's behind it is a bunch of a laser table with a lot more stuff than in the previous picture, because it's been 2 years have already gone. Okay, so we started doing atom mirrors, okay? And so as Jean emphasized, you say things in your proposals and you do others. What we thought we were going to do was or at least what I thought we were going to do, is we're going to try to work on reflecting beams, maybe focus them, maybe you can make the mirror curved and focus the atoms down, make some kind of cavity that would multiply reflect the atoms, things like that. Well, that's not exactly what happened. What we discovered fairly quickly was actually these mirrors are not all that flat. They're, or let's say the atoms are very sensitive to very tiny asperities or roughness in the surface. Essentially, well, the atoms act like sort of a near-field probe of the surface. And that's really interesting to study the surface, but it doesn't make a flat mirror. And so that kind of put a damper on these projects. Although one can circumvent the problem, and that's still something that one can imagine doing. It's just more difficult. But what we did, and I think many other groups that were thinking about evanescent wave mirrors went in other directions where there were measurements of the van der Waals force. And then there was an interesting collaboration that was actually mediated by Bill Phillips with the group of Mara Prentice at Harvard, which proposed to do a similar thing as the evanescent wave mirror using magnetic fields. Magnetic fields created by this serpentine kind of wire, which made alternating wires, and which also gave rise to an exponentially decaying magnetic field, which could also reflect atoms in a way very analogous to the evanescent wave. We did that. Those are also rough. There's also some problems with those. But the most fruitful thing that came from that was that it sort of got us thinking in the direction of doing other things using wires on surfaces. And in particular, we and other people became aware that if you put wires on a surface in a sufficiently complex configuration, you can actually not just reflect the atoms, but you can trap them. And so you can start thinking about miniaturizing and putting atoms on this very tiny atom chip. And this is several groups in the world. I notice Jakob Reisch is in the audience, have been working very hard on this and pioneered it. And in our group, this has been taken over by Isabelle Bouchoul for the last 20 years, and it had a whole bunch of interesting results. And I think of this as sort of what happened when we started thinking about evanescent wave mirrors. Right? We're not doing that anymore, but we're doing something that is possibly even more interesting. All right, then in 1995, there was a bombshell in atom optics. There were some distinguished researchers in, I believe it was Colorado, who demonstrated that you could do Bose-Einstein condensation of a weakly interacting alkali gas. And so we, like a whole bunch of other people, immediately said, geez, how can we get our hands on one of those things? And it actually took us a little time because I have to admit that we did not immediately drop everything we were doing and start doing Bose-Einstein condensation. Part of the reason was we had been working on setting up labs and stuff, and so experiments were starting to work. We were starting to get data. We had to write papers. People had to write theses. So we couldn't just drop everything and go for making a BEC. Fortunately, about that time, Philippe Bouillet was hired to work in the lab as a CNRS researcher, and he sort of spearheaded the quest for making a BEC at the Institut. And here is a pretty picture of one of the most elegant experiments that he and the rest of the group did, showing that you could make a BEC and then couple it out in a controlled way, guide it in a laser beam, and make this thing which we referred to as an atom laser. Even though some people might argue that it's not really a laser, but it's a coherent beam of atoms. All right, so that was a really, really cool thing. By the way, here is another picture of the group from about that time. You see we've all gotten a little older, but we've gotten bigger. So that was good news. And there are more people who will recognize themselves in this picture. All right, so the atom laser was a really cool thing, but maybe a little bit like the evanescent wave mirror, it's maybe not really, really useful. But the importance of it, the importance of doing that research, I think, was what it led to. And the things that it led to, in part, were working on other kinds of atom optics experiments, most notably atom interferometry. And that has been Philippe Bouillet's business for several years. And he moved to the Institut in Bordeaux and has founded a world-leading group doing atom interferometry. Not entirely due to our BEC work, but partly stimulated by it. And then the fact that we had a BEC, of course, led us and many other researchers to the idea that, well, once you have a degenerate gas, you have all sorts of interesting analogies you can make, not so much with optics, but with condensed matter physics. So you have You have the many-body problem, and lots of, you can put them in optical lattices, etc. I'm not going to talk about that very much because I'm supposed to talk about atom optics. But Vincent Josse is going to treat that a little bit. He's going to talk about what happens when you put these coherent beams into disordered systems, which has obvious analogies with what can happen in condensed matter systems, as well as other places. But I want to give a shout out to my colleagues who are working on this, and much of the group has turned towards this sort of research. Instead, what I want to talk about is another project that is very dear to my heart, as well it is to Alain's, I think. No, I'm sure. It is the starting a project on metastable helium in the Institut. The origin was, well, my recollection is that I showed up at the Institut, and fairly soon, in talking with Alain, we said, yeah, it would be really great. We really ought to start a project that involves metastable atoms, because they're really very different from alkalis, and we can do new different things, although we didn't have a clear idea of which new different things we were going to do. We did have a little debate, though, because Alain, obviously from all the success that he got that Jean talked about in doing velocity selective coherent population trapping, using metastable helium seemed like he was a strong advocate of doing that. I personally, when I arrived, had a slightly different attitude. I was actually very impressed by experiments which had been done elsewhere, especially by Shimizu in Tokyo, and also by Steve Ralston at NIST, who'd been using heavier metastable noble gases. The idea being that what I thought was interesting was they had a more complicated structure, and might be easier. There might be a lot of interesting manipulations to do with that. And so there was a bit of a debate about what was the best way to go. Long story short, Alain won that debate. And it was a good thing. It was a good thing because we didn't know it at the time, but metastable helium is the only metastable rare gas that can be Bose-condensed. That wasn't at all what we were thinking about, but that proved to be the most important thing about it. And like I said, well, we thought maybe we'd do lithography experiments and atom focusing experiments, but we wrote that in proposals, but that's not what we did. What we did was, right about that time, Denis Boiron was hired, and we started working on cooling metastable helium as well as we could. And as well as we could means we want to go to BEC if we possibly can. So that was, although metastable helium is the only one you can condense, it was a fairly dicey affair because we weren't sure that it was going to work. And we had some tense moments. Here is a sort of a schematic of the experiment that we were trying to do. We had atoms trapped in a magnetic trap here. There, we were detecting them with a microchannel plate, that is to say, electrically detecting the atoms rather than optically. We watched them fall onto this plate. And here is one of the first signals we ever saw. And what I'm showing is this signal from the microchannel plate, which is essentially measuring the atom current as a function of time. And we're watching the atoms. The atom of the trap was turned off at some time 0, and the atoms then hit the detector. When we don't cool very much, this is almost a millikelvin, we get a time of flight that's this purple curve. And what we see is the atoms arrive, and the cloud is so hot that it essentially expands isotropically. And what you see are the atoms that are basically already pointed straight at the detector. And this peak, roughly speaking, measures the velocity that they had at the beginning and accelerated by gravity. And then as we made this RF ramp to cool further and further, sure enough, this peak got moved to later times. But the problem was that the signal was also going away because we were evaporating away the atoms. And for the first week or so that we were doing this, we did this, and then the signal just went away, and there was nothing. And so we were going, oh my God. Inelastic processes, some other stupid thing, losses. What could possibly be happening here? And if something is happening, how are we going to find out what's happening? Because we only had this MCP to detect the atoms. And then one day, or one night, when the supervisors weren't there, two students, that was Alice Robert and Olivier Sergent, were doing these ramping experiments, and they just kept the ramp going. And you'll notice there's a big gap in temperature between the black curve, 350 microkelvin, and the green one. So they went through this desert of no signal and kept the ramp going, and by damn, the signal came back. Okay? And what was happening there is the atoms were now so cold that in spite of the fact that there were few of them, they were all pretty much falling down. And so the signal came back, we could see something, and then right after that, the ramp was pushed a little further, and then it went way up, and we had evidence of a BEC. So this is what happens, keep in mind, when you let your students do what they want in the lab. I was all set to, I was sort of panicking at the time, but the students did not, and good for them. Alain was actually out of the country at the time. I believe you were in Scotland at a meeting or something. Stuck by a snowstorm in Scotland. So we went late into the night to take some data. It was very interesting and stuff. And then the next day, we started telling everybody. Well, no, actually, we tried to keep it quiet, but we were not able to keep it quiet. The next day, actually, the next evening, the following evening, I got a phone call from Bill Phillips saying, all right, tell me, what have you observed? And I told him, and then there was classic Bill Phillips. It was, okay, did you test this? And what about that? And did you think about that? And could it be this? And what about that? And so I spent an hour on the phone with Bill telling him what we knew, which was not very much because we'd just taken one evening of data. But we kept going, and many of his suggestions were, of course, followed. Alain also got wind of it pretty quickly. And I don't know when he came back, but when he came back, we had the obligatory foie gras and champagne to celebrate the event. Okay, so that was great fun. And then we went on. Let's see, I should be talking another 5 minutes or so? Okay. 5, 6. I don't measure time. So we did a lot of things, but the most interesting thing about these atoms was the fact that you could use these electronic detectors to detect them one by one. And so that meant it was fairly straightforward to make correlation measurements. You could measure the the probability of detecting two atoms together or far apart and things like that. we spent a lot of time together talking with Alain about the Hanbury-Brown twist effect. It's one of his favorite effects and mine too. A lot of talk about it, and we finally did realize something that talked about. We did manage to exploit the fermionic nature of the helium atoms. This was done in Amsterdam, and actually demonstrate a statistical effect due to the fermionic or bosonic nature of the helium atoms using these correlation measurements. And interestingly, we're able to show something that has always been difficult for me to get my head around, which is that BECs don't have any correlations, or at least correlations in this sense. So that was great fun. We also then worked a little bit on another. Okay, so this is really atom optics, right? It's quantum atom optics. We're doing essentially anti-bunching. So we're still, this was 2005, and so we're really still deep in atom optics in a way that we hadn't really anticipated in 1992, but there it is. Then we worked on the Hong-Mandel effect, which is an even more quantum optics effect. I'll spare you some of the details because time is running. And I just want to go to, oh yeah, and here's a picture of, another picture of the group from, I've got one picture from every decade. So here's the picture from the 10s. We're not getting older that quickly here, so it looks, I'm pretty pleased with this picture. And then lately, the thing we're working on now is another correlation experiment. It's sort of the ultimate correlation experiment you can think of if you're thinking about quantum optics and quantum mechanics. That is to look at Bell's inequalities. So Bell's inequalities are returning to the Institut Optique 40 years later. And it is based on the following idea. We are able to make a source of atoms, whose details I will spare you, but which we will believe is capable of producing a superposition of this nature between of two particles, which are in a superposition of having two pairs of momenta. Either they're in the p minus p state, or they're in the p prime minus p prime state. This is done with a nonlinear process, which I won't go into. But you can inject this into a thing that looks like an interferometer, in which you manipulate. You have a source that produces this state, and then you have standing waves here that can deflect the atoms and combine them and act like beam splitters. And if you put this all together and you think about these beam splitters these Bragg diffraction beam splitters actually have phases associated with them that have to do with the positions of these interference fringes, you can develop a correlation measurement that is pretty much an exact mapping onto the CH-SH inequalities that were used by Alain's experiment in the 1980s. So every time Alain comes by and we talk about this experiment, his face lights up, and we have a lot of interesting discussions about how to do this. We haven't done it yet, but we're working hard, and I'm optimistic that some sort of interference experiment is going to come out of this. We even have plans to go and do this in such a way that we would really test some sort of non-locality, unlike this experiment where the separation of the detectors will only be of order millimeters. And with that, there's one more picture. That's the picture from the 20s. You will recognize many of the people there are now here in the audience, so thank you for coming. And I just want to finish with the following list. I happen to have always kept a record of all the students that come through the lab, all the PhD students that come through the lab, because the university asks us for information about where they were, what happened to them afterwards. And so there you have all the PhD students have up until here that have finished a PhD in our group. There are 107 there. And what I want to finish with is to say a big thank you to Alain, whose leadership was instrumental in attracting all these people to work with us over 30 years now. As any experimentalist knows, you can't do anything without good graduate students. And so I also want to thank all the graduate students that are on this list who are listening, for their hard work, their intelligence. And I just want to say that it was really extremely enjoyable, for the most part at least, to work. No, really 99% of these people are just delightful. And I won't tell you the guy that I didn't like. And so a big thank you for the leader who got them here, and then the people who actually do a whole lot of work and contribute, as Isabel said, to the ambiance of this lab, of this group, which has been really great. So that's all I want to say about that. I have just one last slide, in which is that I probably don't need to remind you, but the hallmark of Alain Aspect are good physics and good food, right? And maybe good wine. So I wish you all a very pleasant meal this afternoon. And for those of you who are going to dinner, that you'll have a very, very good dinner as well. And so I wish you all bon appetit. And we are French. I'm French. And I think you can count on us to know how to cook.
No? Okay, so here, does somebody want to ask a question? Yeah, Bill. Ah.
So you declined to give more details about Hungo Mandel. So I'm going to invite you to say a little bit more. Now, you know, sometimes people talk about Hungo Mandel in terms of the coalescence of the photons and saying it has to do with bosons liking to be together. But, you know, it's much more magical than that. Because, you know, there's a phase interference that prevents
yes.
The photons from going in opposite directions. Well, it works the same. What I want to know is about the fermionic version, because what I'm wondering is that, you know, it seems like the statistics will sort of automatically tell you they're not going to go the same way, but where's the magic?
Yes. Maybe there isn't so much magic. I've had this conversation I've had. Juin has asked me this question more than once and has a lot of things to say about it. It's true. The quantum statistics prevent two fermions from going out the same part of the beam splitter. In spite of the fact that it's actually interesting to note that if you mess around in the right way, you can make the bosons act like the fermions. You can make the bosons not come out in the same port. If you have to do a little bit of elaborate messing around. You can't just put phase plates in front of the interferometer. So you have to do something to the two-particle wave function to do it. So you can do that with bosons, but you can't do it with fermions because the exclusion principle will say no. And so with Jean, we're thinking about, well, can we think of a system, a situation where the fermions could have gone their separate ways, but they didn't for a quantum interference reason. And I think there is a situation where it happens. It happens, I wish I had a slide. When there's an experiment that was done, it was done in Heidelberg. It's Jochen Selim's lab. They had two fermions that were trapped in optical tweezers. And they could let them drop and land on an optical, they did some sort of light sheet to detect their positions. And what they see are the equivalent of, well, if you just drop two fermions onto this screen, you just see a uniform distribution of atoms, as you would with bosons. However, if you look at the correlation between these two arrivals, you do see fringes. You see exactly Young's fringes, but the argument of the cosine in the Young's fringes is the difference of the distances rather than just the distance, the absolute distance.
Yeah, so basically you have to look at the second order
yeah, if you look at the second order correlation function,
field,
which is what you're doing also in the traditional Hungo-Mandel experiment, you see fringes, and these fringes have a phase which is 180 degrees. It's out of phase with the fringes you would get for the bosons. Okay, so there are two places where two fermions never go because of interference, or they never go at the same time because of quantum interference. But it is not the Pauli exclusion principle by itself that is preventing this from happening. So that's the best I know, and it's the experiment from Heidelberg. It's beautiful. They have a remarkable signal, and it's a great experiment.
Okay. Thank you. I was told that in the other room they did not hear my request for questions. So if they have any question in the other room, they are welcome to ask. Okay.
Can I make a comment?
Yes, of course.
My comment is that the Hungo and Mandel, we all agree that it is a fantastic experiment, but then we not necessarily agree on what it means. For me, it's not so much the statistics of bosons, the fact that the two bosons go in the same channel. I think the reason is not, well, the fact that they are bosons allows them to be in the same channel. But the most beautiful thing in the Hungo and Mandel experiment is that it is a two-particle interference effect which prevents the photon to go one on each side. And so as soon as you have that, you can ask yourself the question, is it possible to violate Bell's inequalities? And the answer is no, and I have two arguments for that. The first one is that I can build a local hidden variable theory for mimicking the Hong-Mandel effect. You have just to suppose that from the beginning, the two photons know that they will be on one side, or they know that they will go on another side. And talking with the group and thinking about this question, we came to the conclusion that if we want to test Bell's inequality with that kind of setup, we need not two modes, like in the Hong-Mandel experiment. We need four modes, two modes on each side.
We need that.
And so I think that it is very interesting to remark what is the big interest of the Hong-Mandel experiment and what is its limitation compared to test of Bell's inequality and those kind of things. I think it's a very profound experiment that they have done. Ask the chairwoman.
No, just go steal the microphone as fast as you can.
So, continuing on this thing about violating Bell's inequalities, you can see the Hung-Mandel effect without having any entanglement between the two photons. Now, the first experiments
Do you agree with that?
were entangled, but you don't need them to be entangled.
I think Jean begs to differ.
Okay,
but anyway.
well, you see, I think you can do it. All you need to do is to have them to be identical. That is, you could have two push buttons, and that wouldn't result in entanglement. But now I want to hear what Jean has to say.
Right?
Okay,
right?
no, but maybe we let,
okay, well,
we let
this
this
is
for later
for lunch.
discussion, and we go on. So thank you again, and.
It's of course a great honor, Alain, to be here today and to present this work. And to emphasize that it is a more recent part of your career that has been about the study of Anderson localization with ultra-cold atom. And I believe many of you know a bit about the studies. And it's worth really to notice that this work that's been initiated here by Alain has really triggered a new line of research within the ultra-cold atom community, which is the study of disorder system. So as I said, this started almost 20 years ago, and there's been plenty of work done about this subject. So my goal is not, of course, to give you a full overview of all what has done, but I will concentrate more on what we have done in Palaiseau, so under the supervision of Alain, and once again, which is very still active on the subject. So let me start by saying what is Anderson localization and why are we so excited about it. So not only me, Alain, and plenty of other researchers about it. So to understand that, the key point is to realize that if you want to treat the propagation of wave in random media, which appears in many, many, many different situations. And for example, here you have light propagating on the cloud. But this is also the same if you consider the electronic conduction in a bulk material where the electrons experience scattering and impurities. Then the very standard usual way to deal with that is to forget about all interference effect. That seems very reasonable since it should, of course, vanish out as soon as you perform disorder averaging. And then you treat the propagation as if the wave was a classical particle. It's bouncing here on scatterers, and the typical motion is a diffusive motion, characterized here by a diffusion constant. But what was realized by Anderson, and it was the first one to do that in 1958, so a very long time ago, that in fact, even if this works in many situations, and it's extensively used, it's not always true. And there is some situation where the wave can have a very strong effect. Indeed, they can build together, they can first thing survive over disorder averaging, a key point here, but also have a dramatic impact on the propagation since they can completely cancel out the propagation of the wave. So in that case, what's happening is that the diffusion constant cancel out, that it drops completely to zero. And in that case, the wave functions are localized here with an exponential decay here on the wings. So this has a strong impact, for instance, if you consider the electronic conduction, because in principle you had a metal, you were thinking you had a metal in your system. But then if the diffusion constant here drives to zero, if you consider electronic condition, it means that the resistance goes to infinity. That means now you'd have an insulator. And this is the reason why this has been studied a lot in the context of condensed matter physics and to study this kind of metal insulator transition. And I want to notice that Anderson gets the Nobel Prize in 1977 for this kind of result. But it appears if you want to study it from a point of view, it's extremely difficult to do that with electronic systems because for a very fundamental point is that the electrons, they do interact together via Coulomb interaction, in fact, Coulomb repulsion. And this interaction can strongly modify the physics of Anderson localization and even destroy it because it is a purely single particle effect. So in fact, what is happening is that this picture is, as Anderson localization arising from wave interference, has been realized much later than that, even later than the Nobel Prize of Phil Anderson. It was basically in the mid-80s. And then it was only realized at that time that you can study this effect with, in fact, any kind of wave system. And then there was a lot of interest to try to study this with plenty of other systems. So here I show you just a few examples, which are really remarkable in this investigation, like ultrasounds. You can do it with microwave. There is a lot of studies in disordered photonic crystals. And you can do even, think of funny things. We are looking, for example, in localization phenomena with seismic waves. So in principle, it's work with any kind of waves. So if you're interested on the subject, I strongly suggest to read you about this very nice review that was done here in 2009. And the key point here, the key message to retain is that it is a still very active field of research, but Anderson localization is very subtle effect and very fragile. So if you want to study it in a clean way, then what you need is to have very well-controlled system to be able to compare between experiment and theory. So if you think about very well-controlled system, many people know already here that a very good system for that is using ultra-cold atomics sample. And this is why here you see also, and I made it on purpose, you see that two people that you know, that Alain here was also author in this review here in 2009, and Massimo Inguscio, which is here somewhere in the audience. And the reason why they're here also in this review is that in 2009, it was just 1 year after we could observe for the first time this Anderson localization with matter waves in our setup, and this is the story that I will present you now. So the idea here is to use all the technique about the cooling technique, so that was mentioned a bit by Jean this morning, and also of course mentioned by Chris, to cool down the atom at extremely low temperature, and then if you do that, then you cross what we call the Bose-Einstein condensation, where the atoms behave like matter waves. So for us, for the following, it will be our matter wave source, simply cooling the atoms at very low temperature. So when I mean low temperature, is typically hundreds of nanokelvin for typical experiment at the time. And what we want to do is study this matter wave in disorder. And for that, we use the fact that the atom, the light interacts with the atom and corresponds to forces. We can do potential with that. So if you want to make disorder, you have to shine disorder pattern of light. And here, this is something that we master a lot at the Institut Optique because we know everything about laser speckle. So what we can do is just shine here with a laser on a rough plate, focus on the atom, and what you end up with is what we call a laser speckle pattern with bright spots here and dark spots, purely random patterns. Okay, and this will translate directly. What is important to understand is that this intensity profile directly translates as a potential, as a random potential here for the atoms. So this looks like messy picture here, but the key point that you have to realize is that it is extremely well controlled. So it is well controlled not only for here the matter waves here, but also we have full control and knowledge about all the disorder statistics in the system. So this use this ultra-cold atom as platform, ideal system to study phenomena related with condensed matter physics is part of a big line of research in ultra-cold atom community that you will hear more about this afternoon that we call the quantum simulation. And this started in 2002 with a seminal work on optical lattices in Munich by the group of Immanuel Bloch. And if I consider the study of disorder system that we'll talk about today, so to my knowledge, the first paper that mentioned the possibility to observe disorder system and localization phenomena was in 2003, so exactly 20 years ago as I mentioned today. So based on this first proposal, there was different teams that tried to observe this Anderson localization with ultra-cold. And among all the teams that tried, it is really fair to state that there was two main actors. Of course, here at the Institut Optique, under the initiative of Alain, but also Philippe Bouillet, which was here at the time in Palaiseau. And another very important team is the one in Florence at the Lens, with Massimo Inguscio and Giovanni Modugno as leader here on the team. So, and what they try at the beginning, the idea was to try to see this effect in 1D configuration, meaning that you take here your initial atomic cloud, so your Bose-Einstein condensate, then you trap it here at the center, and you release it now using an optical guide, so it's a not focused optical beam, and the atom can propagate along that, and you shine a bit of your laser speckle disorder on it. And the idea, so you let the atom expand, and the goal is try to see can they be stopped indeed by disorder, and do you recover this famous exponential decay as a signature of Anderson localization. So in fact, as many experiments, and there was a lot of example this morning, it doesn't work at the first time. So they took a lot of data and tried to see Anderson localization, but it was not a direct success. So I don't have time, of course, to enter all the detail of that, but you don't have too much worry about it. It's really classical. But the key point is that doing so, then we acquire knowledge how to do that. And what it triggers is a very important theoretical work here done by Laurent Sanchez-Palencia in the group that identifies really a key criterion to be able to observe this Anderson localization that was not met in the first experiment. And the idea seems quite reasonable, is that if you want to be able to observe Anderson localization, what you have to verify is that your double wavelength of your atom should be larger than the correlation length, here the typical size of your disorder if you want the speckle grain size. Okay? So this seems very reasonable, but it's more than that. It's really mandatory. If you don't do that, then very soon you see nothing. And that was the problem in the first experiment. So if you now translate that, okay, for experiments, so what we do, we use light to create disorder potential. So the minimum size that we can do is typically the diffraction limit. So if you put a number, what you can have like an order of magnitude here is the micrometer scale. And if you translate that we use rubidium boson, so you take the mass, whatever, and here you end up with a criteria in temperature which is extremely stringent, which means that the temperature that we needed to use at the time was around 10 nanokelvin. So if you remember, here I said it's basically, for experiment, it was more on the 100 nanokelvin range. So you have to go one order below, and what I call somehow it's not using ultra-cold atoms, but what was really needed here, and what we do in the lab for years now, is to produce ultra-cold atoms. That means sometimes almost the coolest atomic sample ever produced. So having that in mind, we took, in fact, over the experiment in the team. I was leading in the experimental setup at the time, and Juliette Billy was a PhD student. So we struggled a lot. It was not such an easy task, and again, to try to reach basically the same configuration, here to try to let the atom expand in 1D, but now with an extremely low temperature. And doing so, we could manage to be in this situation where here we can let the atom propagate, and when they propagate, their energy here is much, much higher than the disorder potential. It's like very tiny little potential, and you have absolutely no way to have a classical trapping possibilities there. For classical particles, they will just go away. Okay? But at the same time, we still also verify this criterion that the Boy wavelength is larger than the typical correlation length. And doing so, what we could observe, so we let the atom expand, and it's like a miracle when you really observed it, a pure quantum effect in your experiment. It doesn't happen so much, in fact. So what we could observe is that we monitor on time, we do fluorescence imaging, we look at the size of the atoms, and for instance, we plot here the typical size. So with no disorder, as I said, it expands, so no problem at all, it's very well controlled. And then it stops. And once again, there is no way to explain this stop by any classical trapping possibilities, but it can only be a quantum effect. And this quantum effect, if you want to understand it, it comes from the fact here you have small fluctuation of your disorder, and at each small fluctuation, you have small quantum reflection. And all this quantum reflection, which is not evident at all, they build up together to provide, to stop the propagation. And this is not only a fuel, here what I'm showing you, because if you look here at long scale, we could observe localization length on the millimeter length scale, so very large wavelengths, wave functions, sorry. So it means that it's not a few quantum reflections that work together, but thousands of them that build up to allow this localization. So having that in mind, so it was really an impressive experiment, but if we want to go beyond, of course, the goal is to be able here to see, can we see this exponential decay on the wings, which is like the hallmark of Anderson localization. So of course, if I'm here, it worked very nicely, in fact, at the time. So here, what I'm showing you is the atomic profile here in semi-log scale, here and against position. And in this semi-log scale, so exponential decay translates as linear decay. And from it, we can even extract here localization lengths, and really cherry on the cake, they work in perfect agreement with the theoretical prediction of Laurent. So it was a big success. We have good wines and good champagne and foie gras, everything at the time. So it was a very good year at the time. So it was important for us, okay, in the lab. But in fact, 2008 was a very special year for Anderson localization, not only the 50 years about this discovery, because there was several experiments very important in the so in particular in Florence, because at the same time, they could manage also, so the system was slightly different, but also to observe this localization effect in 1D experiment. So basically, the scheme is the same. You put Bose-Einstein condensate, you let it expand, you put disorder, you observe localization, and everything is under control. There is also another very fruitful approach that I won't describe in detail, of course, but which is here, in this case, very different, which is looking at another effect in kick-quarter system, where we keep periodically the atoms. And then one can show that localization is not the genuine Anderson localization, but appears in momentum space that we call dynamical localization. And in 2008, there was also a very important paper along that line in Lynn in 2008. So I won't mention more this line of research, but they made a really important result over past decade to study Anderson localization. So coming back to the genuine one, that means looking what can be done in real space, looking at expansion of Anderson localization, I think it is fair to say that these two works has a very strong impact on the community, and for two reasons. First is from historical importance, because it was the first time ever with electronic wave or whatever that we could observe directly this famous effect with matter wave. So it has never been observed directly before. So this is, of course, valuable for science, but maybe the most important things, if we want to look for future, the idea there is, if you think of the very nice agreement that we could observe here, for example, on exponential decay with theoretical prediction without any adjustable parameters. So you just do ab initio calculation, you do the experiment, and it matches perfectly. So it somehow validates the use of this system, so ultra-cold atom in disorder, to really study in detail this phenomenon, which are very complicated. So the field has, of course, developed in many directions since 2008. But if you think of Anderson localization, the grail somehow is to tackle what's happening in 3D, which is a very peculiar dimension, because here you have a real quantum phase transition between a diffusive and localized behavior. So of course, where we wanted to go. So to have an idea what's going on in 3D, what you have to keep in mind is that if I produce weak disorder, I will define what it is, then basically nothing changed. You still have your diffusive behavior. You can have some interference effect, but basically they don't change qualitatively the behavior. You still have diffusion. And this remains true until you increase the disorder so much that you reach what we call the Joffe-Regel criterion, which tells you that the wavelength, could be classical wavelengths or de Broglie wavelengths, is under order on the mean free path. That means the typical distance between two scattering events. And you have to realize that this is an extreme disorder situation. That means the wave barely experiences one oscillation before it is scattered again. And only if you can succeed to be in this regime, then one can show that the interference effects are strongly enhanced in this regime, and you have this localization. So here, this picture, you see where I increase from low to strong disorder. I can translate it. Disorder potential is fixed. This is an energy diagram. So at high energy, my states are supposed to be diffusive, like a metallic behavior. If I am at low energy, my states are supposed to be localized. Okay, it's the insulator behavior. And in between, there is this famous transition, which we call, the energy under transition is usually called, in the domain, the mobility edge. So the goal is to try to measure it, look at the critical regime, and so on. So since the beginning, it was really strongly studied, not only by experiment, but also on theory. And the key point is that it's still a theoretical challenge to address this question. And to keep an idea why it is, because once again, about this Joffe-Regel criterion, which tell you that if you want to tackle and to describe qualitatively the Anderson, the localized states here, then you can forget about all perturbative approach that will completely break down when approaching here the transition. So at the moment, there is still no exact theory to describe the transition in a quantitative manner to be able to describe it, position of a mobility edge or critical exponent. In the same idea, these highly scattering medium here are difficult to produce numerical simulation, but they are, of course, more and more possible with the development of all the capabilities. And in this respect, I really want to mention the influence here on the team by Dominique Deland, and I'm sure Alain will do the same. On all his knowledge about theory and numerical simulation, he has really a huge impact of all what we can do in the lab since the past decade. So this is, okay, a theoretical challenge to address all this story of Anderson localization and 3D one. But the good thing is that, as I said, it's still alive, and there is still new approaches that develop on time. And a very important one at the moment, it's what we call the landscape theory that was initiated by Svitlana Meroboda, which is a mathematician in US, and Marcel Filoche, which was at École Polytechnique and now at Institut. So I won't enter to the detail, but the idea is that they found that behind your potential, there is like an hidden landscape that can tell you a lot of properties about the localization properties, and we are also collaborating a lot with them at the moment within the foundation, collaboration funded by the Simons Foundation. So this is for theory. So theory is difficult. And as you imagine, it's also difficult for experiment. So at the moment, in fact, there was 3 experiments that were addressing this problem of 3D Anderson localization. One in Urbana-Champaign in 2011, which is in fact highly debated, but still existing. There is 2 other ones, one in Palaiso, it was in fact roughly at the same time here, and one in Florence that appeared 3 years later in 2015. And all of them, in fact, were faced to common difficulties. And to give you an idea what's the problem there, I will just present you what we could observe here in Palaiso. So the idea is still the same, so we keep the same idea. You take the BC, you let it expand in disorder. So if you want to go in 3D, what we did is we have to rebuild everything, of course, but then we could shine speckle laser from 2 sides to make it as isotropic as possible. We also implement here magnetic coils here to produce magnetic levitation so that you can forget about gravity, and we let the atom here expand and disorder for a very long time. And looking at it, so there was a very good news, because if you wait very long time, what we could see here is that at long time there was really a localized part that was not moving anymore that appears at the center. And this, it was the very first clear evidence that we could observe 3D localized states here in the system, which has, of course, a very important result. But at the same time, there was also bad news, because when we were looking here at the wings, these wings here, we could show that they still evolve very, very slowly. So you have to wait very long time, but if you look closely at it, they're still diffusive. So what we could observe is that at the same time, we had localized part, but also at the same time, a diffusive part. And to understand why it was like that, and we could not then observe the transition, and to understand why it comes like that, the idea is to come back to this idea of very strong disorder. So as I said, we start from extremely cool atoms. So in this energy diagram, it will correspond like to 0 energy. So it's extremely cool, perfect, clean, etc. We master everything. But then, if you want to see this localization, you have to increase the disorder so much that in practice, whatever you do, it's impossible to avoid strong excitation on your system. And basically, for all experiments, what we end up is something like that, with some subtleties, but always the same idea. Here you have your distribution of energy that span across the mobility edge, with atom here above the mobility edge, and here below in the localized region. So if we want to go beyond that, we have to find a way to be able really to master this distribution, because doing so like this, it's really impossible to observe directly the transition, or neither to be able to look at the critical region. So the goal was to find a path here to go from this experiment. Okay. Can I get some help, please? So Isabelle, can you, you give me 1 minute more? Ah, okay. Thanks a lot. So, okay, so let me come back. So the idea here, what we have to do is to find a way now, if we want to really study this Anderson transition, to find a way to be able to control the energy in a very controlled way, to make it as narrow as possible, and also to be able to scan it at will across the disorder. So that's the way. So to do that, to go there, as usual, and it was many experiments. In fact, the path was not straight at all. It was really a path where we explore many things. Of course, I won't detail here, but the message is that we really take time to explore in detail many properties of transport of matter waves in disorder, looking at signature of phase coherence, looking in detail at the elastic scattering time, measuring special things like what we call the spectral function, etc. But still, we had in mind to go to there. And the key point for that was to find a way, by a new technique, which we call the RF transfer technique, to be able to load the atom as a specific energy in the disorder here, which is exactly that, and to be able to control it. And the last result, which was very soon here, we found a way also with this system to achieve sufficiently long time to look at the transverse properties, and this we do it by so-called bichromatic laser speckle disorder. So having that, now we have the perfect tool to try back the experiment. And I will show you it's really preliminary data. It's really new data that we are achieving at the time in the lab. So what we are doing is still the same, keeping the same idea. We let the atom expand, but now with a very different system is that we control the energy. So what we do is we set it for example, at low energy here. We let it expand for a given time, 2 seconds, and then we look at the cloud and measure the RMS size and plot it here. And we redo the experiment by here increasing progressively here the energy and going from low energy here to high energy. And what you see here, which is quite remarkable, is that you see that at low energy, nothing much happened. I'm almost done, Isabelle, don't worry. I'll take my extra minute, okay? And then what you see that after this somehow critical energy, then it starts to move. So it's really tempting here to address this transition here to be the mobility edge. So what we can do, and this is almost the end, Isabelle, don't worry. I can now compare, as I said, Dominique Deland can make many wonderful things, and he can now produce numerics to tell you what, in principle, where should be the mobility edge. So this is this graph here on normalized units, you don't care, but this is here where should be the mobility edge according to the disorder amplitude, and if you are below here, you are localized, if you are above here, you are diffusing. Here you have the experiment in Florence, which you see they are quite far, so the message is not to say it was a bad experiment. The message it was just an extremely difficult experiment. And what they didn't add at the time is this way to control the level. So to finish there, so you see if for this parameter range, basically we are here in this graph, and when we increase the energy, we go on this line. And here is now we try to put on this slide where should be the prediction of Dominique. Maybe you don't believe me, but it's there. See, it's incredible. Okay, so maybe we are lucky, but we are starting, it works for other points. So it's really the status of the experiment at the moment, and I believe it's a good time to end up with that. So in conclusion, we have now, I believe, a perfect setup to study what was really a goal for us and for Alain since the beginning on that is studying this 3D Anderson transition, mobility edge, critical regime. We have a very nice collaboration initiated by Marcel and Vilitana. And plenty of things can be done, not only 3D Anderson localization, there is plenty of exotic things to be done in 2D. You can, of course, I didn't mention it, but there is a whole area of doing disorder and interaction. And also, just wanted to mention here, because of course it's from foundation, so it's what we do. Okay, we try here to look very detailedly in physical feature, but if you look to think to innovation, there is a general trend now to try with this knowledge acquired on disorder system to develop innovative application, and there is plenty of things going in wave on disorder, so I won't mention that, but for example, random laser, focusing, and so on. So I stop here. Sorry to have been long a bit, and really thank you, Alain. It was a pleasure to be on with you all along the way, and thank you.
Okay, thank you very much, Vincent, for this very nice overview. So, is there a question in the other room or comments? Okay, and here? Does somebody else than Bill Phillips?
So that's the scary question now.
Okay, well, I have so many questions. So let's go back to the 1D.
Yeah.
So you talked to us about the sort of the tension that there exists between having to have the energy low enough, but that the de Broglie wavelength is long enough that it's longer than the correlation length. But at the same time, you can't have it so low that you get classical localization. Now, so what I was wondering about was the ability to find the good spot. Now, in 1D, if I'm remembering correctly, so please correct me if I'm wrong, you always get localization no matter how strong the disorder is. But, of course, your apparatus is only so big. So you could imagine being in a situation where, in order to satisfy both conditions, that the atoms be cold enough but not too cold, that you might end up having to have the apparatus be longer than what you have available. So what I'm wondering is, but that doesn't happen. So is what parameter? Is there a parameter that guarantees that the localization length will be reasonable? That is, would it go worse with a heavier atom or a lighter atom, or what insight can you give me on that?
I think there is no direct proof, somehow argument to say that it should happen. It may depend on plenty of properties of your atoms or whatever, so I won't get to there. But what is sure, what is important to have in mind here is that, okay, you can, the important point is to trigger the size of the speckle. So this is what we do. That means we made as small as possible to increase, I translate somehow your question if it's not clear to everyone, is that by making it this small as possible, then I can avoid to have different wavelengths, smaller wavelengths, and then to play with higher energy. Okay, so this opens somehow the gap where you could observe this Anderson localization. Okay, then now, okay, you have a given experiment, sorry. So what you do, you can estimate where it is, but the idea is now to try to come back, maybe not as far. So we could on the experiment, because looking at parameters, it was on the millimeter scale. Millimeter scale, this is basically what you can do. So, but we could have also localization much smaller than that. But then you enter here, and then you have to pay attention of classical trapping. But what is a very good point for Anderson localization and with speckle, that what you can show is that the probability of disorder is exponential. So for a given energy, the probability to be trapped can decay exponentially, whereas the localization length, when you increase the disorder, increase only algebraically. So I believe this is not the full answer of your question, but it is part of your question, which makes it possible to find a way where you can surely exclude any classical trapping effect, but still having efficient localization. But after, you have to look precise number of it. I think this is one part of the answer.
So, okay, a short question.
Of physics, the phenomenon of Anderson localization is significantly affected by the interactions between the particles. So in your system, do the interaction play a role? And did you reach this regime?
Okay, so here, for this first experiment, they played a role. Okay, for the reason is that at the time, they could not match, so it's really relative to the first question. They did not add, the sigma was too large somehow, and there was no room to go too much. So then you go lower, and then what you can have is two things, because you still have initial interaction on your system. I mean, we had on our system, okay? You can find another system now with Feshbach resonance where you can cancel out, okay? So one part on the answer, sorry, will be you can find atomic system where you can really make it to zero, and then you don't care about it. Second part is, in our setup, it was not the case. There was still remaining a little bit of interaction, and that's why it was not so easy to understand what was going on in the first experiment, which was a subtle thing between classical trapping, interaction, that we normalize, yet then you can have super fluidity, plenty of fancy things. For our experiment, what we made it to make so cool is then we made extremely dilute. There was only few atoms, so it was extremely hard experiment because we have to average for many, many shots. There was only few atoms there. And then as soon as they expand, they get dilute and the interaction is getting almost zero. So looking at this picture, in fact, there could be interaction effect residual here, but we understand that what we do is when you look now at the exponential decay and the wings, here, the interactions are in principle completely negligible. After, if you look to theoretician, even, okay, sorry, they told me to stop. We can discuss, there is plenty of things interesting with interaction for sure.
Yes, thank you very much. I think we will stop. So now comes
yes, I was still in my... we have several surprises. And the first one is that, I didn't mention it, but of course it was said many times, we're all happy in the group to have you, to have funded this. In fact, all the permanent members were somehow hired by you, but now there is plenty of students, there is plenty of pictures. So this picture is the most recent one, and thanks to the Nobel Prize, we could at least make one. So we made it every 2 years, or sometimes 10 years. So I also add here the student, interns, etc. So now I believe they will come here, and really I think it's important for all of us to thank you. So please. So you will see that it's quite big. So oui, viens là. So I didn't prepare too much to say, but I think the main message is everyone is here and so happy to have you here in the lab. Je sais pas si entre différentes générations.
Le photographe est fini son travail. C'est bon, on peut.
So I don't know if you want to say something.
On dit faire ce que vous avez envie de faire. Voilà, c'est ça.
Merci. Cher Alain, dear Alain, so there is a small surprise before we go for lunch. The origin of the surprise is the following. So this day is a tribute to your research activities and the Nobel Prize that you received last year. But when we discussed the program of this day with the scientific committee, so with Rémi Carminati, Jean Dalibard, and Philippe Grangier, we also thought about your strong commitment to teaching and to the students. So you've been lecturing in many different places. First of all, at Institut d'Optique for many years, and you're still teaching. But also at VNS in Paris, at VNS Cachan, now NS Paris-Saclay, and École Polytechnique. And so we thought that there should be something which is mentioning your commitment to teaching. And so we discussed with Clémentine Bouillet, and we came to the idea that what we could do is contact a former PhD of the group, Hugo Kaila, who is now a video maker, and that we will, let's say, collaborate to have him realizing a short video. So this is a small gift from the Institute.
ce que j'appelle mes enfants scientifiques, c'est ceux qui ont fait la thèse avec moi ou qui ont suivi mes cours. Et puis les petits-enfants, c'est ceux qui ont fait les thèses avec mes enfants. Donc j'en ai beaucoup finalement.
Oui, donc j'ai eu Alain en cours lorsque j'étais en première année à l'école normale supérieure à Paris, et donc en fait il faisait une option sur l'optique et les lasers au deuxième semestre de la première année.
J'ai rencontré Alain en tant que professeur en cours de laser et d'optique quantique à l'école polytechnique. Donc 2 cours, 2 années d'affilée.
J'ai eu Alain Aspect en cours, donc à l'Institut d'optique en 2e année. Donc c'était un cours qui s'appelait Interaction, rayonnement matière.
Alain Aspect était mon enseignant quand j'étais à Cachan. Il était très apprécié comme enseignant qui nous préparait à la grègue.
Ça c'était un très bon prof, oui, c'est le moins qu'on puisse dire. Il était même célèbre dans l'école. Il faut rendre à César ce qui est à César. Il a un talent énorme, considérable pour expliquer les choses, pour convaincre les gens.
Do we really need to quantize light? Until the 1970s, the answer was not 100% yes. Almost all known phenomena of optics could be described in the framework of classical electromagnetism without any reference to the notion of photon. But it is not the end of the story. We need to quantize light if we want to understand modern optics. But why should you want to study quantization of light?
Je me souviens que c'était quelqu'un de très très captivant, donc quelqu'un qui récite pas son cours, mais qui nous raconte une histoire. Donc en fait, on l'écoute un peu avec des étoiles plein les yeux et ça marque.
Alain insistait énormément sur le fait que ça n'a pas à être facile, la physique. Il faut se concentrer, il faut passer du temps, et que l'enseignement, enfin la salle de cours, ça devenait un endroit où on se faisait des images. À Polytechnique, on a l'habitude d'enseignement assez mathématisé, assez formel. Et lui, une chose que j'ai bien aimée, c'est qu'il insistait beaucoup plus sur les aspects liés à l'intuition physique.
Les notions qui s'enchaînent, les réactions, on les retient mieux s'il y a quelqu'un qui a trouvé une bonne image pour ces notions-là, quoi.
À quoi ça sert les images? Ça sert à avoir des intuitions. En tant que physicien, c'est à vous de choisir l'image que vous voulez. Bricolez-vous votre propre image. L'essentiel, c'est qu'on fasse tous, que vous appreniez le formalisme et qu'on fasse tous les mêmes calculs.
Bon, moi je pense que c'est vrai de tous les profs remarquables que j'ai eus. En fait, on voit que c'est des gens absolument passionnés par ce qu'ils racontent. Et en fait, ils sont absolument pas blasés, même si c'est des choses qu'ils ont racontées déjà à 10, 20, 100 fois.
Donc ça, c'est vrai qu'il y a un cours d'Alain, il y a les mains, il y a le corps, il y a la voix, il y a tout ça au service d'un contenu qui est difficile d'accès, qui est difficile. Alors, j'ai pas eu Alain comme enseignant de travaux pratiques. Je sais qu'Alain s'est occupé de l'agrégation pendant un certain temps aussi. Mais il y a quelque chose qui ressort énormément dans ses cours, même si c'est pas dans le cœur des matières que j'ai pu aborder lorsque j'étais étudiant en face de lui, c'est la partie technique. Toute l'histoire de comment on est passé des expériences historiques d'Alain aux expériences de travaux pratiques, c'est ça. C'est une succession de questions techniques.
Et quand j'ai vu ce sujet-là, j'ai vu que c'était les inégalités de Bell pour les étudiants. Je suis monté voir Alain Aspect qui était toujours dans la maison. Je lui ai dit, tiens, il y a des gens qui ont monté ça pour des étudiants. Qu'est-ce que t'en penses? Alors immédiatement, évidemment, il a été plus qu'enthousiaste. Il a dit, vas-y, tu commences, je te trouve l'argent tout de suite, il n'y a pas de problème, on fait la manip.
je dis, vous savez, elles étaient dures les expériences, mais aujourd'hui, les étudiants de suboptique, 5 jours par semaine et 30 semaines par an, ils testent les inégalités de Bell. Alors donc, je fais un peu de pub pour ça, voilà. Bon, sur ce, si vous le souhaitez, vous pouvez applaudir.
Alors, c'est une vraie surprise. Écoute, c'est magnifique, Hugo, et j'en profite pour dire à tout le monde que c'est un récidiviste. Avant de faire ça, il a fait une série de petites vidéos sur les inégalités de Bell, que je cite à chacune de mes conférences, et je vous encourage. Pour le trouver, il faut aller sur YouTube et taper quoi ?
Photon jumeau, c'est le nom de la chaîne YouTube. Voilà.
Voilà, donc Hugo, qui a été par ailleurs un étudiant tout à fait important dans le groupe, n'est-ce pas, Vincent, qui a beaucoup contribué... Hein ? David. Excusez-moi, je suis fatigué. Qui a contribué à des résultats importants du groupe. Et donc, maintenant, il fait des vidéos. Je ne sais pas si un jour tu reviendras à la physique. Tu fais un peu de physique au travers de tes vidéos. Voilà. Merci beaucoup. Merci à tous pour avoir manigancé cette surprise. Merci à tous les orateurs de ce matin, parce que je ne vais pas les passer en série, là, pas maintenant, peut-être ce soir, on verra dans la conclusion. Mais en tout cas, merci à tous. C'est vraiment merveilleux pour moi.
So, as always, a tremendous pleasure to be here, and I'm really delighted to have this opportunity to address this. This is a celebratory occasion, a festival, and so it's an opportunity to say, here we are today, but where have we come from? Where is our native lands? Where do we hunt? Where do we fish? Where do we tend to our vineyards and to our fields? Sociologically, many of us here will say we are atomic molecular optical physicists. We can tell that must be the case because when we go to conferences, they have names like DAMOP or ECAMP, you know, so they have A or OM or O or sometimes P for photon or S for spectroscopy in them. Perhaps we were professors at or were students in institutes that begin with an O, such as Institut d'Optique, which is again part of the world of AMO. This is maybe who we are from a point of view of sort of a professional establishment, but I think there's a long tradition in our field that intellectually we go wherever we want. We jump over the fence, we think of all of physics and all of science really as a place where we are allowed to go hunting and fishing, and we can take grapes from the other vineyards if we want to. In particular, we should mention that and wander across the world of physics as we please. And who has wandered with more purpose and more effect and more joy than our friend Alain. So I'll be talking about that today, sort of telling a little bit about a history in order to put the work of Alain in some context. It is not a traditional history of physics. I'm not a historian of physics. Instead of saying, like, let me present exactly the things that have happened in the order they happened, I've just mentioned things that caught my attention over the centuries as they happened. It's not the traditional order of things. In particular, I think I'll be mentioning how the sort of influences that AMO physics has had upon foundational questions of quantum mechanics, upon the very structure of quantum mechanics, but also on particle physics. I think that there was a time when particle physics was atomic physics. Atoms were the small things that we studied, but we still continue to be influential in that world. I should tell you I'm really not a historian of physics, and I'll mention various names of famous names in most cases for illustration, but I don't mean to insult the vast majority of equally famous people that I don't mention. Okay. When did AMO physics in particular begin? Very difficult. You could quote, Newton. You could quote Aristotle, but I would instead prefer to start with two famous monks or friars, I should call them. And my notes, I have them as Friar Enel and Friar Fraunhofer. Let me look at my notes more carefully. Fresnel and Fraunhofer. They are obviously, it's sort of amazingly parallel lives, lived through the Napoleonic era. And in my opinion, they even looked like they might be brothers. When I was arranging these slides, I had to go back to Wikipedia to make sure I had the right names, the right pictures next to the right names, and I'm still not 100% certain. Yeah, a lot of ideas that we now think of as atomic physics come from them, AMO physics come from them. Obviously, here in Paris, I don't have to tell you about Fresnel, but really he was the person who made the wave nature of light a fully quantitative discipline and fully inescapable. Like at some point you say, okay, there's nothing we can do about it, photons are waves. And Fraunhofer invented, okay, this is a strong claim, but you might say he invented spectroscopy, this famous postage stamp that shows the absorption lines in the sun, where it was actually apparently a painting that he made himself from his observations. Fraunhofer also contributed in the sense that there were diffraction gratings before him, but he made better diffraction gratings. And I actually thought that, well, before Fraunhofer, there were prisms, triangular shaped pieces of glasses for dispersing light, and afterwards are gratings. That turned out to be wrong. Prisms continued to be important. Even now, people sometimes will use prisms under certain circumstances for dispersing light, but even 40 years later in the 1860s, this guy, Kirchhoff, I teach second semester physics, and when I think of Kirchhoff, I think of Kirchhoff's loop laws for current flowing and these various things for doing electromagnetism. But he was also famous as a spectroscoper and invented various optics for doing really quantitative dispersive measurements with prisms. But in particular, he came up with these three basic rules, which is if you look at something which is hot and dense, you see a continuum of light. If you look at a gas, which is not too dense, you see individual spectral lines. And then if you look through the gas, through a cold gas at the hot object, then you see absorption lines, and many of those absorption lines, but not all of the absorption lines, not all of the emission lines you will see in the absorption. So this is not really quantum mechanics yet, but it's now sort of 50 years before quantum mechanics. It was laying out the sort of set of facts that quantum mechanics had to explain. Gratings got better and better, and I think there's a story of diffraction gratings getting better and better is the story of dispersing light getting better and better, and also I think sort of a story of AMO physics, which is we've always had a technological component. Many of Alain's students and many of my students work in the world of industry now. There's always been a sort of flow back and forth between commerce and industry and the science of light and matter. And the development of diffraction gratings I think is a particularly good example of it. The development of diffraction gratings through the last half of the 19th century was kind of like these days we make better lasers. It's really the same story. In my own country, in the United States, very early on, Benjamin Franklin, I'm not sure if I want to include this in AMO physics, but he did invent bifocal glasses such as I'm wearing now. But he's not otherwise part of the AMO story. You really had to wait around for about 100 years after Benjamin Franklin before there was a notable American AMO scientist, and that was Henry Rowland. He was the first president of the American Physical Society. And he invented a machine for scratching glass, basically for putting extremely parallel and extremely evenly spaced lines in glass, basically building better diffraction gratings. Here's what this guy looked like. I think of him sort of roughly 100 years, sort of as equivalent to a Jan Hall, or a Ted Hench, or someone who sort of took lasers and increased their ability to resolve, to disperse light by a factor of 1,000 or 100 or something like that. He was very much in this model, except 100 years earlier. He built machines. He built 2 or 3 machines like this. These are rulings for diffraction gratings. And it's not an exaggeration to say that really probably a majority of the spectroscopy, which was the high-end spectroscopy, which was done at the end of the 19th century, early 20th century, was done on gratings which came from his machines. There were just 2 or 3 of them, but they made a lot of gratings. You sort of imagine the analogous situation as if in these days there was only one laser company. It would sort of be like that. It was like that for several decades, the Rowland gratings. Eventually he did have some competition, and Albert Michelson in particular felt that he made better gratings than Rowland. Albert Michelson won the Nobel Prize in the earliest part of the 20th century, and when I was doing a little research for this talk, I found a quote from a spectroscopist, George Harrison. In addition to his guitar skills, turned out to be a very good spectroscopist. He was a professor at MIT. And this quote, charmed me so much I had to include it. He was writing in 1950. He knew Michelson, and he was writing about the story from 30 or 40 years before when Michelson won the Nobel Prize. Harrison wrote, "Michelson took his first 10-inch grating with its 100,000 grooves to a banquet held to celebrate the award to him of the Nobel Prize. The grating was to be taken to Sweden so that the king might see how well justified the award had been, and at the dinner it reposed on a table in front of Michelson in a handsome wooden case. During his after-dinner speech, Michelson raised the box to display the grating, but the cover had come unlatched, and the precious grating fell to the floor where it broke into several dozen pieces. Harrison was proud to have like a small piece of the grating which broke on the floor in the Great Hall in Stockholm. And this began a tradition of ill-advised people bringing ill-advised things to the Nobel ceremonies in Stockholm. Myself, shortly before leaving to Stockholm, I scooped up one of my largest and coldest Bose-Einstein condensations, put it in my pocket so I could show it to the king, but it melted on the airplane and ruined my good pants. And I think we should all take the opportunity when we run into Alain and ask him what he brought to show to the king in order to convince the king that this award was well justified. I will skip over some things which are sort of in the traditional story of AMO physics and the beginning of quantum mechanics. I think we know the relevance of black body radiation and the ultraviolet and infrared catastrophes associated with the shape of the spectrum of hot bodies. The hydrogen spectrum obviously was very motivational to Bohr and to quantum physicists ever since. I'm going to jump instead to another guy, this guy, Pieter Zeeman. I wrote Zeeman, I'm sorry, it's Zeeman. Working in particular at the very end of the 20th century. He knew that Faraday had applied, Michael Faraday, who was influential in thinking about polarizations and magnetic fields. He had applied a strong magnet. Faraday had applied a strong magnet to a flame and tried to disperse the light that came out of the flame, but he saw no effect in the spectrum. But again, and I think this is something that happens in physics so many times, you try to answer a question and then 20 years go by and the technology is better, experimental techniques are better, and you go back and look at the question again, and Zeeman did this. And now with a very high-end grating and a larger magnet, he saw that when he applied the magnetic field, the diffraction line, the lines broadened, the various spectral lines got broader, and it eventually got to the point where he saw that the lines were not only broadening, but splitting into three distinct lines, some sort of Zeeman splitting. This picture, by the way, is not that particular picture, but it's the sort of practice of taking these lines and putting them on photographic film came just a little bit later. So this picture is slightly anachronistic by about a decade. Zeeman and Lorentz at Leiden had a model. They had no quantum mechanics, but they had electromagnetism and they had classical mechanics. And they said, well, suppose an atom it has a charge on a spring. And the particle can move in 3 dimensions with a frequency, think of it now as a 3-dimensional harmonic oscillator, spherically symmetric, so there's a frequency omega naught. And then there's also a magnetic field. And so if you solve, there are 3 normal modes, and the 3 normal modes have frequency omega naught, which is the frequency along the direction of the magnetic field, and then omega naught plus the Larmor frequency and omega naught minus the Larmor frequency. 3 frequencies quite close to each other, but perhaps it's the triplet. And so they liked this idea, but then when they thought about it more carefully, they thought, well, we can look at this formula here. The frequency, the line should be split by a frequency which is whatever the charge is on this thing and divided by its mass. They had no idea what that charge or mass might be, but they could extract the charge to mass ratio. And when they did this, they got a number which was a factor of 10,000 too large compared to what they thought it should be. Again, this was before we had a fully atomistic theory of matter. We don't know exactly how small matter is chopped up to, but from electrochemical measurements, you flow some electricity into a electrochemical cell and you get a certain amount of stuff plated, a certain amount of chemicals released, you can get an idea of the charge to mass ratio of ions of matter. And whatever this thing is, it's either much, much more electric or more likely much, much, much less massive than the ion. What is that thing? We know today it's the electron. This was really perhaps the first piece of evidence for the electron. So this is people doing, for what in the day was the most precise spectroscopy done, and in doing this most precise possible spectroscopy, they had discovered a new particle. This, of course, I just showed this because this is apparatus from the turn of not this past century, but the century before. I put it up there because to an atomic physicist, this looks actually fairly familiar. You can see a scale down there. Look, there's some flanges, there's a vacuum. Looks like an optical feed-through, an electrical feed-through. I could have something like this in my lab. I would think, well, this is probably a little old. I might not guess that it's 120 years old. And this was, in fact, where the oil drop experiment, one of the first pieces of evidence for discreteness of matter, happened. But looks familiar to us. This, if you look more carefully at the spectrum, the idea of one line turning into three line turned out to be not the rule, but rather the exception. More typically, one saw a complicated series of lines and a behavior with magnetic field, which became known as the anomalous Zeeman effect. And someone saw Wolfgang Pauli sitting at a table, and he was looking unhappy. And they said, what's the matter, Professor Pauli? He said, how can one look happy when he is thinking about the anomalous Zeeman effect? And it's true. It's a disturbing thing to worry about. I remember that from my original classes. And eventually people came to realize that the electron has spin one. There's an electron with spin 1/2, and that it has a G factor, an effective magnetic moment, which is twice what you might otherwise believe it to be. This, in turn, was this is one of the two experimental pieces of evidence early on for the Dirac equation. This guy, Dirac, invented an attempt to reconcile quantum mechanics and special relativity, and there was he post-dicted, basically, they already knew that the G factor of the electron was 2 and not 1, but he explained it using his theory, and he also predicted antimatter, which appeared shortly thereafter. So again, the anomalous Zeeman effect, the best spectroscopy of the day, predicted important results from particle physics and for quantum mechanics. Through the teens, the 19-teens, 20s, and 40s, molecular spectra, such as this one, you see multiple rotational bands, and the effect of the different vibrational bands were as much as atomic spectra at the basis of our developing understanding of quantum mechanics. This stuff is from the 1930s, but it's a particularly nice spectrum. But the harmonic oscillator, which people originally used to explain the atomic spectra, actually exists in molecules. And I think maybe perhaps more important is if you look at the spectra of rotating homonuclear diatoms like nitrogen or oxygen or something like that, and you look at the rotational lines, there are lines which are missing in some cases. Sometimes even lines, sometimes odd lines are missing. And people are doing call them quantum bosonic and fermionic interference. Like we were just talking at lunchtime with Jean Dalibard about experiments you can do with entangled fermions and bosons. And in any case, in a very early time, you could see missing rotational lines because various rotations are not allowed by statistics. And this was before Fermi statistics and Bose statistics existed. Molecular physics plays a part in the story I want to tell today. Among other things, there was some of the famous people doing it. This is John van Vleck, who was a noted molecular physicist. Where he fits into his story is that as a molecular physicist, he trained another molecular physicist, famous for his molecular spectroscopy, this guy. Oh wait, maybe that's not so much what he's famous for. But this guy, Phil Anderson, our good friend, actually learned his quantum mechanics in the context of molecular spectra. That was what he did his PhD thesis in. And so it's not so surprising. This was, in those days, there were people building synchrotrons and trying to build bigger and bigger accelerators, and there were people instead using quantum mechanics to understand the stuff around us, like molecules and condensed matter physics. And Anderson was very much in this tradition, and now we think of him as perhaps not just a condensed matter theorist, but more or less the condensed matter theorist. But in fact, he comes from this tradition of, as I see it, from AMO physics. So we'll claim credit for him. Why not? I want to switch briefly to the correspondence principle. Depending on what year and with which professor you learned quantum mechanics, the correspondence principle is either extremely important or extremely not. And I think these days one perhaps learns a little bit less about the correspondence principle. When I was learning physics, it was presented as extremely important. Whatever the pedagogical usage of it is, my view is that it's extremely useful for two rather orthogonal reasons, the correspondence principle. And I'm using this term there have been attempts to make this the correspondence principle, this idea that we know that classical mechanics is right, and not just right, but very, very quantitatively accurate. Now we have this whole new theory of physics, quantum mechanics. Quantum mechanics, we can't allow quantum mechanics to screw up everything that we know about classical mechanics. Classical mechanics is already a very, very good theory. Somehow we have to protect classical mechanics from quantum mechanics, and the correspondence principle is an attempt to say, well, under all the right limits, quantum mechanics becomes classical mechanics. And so this is one reason. It can convert, we all have, or many of us have, a stronger classical intuition than a quantum mechanics intuition. That's probably not true for the young people of today, but was certainly true for me. And we can convert our knowledge of classical mechanics into insights into quantum mechanics. And these insights are not only heuristically helpful, but often are quantitatively quite precise and accurate. That's one reason why the correspondence principle is useful. And the other reason is a correspondence principle can convert our knowledge of classical mechanics into insights into quantum mechanics, which are spectacularly incorrect. So both things happen with the correspondence principle. And in some sense, the fact that both things happen, I think, is part of the value of the correspondence principle. It allows us to understand where is quantum mechanics at its purest, at its most counterintuitive, at its most, in some sense, sort of exciting and spectacular. It's in places where the correspondence principle explodes in our face. And so that's okay, so we'll just discuss a little bit of both cases. In the early 1960s, we could predict, when I was first reading the newspaper, I would open up the newspaper in Boston, as it turned out, and at the very bottom they had a prediction of the weather for the next 2 days, and they had sort of almost like in fainter print the prediction for the 3 days out, because that was probably not going to be very accurate. Fortunately, in the intervening 50 years or so, computers have gotten 1 billion times more, roughly speaking, 1 billion times more powerful. And therefore, it's easy to do this extrapolation. We can predict the weather 3 times 10 to the 9 days into the future, 3 billion days into the future. Okay, I'm cheating. Now, actually, when we do things numerically, weather is predicted on a 3-dimensional grid, and there's time, so we have to take 10 to the 9, a billion to the 4th power. And indeed, weather prediction is good for about 500 days. No, it's not. In fact, weather is good for the increase of computing power of about 1 billion. Took us from predictions 3 days out to about 8 days out. I think if you look at a correlation function between prediction and actual values, it has mostly decayed after 8 days. It's certainly decayed down to less than a half after 8 days, maybe it's less than that. So this is a function of classical chaos. Oh no, sorry, it's not classical chaos at all. In fact, there's an important quantum mechanical uncertainty principle, which I think was formulated by Heisenberg. One cannot simultaneously know to arbitrary accuracy both the calendar date and the temperature outside your physics laboratory. Of course, it's absolutely not a function of, there's hardly anything more classical than weather. And this is a chaos effect, basically, in nonlinear systems. Tiny differences in the initial conditions exponentially grow with time, and this is if things are being driven hard enough or the system is sufficiently nonlinear, you get chaos. Okay, so that's classical chaos. Just as I was, when puppies are first born, they're very small puppies and their eyes are closed, So right around the time that my puppy eyes were opening, I was perhaps a first-year graduate student or something like that. The connection between quantum chaos and classical chaos was an extremely fruitful and interesting series of discussions in those days. I'm not going to really talk about this very much, but we can ask ourselves, what does the correspondence principle? Correspondence principle says, okay, in classical physics, we have chaos. What do we have in quantum physics? If we have, after all, we can have exactly the same Hamiltonian, the Hamiltonian which gives us classical chaos. What does it do in quantum physics? And it's a complicated question. Many people have contributed to this subject, both in terms of theory and in terms of experiment. Atomic and molecular spectra, especially in high electric or high magnetic fields, were a noted model system for sort of understanding these things. The relative spacings, the statistics of the spacings between adjacent energy levels turned out to be a very productive thing to study. Here's a calculation. This particular potential here is just a hard-walled circular potential, and you can see the behavior, a classical behavior. A billiard is just bouncing off of the walls, and it forms this very regular pattern. In this very regular this is a non-chaotic potential, and the classical behavior is not chaotic. And the quantum behavior is very nice. So here are this is the 100th excited state of a wave function inside here. Here's the 1,500, this is the state which is numbered 1,500 up from the ground state. You see has a very regular pattern to it. No problems here. And then we take a potential which indeed still has a fair amount of symmetry, but which gives rise to chaotic behavior. If you launch a single billiard, and it will go in a very complicated pattern. If you launch 2 billiard balls, one after the other, and each one has a slightly different trajectory, in only 3 or 4 bounces, their positions in here will be fully uncorrelated, having exponentially grown to cover the entire chamber. And this maps over, whether you want to call this the correspondence principle or not. Here's the 100th state. You can see that instead of forming some regular pattern, the wave function fills the entire space. There is a pattern to it. There's places where you see atoms and places where you don't see atoms. If you go up to the 1,000th level, this atom, non-atom thing is on a correspondingly finer structure, and by the time you're up to 2,000, this looks almost gray, basically. And this is, whereas in the classical case, there's still very regular patterns. So here's an example of sort of quantum chaos, if you want to think of it this way. It's a very small step, I think, to go from a potential which is classically chaotic to a random potential. After all, if a potential this simple is chaotic, then we go to, this is supposed to represent a potential which is random. Sorry, this is the best I could do with my PowerPoint drawing things. If this is ergodic, if this is random and also irregular, it must be even more ergodic, right? Right? Oh, wrong. No, Phil Anderson tells us, no, it's not right. Under certain circumstances, and we've heard already quite a bit about what those circumstances are, you could get behavior where you start with particles in a certain region and the particles stay there. They are not ergodic, they do not fill up they do not diffuse to fill the full possible space. We've already heard extensive lectures on this, but I just want to point out that, of course, Alain Aspect and his friend and mine, Massimo Nguscio, and their respective groups have done beautiful, beautiful work on this topic. So just wanted to bring this into this topic of why AMO physics is wonderful, which is probably a shorter version of my title. Returning to the correspondence principle, when does it apply? Usually one thinks if you have very large quantum numbers like Rydberg atoms, or less formally with large length scales with lots of particles, quantum tends to fade into classical. Except, well, as for large length scales, famously 12 meters. Where do I heard the number 12 meters before? 12 meters is the distance between detectors in Alain's original entanglement experiment with the widely separated things. Again, a situation where quantum mechanics is not frightened by the very, very large distances of 12 meters. Quantum mechanics says, oh, I can handle that. I'm still going to be, you can look across 12. You may think that quantum mechanics lives inside of atoms or maybe molecules, but in fact, quantum mechanics lives across 12 meters. So there are many things which were amazing about these measurements, but one of them was the sort of the massive length scales over which quantum mechanics continued to apply. I won't say very much more about it, except to say that when Alain wanted to find himself two, I think we call them now itinerant qubits or flying qubits or something like that. He knew where to find them. He found them in an atomic system. And so no surprise there. This is as so often in the past, atomic systems, our friends, the atoms, the molecules, and the atoms, the molecules, and the photons. These days, we don't often, in our field, we're not studying atoms, molecules, or photons so much. We're using these very well characterized tools, atoms, which we understand extraordinarily well, small molecules as well, photons, for which we have coherent sources to go out into the rest of the world of physics and to play. So 12 meters. And as for lots of particles, now I'm looking forward a little bit. This is not so much a history of atomic physics, but a future of atomic physics. A quantum computer has a lot of particles, and I feel like the quantum computer, especially a large-scale practical quantum computer, is the ultimate example of human people saying this to the quantum mechanics, to the correspondence principle. It's like, here we have now many, many thousands of atoms. Show me where this is classical anywhere. So, okay, hasn't happened yet, but already we have some examples across long distances. Going back to the electron's magnetic moment. It's somewhat surprising to me that diffraction gratings stopped getting better, more or less. I mean, we still have diffraction gratings. You can buy a diffraction grating today, which is better than the diffraction gratings that they had 120 years ago, but not very much better, not an order of magnitude better. But spectroscopy itself has gotten much, much better, and that's because of, originally it was because people did spectroscopy in the ground state using coherent photon sources, which were not lasers. They were radio transmitters and microwave transmitters, which were basically essentially lasers from the point of view of spectroscopy. So this is, I think I've already mentioned this, like maybe the two secrets of the ongoing relevance of AMO physics, even though to physicists, even though atoms, molecules, and photons are well understood, we have these very powerful tools and very flexible tools, atoms and coherent sources. Using not diffraction gratings, but with a microwave experiment, people looked again at the magnetic moment of the electron. They discovered it's not 2. It's 2 plus alpha over pi. Basically, fractionally speaking, it's about a factor of 1,000 too large. So the fine structure is already fine, and if you can measure the fine structure to a part in 1,000, you realize that there's something strange going on there, not contained in the Dirac equation. And this is still part of this tradition of new particle physics coming from precision spectroscopy. When they first discovered that G is 2 for the electron, not 1, this was a test or a proof or a validation of the Dirac equation. When they discovered it's not 2, but 2 plus alpha over pi, this was one of two early tests of one-loop quantum electrodynamics. Schwinger and Feynman famously calculated the effects this would have on the electron G minus 2, and they got this effect here. And now, from the experiments in Jerry Gabriels's group and equally impressive theoretical achievements, they've been able to compare the G minus 2 factor of the electron experiment in theory out to part per trillion, basically 5 loops of. I don't think Schwinger or Tomonaga or Feynman or any of these people ever really imagined that fifth order perturbation theory would be relevant, but it was relevant and correct. We can think of this extra factor of alpha over pi as arising from the electron emitting a running particle, a photon, which appears for a little while but is reabsorbed. In the meantime, the electron interacts with a static magnetic field, then it reabsorbs this virtual photon, and the effect of this diagram gives us this additional contribution to the magnetic moment, but not to the electric moment. We can generalize this. And instead of having a photon here, we can have an electron go along. Electron can split virtually into a particle A and a particle B. The particle A can interact with the magnetic field or an electric field. And then it can sort of recombine with these two virtual particles can recombine. And a term like this can give us not only a magnetic moment, but an electric dipole moment. And people have done the calculation. If you just sort of roughly assume within a factor of 2 that these two particles, hypothetical undiscovered new particles, if you assume these new particles have a mass with they're comparable masses, which we'll just write as capital N, say within a factor of 2 of each other, gamma as the I was getting a little carried away with my PowerPoint skills. This is supposed to be G. The G is the coupling constant at the vertex. Phi CP is some CP violating angle. Then people have calculated for this sort of diagram a contribution to the electric dipole moment and a contribution to the magnetic dipole moment. The contributions are almost exactly the same, except that in both cases they have a contribution which goes as the mass of your fermion, which could be an electron or it could be a muon, times the mass of the hypothetical particles, the square of that ratio, a trigonometric function having to do with whether there's CP violation or not, which corresponds to electric dipole moments or magnetic dipole moments, and then some constants like this. This is the idea. The idea is that you could go and measure the magnetic dipole moment, or you could measure an electric dipole moment. You could subtract away everything which you can account for by understanding the standard model physics, and anything less presumably comes at the lowest order from a diagram that looks something like this. So you could perhaps discover, if you like, even as atomic physics discovered the electron in 1890s, maybe we can discover new particles now 130 years later. Possible? I don't know. We're going to try. We are trying this. You can take something like this and invert it and say, oh, if I see a change in my electric dipole moment or a change in my magnetic dipole moment beyond what is predicted in the standard model, then I have predictions for the masses, although unfortunately there's a great uncertainty because you're really predicting sort of a combination of the mass of the unknown particle and its coupling constant G to the electron, or the mass of the unknown particles and their coupling constant to the electron. As it turns out, looking at lepton dipole moments, these last 2 years have been experimentally lots of news. There was a muon magnetic dipole moment measured at Fermilab. There was an electric magnetic dipole moment measured in Jerry Gabriels's group, formerly at Harvard, now at Northwestern. And just recently in my own group, actually jointly with Juin, we have a new, more accurate measurement of the electron's electric dipole moment. And so all three of these can can contribute to this. Here is the electron magnetic moment. And this is the red line is this new measurement from 2022 from Gabriels's group. And in order to compare it with the standard model, we have to know the fine structure constant, which we can measure using rubidium. And we can see that these numbers are in disagreement. And it's also in disagreement with the fine structure constant measured with cesium, but in the opposite direction. Okay, this is a little awkward. And it comes from the fact that currently in atomic physics, measurements of the fine structure constant in rubidium and cesium are not agreeing. And presumably this is because of these experiments are extraordinarily difficult. We expect, I expect and hope that these numbers will be reconciled. But it actually serves as a reminder that these measurements of the magnetic dipole moment come against what's called the standard model background. This is not really zero. They just actually constrain this point to sit at zero. It's not really a prediction for new particles until you're able to successfully subtract out the standard model background. And you can see this is on 1 part per trillion. You have to have a very good idea of what the standard model background is before you can start saying, yes, we see something new. A similar thing happens with the muon magnetic moment. There was, this is the most recent muon magnetic moment. This is the prediction from the standard model. It was differing by 4 sigma, which in the world of particle physics is significant statistical, what's the word they use? Tension. Significant statistical tension, 4 sigma, meaning statistically this is not very likely to happen. However, there has a new calculation has been done. This is a very difficult calculation. This calculation depends on knowing how the muon can virtually emit not an exotic new particle, but non-exotic particles, quantum, like gluons and W particles and so on, and understanding all these connections in the chromodynamic, the hadron sector is a very, very difficult calculation, a very difficult measurement. And there's now, it turns out that these corrections have a lot of uncertainty in them, which seems to have gone a long ways towards resolving this tension. How am I doing for time? 5 minutes and then questions? Good, perfect. Okay, so the advantage of measuring the electric dipole moment is that in the standard model, the electron-electric dipole moment is predicted to be 0, so we don't have to subtract any background. In order to measure it, we put electrons in a molecule, a polar molecule, which has a very large electric field. We apply only 10 volts in the lab, and we get effectively 9 orders of magnitude larger, 10 to the 10 volts per centimeter, applied effectively to our electron spin. Then we do the spectroscopy. Bill will appreciate that in order to show the scale of this, I put an SI artifact. This is the standard length of 6 centimeters here. This is the 6 centimeter length artifact, and you can see it gives a scale to the size of, we have a very large ion trap compared to most experiments. Because we have to apply an electric field and because we are trapping our ions to get our molecules to get long coherence times, the electric field would cause the molecule to fly away. We actually make our electric field rotate, which means we have to deal with Berry's phase and many other exciting things, but we know how to do that. I won't talk very much about what the experiment looks like, except that it is extremely complicated. We have not 1, not 2, but 9 coherent electromagnetic sources, 10 if you count the microwave. So it's a very, very complicated experiment and took a long time to do. Many different lasers, lots of optical pumping techniques. I won't talk about one of our primary systematic errors, which is associated with Berry's phase. If you have a rotating quantization axis, there's an additional angle added to your quantum coherence every time you make a rotation around. That has to be accounted for very precisely. It turns out that gravity matters. And here's, we took the data for 500 hours of data. This took about 5 months. We took the data blind because the result actually matters and you don't actually want to know what the answer is until you've decided what the error bars are. Here's Juin, my longtime colleague in that. I want to call out in particular Luke Caldwell. And not shown here, she was absent on the day we unblinded the data, Tanya Rusi, who was a senior graduate student, and many other graduate students who helped with this project. This was, I would say, because it represented the culmination of 6 years of development, was one of the single most tense moments in my professional career, because we knew already that our error bars were considerably smaller than ACME. We also knew that the ACME central value was offset from 0. So it was entirely possible that the ACME value was offset from 0, but not statistically so much. It was in some units 4 plus or minus 4. We could measure 8 plus or minus 2, and that would be consistent with ACME, but distinctly not consistent with 0. Could have happened, did not, as it turned out, but it was a tense moment. There is the ACME result at 0.4 plus or minus 0.4 away from 0. Here is our measurement, basically minus 0.15 plus or minus 2. Traditionally, one takes these things and converts them into a 90% confidence interval on the absolute value. So this blue bar here is what ACME reported. We reported something smaller by a factor of about 2.4, but again, completely consistent with 0 at the 90% confidence level. All a little disappointing, but also very exciting because we can turn that around and we can compare it. Actually, first thing we can do is we can compare it to the magnetic dipole moment measurements. I mentioned before we were all educated in different ways. In the system I was educated, electric and magnetic fields have the same dimension, and therefore electric dipole moments and magnetic dipole moments have the same dimensions, and I can report them in the same units. You don't usually see magnetic dipole moments reported in eV centimeters, but you can. There's nothing wrong with that. And so our measurement in terms of a dipole moment is 6 orders of magnitude more accurate than the electric magnetic dipole moment. Almost, it's even more accurate compared to the magnetic moment of the muon. The muon is a heavier particle. So if you compare this in terms of sensitivity to new particles, we can put it into a formula like this, and we find that we are sensitive to new particles which are roughly 1,000 times more massive than the magnetic moment experiments. So we have immense sensitivity, and not just to the magnetic moment experiments, but also to the Large Hadron Collider, which is in some sense our competition in the business of discovering new particles. You hear of the Large Hadron Collider as having 10 tera electron volts collision energy, but they don't actually collide protons, they collide quarks. At that energy, what matters is the energy of the quarks, and the individual quarks have much less energy. Practically speaking, their sensitivity does not really get up, barely gets into the 1 or 2 or perhaps 3 under certain circumstances, tera electron volts. We have sensitivity into the tens of tera electron volts in a way which is very model dependent. But it must be included that if you want to describe the Large Hadron Collider as being sensitive above 1 tera electron volt, they also are only sensitive to particles of those large masses under particular models of how the interactions would go. So I guess I want to say that we're back in the business of AMO physics is in the business now. Condensed matter physics. We've heard from Bill Phillips, fundamental units and constants. Many other kinds of physics do we wander around in. The foundational issues of quantum mechanics, and particle physics. Now, as before, as 130 years ago, we're very much in this business. We're a discipline without boundaries. Alain Aspect really, I would say, exemplifies that. We wander wherever we want to. I have barely touched on the myriad ways that a scientist working in AMO tradition of our original two friars, Friar Enel and Friar Aunhofer, have contributed and can continue to contribute over many subdisciplines in physics and beyond. Alain Aspect and his colleagues and collaborators have played a pivotal role in this ongoing story. Congratulations, Alain.
Thank you very much. We see that there's still a lot of work to do. Okay, we have time for a few questions. So first, are there questions in the other amphitheater?
Well, we're waiting. The amphitheater is waiting. I want to tell one more story about Alain, which which was my origin story with Alain. I first met him in a conference in New England. Alain was having lunch at a Gordon conference, and he announced to the table that afternoon he wanted to go windsurfing. But it was only possible to rent the windsurfer for 3 hours or something like that. And no one can windsurf for 3 hours. It takes maybe some people are that strong. But so he wanted to windsurf for less time. And he wanted to know, did anyone want to rent the other half of the windsurfer? I had never windsurfed before. I said, oh, I'll try that. So Alain went and windsurfed for an hour and a half. And he came back ashore and gave me the windsurfer. And then I did not windsurf for an hour and a half, but 15 minutes of the most miserable time I've had in my life. And so in some sense, I blame Alain for this and did not speak to him for several years thereafter. Not true, of course. And then since then, for every other year, more or less, for 20 years, we've gone for a ceremonial run at the Bose-Einstein conference and in many other situations as well. I value my friendship with you, Alain, and I have learned so much from you. So congratulations again.
But there are always unpredictable results.
Yeah.
Okay, no questions? So questions from the room?
Christophe.
and Bill. Christophe?
On the dipole moments, okay, I'm really fascinated by the formula you wrote down with a sine and a cosine.
Yeah.
And I'm wondering, okay, so can I just say, okay, so if I think of this as being a measurement of an angle, both the electron muon and the magnetic dipole moments and the electric dipole moments, they both put a limit on this angle, right?
Yes.
And so how do those compare? I want to say that the EDM measurements are quite a bit better, but actually I couldn't do the math in my head, and so broadly, I'll make the second part of the question is, well, how universal is a model like that?
We don't have much time.
Is that just a toy model that you make up to explain it to people who only understand sines and cosines?
Really what it said is, all that really says is that if you have some piece of physics, the sum of its contribution to the CP violation and the sum of its contribution, okay, we take the ratio of those two things, of its contribution to the CP and non-CP, and call it an angle. There's no real angle. And as for the contribution, the relative contributions, there are enormous error bars, a factor of 1,000 in the x-axis, and tiny error bars, a factor of 1,000 smaller in the y-axis from our experiment. But an angle could be anywhere in 2 pi because you're measuring a length and an angle. So if you know that it's a very long line, I can tell you that the angle is very, very close to 0. But no one knows that. Do you see what I'm saying? So it's there's an exclusion zone in real and imaginary, if you want to think of that, which is extraordinarily elliptical along the x-axis. It's very narrow in the electric dipole moment and very large in the magnetic dipole moment.
Okay, so Bill?
So first, just a very brief comment. I loved your reference to Zeeman's paper. It's something like one column in Nature, you know, and it revolutionized, and we write all these long papers that don't do anything.
To be fair, read the next page in Nature and you'll find nothing interesting.
Yeah, right,
Yeah.
but it just, you know, it was an amazing time. And he looked at the polarization of the light on the edges of this broadened line and found that they were more circularly polarized, one direction on one side and one when he looked along. I mean, that's just astounding, and then concludes that atoms must be made of electrical bits before most people believed in atoms.
Yeah.
And, but anyway, the question that I had was, would you say something more about this Berry's phase and how gravity comes in?
Oh, yeah, I'm very happy to. So we have a rotating electric field, and it rotates in basically in the horizontal plane, X and Y. And it better because you know that every time it goes around, it picks up 2 pi additional angle, right? Typically, when you think of Berry's phase, you have a quantization axis which is tracing out some small little angle, and you pick up that angle each time. But if you're in the axis, you pick up 2 pi every time you go around. This is what saves us, because 2 pi is the same as 0 in an angle. If instead we have a slight angle upward, we're totally out of luck. Or if we slight angle downward, we're totally out of luck. But how would we, if we apply a rotating field and electric field, the way it would be tilted upward is if we had a static electric field pointing upward. In an ion trap, the ions will never feel a static electric field because they'll just move upward to where the electric field averages to 0, unless this circle is in the horizontal plane and you have a non-electrical force like gravity pulling that molecule down. That ends up giving us about a millihertz of frequency shift, and we're trying to see 20 microhertz of shift. So it's a serious effect. Gravity is real. However, for other reasons, it's what I'd like to emphasize is not actually very easy for us to see that. What we do is we subtract. We take data in such a way that subtracts it out. The same data subtracts out another effect, and we can't tease out those 2 different effects. But by basically taking data clockwise and counterclockwise, we can subtract out the effect, and we're not worried about it as a systematic effect. But it's interesting that the raw size of the effect is large compared to our raw sensitivity.
Okay, so thank you very much.
Thank you very much. Well, thank you, Alain, dear Alain. Thank you because you made me so happy that at last, the Nobel Committee recognized Bell inequalities. And this is, I think, the perfect occasion to go back to foundations and ask this question, non-locality or signaling? Now, by signaling, I mean, faster than light influences that could explain these strange quantum correlations. Now, of course, faster than light signaling, or influences, is clearly not in accordance with the spirit of relativity. But after all, we have learned, thanks to Alain and many others, that asking questions like whether quantum mechanics is complete is actually a good question. So maybe today I'd like to allow myself to raise the question whether relativity is complete. So I think it makes sense, so at least in the next half hour, I will talk about the possibility of finite speed hidden influence. But finite speed doesn't exclude faster than light, but finite speed hidden influence. And suppose that something like that is actually explaining all these correlations that we have observed. Because it's faster than light, you have to define them in a privileged reference frame, possibly the one in which the cosmic background radiation is isotropic. So they exist privileged reference frames, but it could be any other one. And by the way, if you have faster than light signaling influences defined in a privileged reference frame, there is no grandfather paradox. But then maybe these potential hidden influences would just remain hidden. They are, let's say, subquantum, whatever exactly it means. They're just hidden. We don't have access to them. For sure, they are hidden according to today's physics. maybe they may remain hidden at that kind of level. And that would be a kind of explanation, which is still a kind of mechanical, bit old-fashioned explanation. Let's investigate that. So I think it makes sense to investigate that. And actually, to start that and motivate also that, let's go to another theory, which is very well known, which also makes non-local predictions. That's just Newton's gravity. You know, according to Newton, if you would move, according to Newton's theory, if you would move a stone on the moon, that would have an immediate effect on our weight here on Earth. And of course, already Newton was asking the question, so how could these two regions in space-time know about each other, you know, the moon and Earth? Of course, today we know that this is the theory, that reality are gravitational waves and so on. But still, we have here an example of a theory, of a well-known physics theory that has some non-locality. And here, just to recall, remind you, Newton himself was very puzzled by this non-locality, so he wrote that one body may act upon another at a distance for a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one to the other, is to me, so to Newton, so great an absurdity that I believe no man who has in philosophical matter a competent faculty of thinking can ever fall into it. Huh? Nevertheless, we still teach this theory to our high school students. Okay, so let's see whether something like that also could happen in, with Bell non-locality. So signaling here is sending information that one has. I start here from Landerer's principle. Information is physical. Hence, to send information, one has to encode it into some physical support and send that physical support. Encode it in photons, you send the photons, or in a letter, and you send the letter. And any other way of communication would be non-physical. Moreover, if one could signal this non-physical communication, then of course distance doesn't matter, so you can go faster than light. Actually, you can go arbitrarily fast. So here what I want really to emphasize is that the speed of light is not part of relativity. So signaling according to relativity is just this non-physical communication. Has nothing to do with the speed of light or with Minkowski space-time and things like that. Okay, so let's assume a kind of principle of continuity. And according to that, so everything moves contiguously from one place to the other. In French, there's a nice terminology, se propage de proche en proche. I think in English I would say contiguously, but I'm not exactly sure. And then we know that there are only two kinds of explanations of correlations. It's either the common cause, excluded by Alain Aspect and others, or these influences at finite speed. And so here, you know, the explanation by local hidden variables, this leads to Bell's theorem, and this has been falsified experimentally. Let's look now at the other one, the direct cause. So here we have influences. They might be hidden, at least they're certainly hidden today. Let's suppose now that they are at finite speed. This is really the topic of my talk today. So we start from this curiosity lab, and I name it the curiosity lab, and I can certainly witness that, confirm that, sorry, that at that time, this was just curiosity. Not many people took it seriously, not even in Paris, correct? So let's go to the real-world lab, and then you can do essentially the same, just over 10 kilometers instead of 10 or 12 meters. And you still see that it's not only in obscure laboratories down in some basement not far from here that you can violate this Bell inequality, but it's really in nature that you can do it. So nature, in some sense, violates Bell inequality, so excludes, you know, the common cause explanation. So again, let's go to the direct cause possibility.
Je pense que ton micro frotte. Est-ce que tu pourrais pas le mettre un peu ailleurs? Il faut parce que la chemise, ça fait un bruit bizarre.
Ouais.
Comme ça, c'est mieux? C'est mieux? OK. Merci, Philippe. Should I start again? No. OK, so real world. But you see, here we have distances, and distances are going to be important. So let's assume that this real influence. So we have our usual Alice and Bob, and we make a choice here of which measurement to perform. And then there is some hidden influence that goes on the other side, and then we do a measurement there. Of course, already Alain did better than that. You know, you had this space-like separation. But now let's suppose you really do very good timing, and then for sure this hidden influence, if it goes not fast enough, it will arrive too late. And then if it arrives too late, you can no longer violate Bell inequality, if this is really the explanation. So if everything is based on these local variables, the lambda, and this hidden influence. OK, these I have already said. So if everything is defined in a privileged reference frame, there is no grandfather paradox. So here we did the following experiment. OK, again, 2 villages near Geneva. You see Geneva and the lake Geneva here. And important reason why we changed the experiment from the previous one is that this one is almost exactly east-west. And this is important for the following. So we have some distance. We want this good timing. But good timing in which reference frame? And so here, in order to choose this reference frame, we use for the idea that if we have Alice and Bob east-west, and we have in this local reference frame very good synchronization, then this very good synchronization is also correct in every plane which passes through the north and south pole, every plane which is perpendicular to this east-west orientation. And then Earth rotates. And now if you have this plane and it rotates 12 hours, you see that during 12 hours you scan all possible reference frames. So what we need to do, according to Philippe Eberhardt, is to violate Bell inequality continuously during 12 hours over this relatively large distance. So here we did it. So here it's just 6 hours, but you see the 2-photon coincidences, so what is also named 2-photon interferences, and you get what is expected. And you see that it's not 100% visibility, but pretty good. And then we here just present the visibility that were collected over 4 times 12 hours, so 2 times 24 hours. And clearly they are systematically and continuously above this 1 over square root of 2, the 71% here. So we have continuous violation of Bell inequality. And we have scanned all possible hypothetical privileged reference frames. Very nice. Then we compute what is the bound now, because of course it's a real experiment, so nothing is perfect. So for instance, it takes a few minutes to violate the Bell inequality. It takes also during that time, Earth rotates a bit, so it's not perfect. And also the analysis depends on the assumption, on an assumption, namely what is the speed of Earth with respect to this hypothetical privileged reference frame. Let's suppose it is lower than 300 kilometers per second. This is, of course, a bit arbitrary. But if we make that kind of assumption and do all the error analysis, also it's not exactly east-west. There is about 6 degrees, if I remember well, off the east-west. We were slightly off that east-west direction. But nevertheless, we get as a bound something which is of the order of magnitude 100,000 times the speed of light. So probably every reasonable physicist stops here. Probably every reasonable physicist stops even before that. But I'm not a reasonable physicist. OK, so 100,000 times the speed of light. But so, yeah. And maybe the influence simply propagates faster than that. Maybe it goes at 1,000,000 times the speed of light. After all, what are natural speeds? There is the speed of a man walking. There is the speed of sound, which is significantly faster. There is the speed of light, which is, again, way faster. So maybe this speed, if it exists, is again 1,000,000 times faster. And if it is 1,000,000 times faster, we haven't excluded that. So if we do now another experiment, and I think it would make sense to make another experiment, well, the only thing would be to, again, just put a better bounds. But we can never exclude it with these experiments where you have only two parties. But quite surprisingly, at least to me, that came, oh, okay, I'll come back to that, sorry. And now, to motivate also, I'm not the only crazy person. So there are also these ones, and others, okay. So for instance, John Bell was saying, so correlations between distant events strongly suggest that something is going on behind the scene. You know, that maybe there is some hidden influence, subquantum, that remains hidden to us. Or here you have David Bohm in his book with David Haley. It is quite possible that a quantum non-local connections might be propagated not at infinite speed, as it is according to Bohmian mechanics, but at speeds very much greater than the speed of light. In this case, we could expect observable deviations from the predictions of current quantum theory. This is actually very good because this is real physics, because at least it could be wrong. And you can also just read textbooks. Now, in a textbook, most textbooks tell the story in the following way. There is a first measurement that collapses the entire wave function and hence changes the state of all systems entangled with the measured system. That's more or less what you find, well, Cohen-Tanucci's book and so on and so on. So that's actually also the way we usually teach our students. You know, you do something here, there's a collapse, or the collapse affects everything, and so it's also changes there. So maybe it's not so crazy to try to be serious about these kind of explanations. Okay, so let's be serious and define V causality. So we have a speed, finite. Could be, again, larger than the speed of light, but nevertheless finite. Whenever an event happens, the rest of the universe gets informed at that speed. So it's just not gravitational waves, it's unknown waves, unknown influences. And whenever the hidden influence arrives on time, of course, the future events are correlated as predicted by quantum mechanics. We also would have a kind of correspondence principle to quantum mechanics, which is quite successful, certainly. But however, whenever the hidden influence does not arrive on time, only Bell local correlations can happen. You know, everything has to then be explained by local variables. Okay, so this is different from Bohm in the sense that by imposing this finite speed, we can get different predictions. So let's look at which different predictions. So this is, again, just in blue, the light cone, which is very well known. Now, in this privileged reference frame, so privileged space, privileged time, hypothetically, we would have another cone, which is now defined with this velocity v. And clearly, so this one gets the information of that event, about this event on time, but that one not. So these ones are V-connected, these ones are not V-connected. So here is now a scenario in this hypothetical privileged reference frame with four parties, A, B, C, D. And we have here indicated this V causality, so this hypothetical speed V. A is in the past of everything. Then comes D. But B and C, they are outside the cone, their cone. Of course, we don't know how this cone is. We just say this cone is not completely flat. So if it's not completely flat, there must be a region here. However, since we don't know how precisely we need to measure B and C here. But we have a trick here, and this is the interesting trick that comes now. So we are looking at this kind of situation. Of course, ADB and ADC, these ones are just the standard quantum mechanical predictions because they are well time ordered here. They get the influence on time. Just BC, that must be non-local here. Non-Bell local, that's what I'm writing. So BC must be local or Bell local. And then there is a theorem, and a surprising theorem in my opinion, So we do similar things in Bell inequality tests. Of now here we have 4 parties, so it's the probability of A, B, C, D, given the experiments X, Y, Z, W. Inputs and outputs are binary. Everything is binary. And if this expression is formally non-signaling, so if I look just at a subset of the 4 parties, 3, 2, or 1, this marginal probability does not depend on the input of the others. This is the meaning here of non-signaling. And BC is local, even when conditioned on whatever happens to A and D. Then there's an inequality. So of course it's not CHSH. Is this, you may say, horrible inequality? Anyway, there's an inequality. It's a linear combination of correlations and so on. But if you look carefully into that, you will see that BC never happens herein. You never have to measure B and C together. And that is very good because we don't know how open these V cones are, but we know that there is some openness. Now, it cannot be completely flat. So we don't need to do excellent measurements with super good timing because we never measure B and C together. You know, sometimes we measure A, B, and D, but not C, or A, C, and D, but not B. So everything here, you can check, can be measured without the need of this perfect timing between B and C, perfect timing being impossible anyway. Okay, very nice. So we have that. And moreover, we have a prediction. What is this, the value of this J? So J smaller or equal to 7 is the inequality. Well, here we have never more than 3 parties. And for 3 parties, we know that the prediction will be the same as quantum mechanics. So we know the prediction. Yeah, it's the same as quantum mechanics. And there is no BC timing issue. Okay, and then, of course, this is only interesting because there are quantum states and quantum measurements that predict a violation. So we can violate, at least, okay, the experiment has not been done, but you know, probably quantum mechanics is still correct also in this case, and you can violate. So what would be now the conclusion or the consequence of a violation of this inequality? Now, there are 2 assumptions here. Either it's non-signaling. No, one assumption is non-signaling, so either it is violating this non-signaling assumption, so it would be signaling, or it is violating the second assumption, so it would be actually non-local. So you know, non-local or signaling, this is the question. Now, in the spirit of the causality, BC have to be local, because that's the entire name of the game here. Now, BC are outside each other's V cones. So there remains, in case of a violation of this inequality, there remains only one possibility, namely that this distribution is actually signaling. It has to be signaling. But now it is signaling not at a subquantum level, hidden, that we never will see, or that is, I don't know, hidden somehow. This is signaling by just looking at the outcomes, so measurement outcomes, so macroscopic signals, and macroscopic measurement settings. So this is now signaling at a macroscopic level. This is no longer hidden. It's completely against relativity. It's not just, you know, not in the spirit of relativity. It is contradicting relativity. Okay, here, maybe I don't go into the details, how you would exactly see this signaling at the macroscopic level, but it really means that, you know, Alice, by deciding which measurement she performs, how she orients her polarizer, for instance, can tell to Dave here, being outside the light cone, can tell Dave some information. So Dave can read the information before any signal at the speed of light originating from Alice would have reached him. Of course, it could be also that the signaling goes in the opposite direction from D to A, but there is something necessary either in one direction or in the other direction. So we really have now this supraluminal communication at the level of classical inputs and outputs. So the conclusion here, so these we already know, that is, let's say, Alain. Here what we see is that we have a contradiction with no faster-than-light communication at the classical level. And we may say, okay, this is impossible because we believe somehow in relativity, at least relativity at the macroscopic level. So we have falsified everything. And the conclusion from that would be that indeed nature is not local. Not only are there not local hidden variables that explain all that, there are also no finite speed influences, including superluminal influences that can explain quantum correlations. So indeed, so mid-conclusion, actually I'm close to the end of this presentation. So you know, Eva, we had this non-locality, so this violation of the principle of continuity. Things are not propagating contiguously, or we violate relativity. And clearly, both alternatives are hard to swallow. Some people hate when anyone is using the terminology non-locality. I guess here for Alain's celebration, we can use that terminology. But depending on the environment, you have to be careful with that. But there is no alternative. So Eva, there is no spooky action at a distance. There is not a first event influencing the second one. And you may just say quantum correlations just happen without any time ordering somehow from outside space-time. What exactly it means that they happen from outside space-time, I'm not exactly sure. But I like this terminology. Probably what it means that it happens from outside space-time is that there is no story in space-time that tells us how it happens. It's also quite annoying that we are facing a situation where we can no longer tell a story about how things go. How are you going to teach our students, not only with equations? Equations we have, we master, that's okay. But we need to be able to tell a story. The only way that remains to tell a story now is to use some non-local concepts, saying, it's not written here. Okay. Maybe it's on the next one. You could just say that there is a random event that happens and manifests itself at several locations. That's a non-local explanation, but at least I can say these words. Whether these words really make full sense is not totally clear, but we need anyway to say something. Still need to teach. Let me just almost finish here with some open questions. Again, crazy questions, which today I'm allowed to raise in front of this audience. How does an event A know that it is non-locally correlated to an event B? Are we telling that out there are angels that manipulate huge Hilbert spaces and keep track of who is entangled with whom? What are we saying, really? How do you teach quantum mechanics? Who keeps track of who is entangled with whom? In the lab, we do it ourselves, okay. But in nature out there, is certainly also entanglement. Who does that? And then there's a more positive question. What can one do with these bizarre non-local quantum correlations? Quantum technologies. Now, we have innovation. Where is it written? Somewhere, innovation there. Yeah, so we have now innovation. So let me just finish by showing you one innovation which I find fun, and which is actually really the consequence of Alain's experiment of 40 years ago. You know, from Alain's experiment, we know that if we have this photon, that's the last beam splitter of Alain's experiment. It's a polarization beam splitter in his experiment. You can also do it with interferometers and have just a normal beam splitter. And so you have these photons arriving, you have the two detectors, and then you can name one detector 0, the other one 1, and then you get a string of bits, and these string of bits are random. And then you take Alain's experiment, so instead of making it larger now, I make it smaller. And I put it in this matchbox, about 4 centimeters large, and I have a commercial quantum random number generator. Very nice. But then you go to engineers, real engineers, and these guys are completely amazing. They take that and they put it on a millimeter size chip. So herein you have a light source, you have the detectors, everything. And it has very low power consumption. So now that you have that, you can put it into a smartphone, Samsung. And in Korea, they commercialize a phone that they now name a quantum phone. Okay, that's marketing. But the chip at least is quantum. It's quantum according to the second quantum revolution, because all chips are, of course, quantum according to the first quantum revolution. Okay, but anyway, so this is nice, and this is the first mass production of quantum technology, or maybe the first mass production of Alain's contribution to quantum physics. Thank you very much.
Thank you very much, Nicolas, for this talk. And of course, beyond the quantum number generator, we still have a lot of questions for the future or the past. I mean, if...
Yeah, please ask your question not in a space-like separated way.
Yeah. Okay, so are there questions? We first start with the second amphitheater. Any questions?
They should be at least able to hear me.
Okay.
If not, I guess they would have left.
Okay. But I'm not sure your question goes through. There was one question by Philippe.
Yes, so Nicolas, you know, I completely disagree with you.
Yeah, and this is a symmetric relation.
Yes, it's a symmetrical position. So the QRNG is okay, this is not the point. I think I don't want to, okay, it would be another talk to go into all details, but I think what you are doing is what people call a forced choice fallacy. You put us in a dilemma between Charybdis and Scylla, and there are many other ways to go. And if you forget about these other ways, for instance, predictive incompleteness, that it's not from me, it's from Jarrett, Simony, and others. There are other ways to explain what happens without being stuck in this kind of forced choice fallacies that you presented. Okay,
this is not a question, it's a statement.
It's a statement. you may answer if you want, but since we disagree, we will not agree.
Yeah, but we're discussing, debating that for years, so I think it's okay.
Okay.
Jean, une question?
Jean?
I have a question, and thank you very much. I have a question on the very first slide of your talk, very naive question. You said that with a non-infinite velocity, you have no grandfather paradox.
If the speed is defined in a privileged reference frame, yes.
So
it's just, okay. Let's say you have Newtonian physics, you can have arbitrary fast communication, and everything happens in this privileged reference frame. You can change the time ordering with this boost, going to another reference frame, but you're not changing the causality relations. The causality relations are defined in this privileged reference frame.
Okay, so this is essential in your talk, that the frame was... You mentioned the cosmic background, but I didn't realize it was so essential for...
Well, it could be the cosmic, the frame in which the cosmic microwave radiation is isotropic. It could be any other one.
But you need one.
But I need one, yes.
Okay.
I don't know how to test these ideas without the assumption of a privileged reference frame.
Thank you.
I'm just commenting because I thought about that. Why not favor the reference of frame?
It's not the spirit of relativity, not at all. But, relativity might be incomplete.
Any other question? Bill?
Yeah, you always have a good question. Wait for the microphone.
So I guess my question is following up. I really had the same question that Jean had about the grandfather. So I was wondering, maybe if you just show one of your many pictures that shows light cones and whatever else the cone is, the the extra cone. Maybe you can, well, so I don't see what choosing a privileged reference frame has to do with it. What happens if I don't choose a privileged reference frame? Then do I have the grandfather paradox? How does it? Maybe you could show how it works, you know, from that diagram.
Yeah. So if you assume that you have faster finite communication, but that this speed is always the same in all reference frames, then I can go from Alice to Bob in one reference frame at this speed. Then I change the reference frame, but the speed would, in this new reference frame, you still have this faster finite communication, and I can go back from Bob to Alice, because then in a new reference frame, of course, Alice is in the future of Bob, and then I can again go from Bob to Alice. So I have the possibility of influencing, well, my past, things like that. So you need to say that the speed is only superluminal and a specific velocity in a privileged reference frame.
Okay, but now if you choose a different reference frame that's only a little different,
Well, the speed would be a little different, of course.
A little different, but still superluminal, right?
Yeah, but that's okay. In this way, I cannot go back to kill my grandfather. For that, I need to maintain the same superluminal speed.
Okay. Well, I don't get it yet, but maybe a little more thought.
Well, this is not something for me. Huh? This is known to, I don't know exactly to whom, but there are communities who know that. It is known to everyone who knows it well, exactly, correct.
Okay, any other questions?
Yes. Thank you very much for the talk. Just have the question about the last slide you showed. Why do you want to have a quantum number generator in a cell phone?
Okay, there are two reasons. One is marketing. It's very important for everyone who, well, the next session is on, on applications. So everyone there will understand that marketing is very important. No, but indeed, I agree. If you just have a quantum random number generator in your phone, it's not useful. But then you need applications. And the applications that we have developed in Korea is for banking, for gaming, for I think also consulting your health medical file. And they have even more. I don't remember exactly, but they have about half a dozen of applications that use it. But at least for cryptography, so classical cryptography, is obviously useful. If you choose your two prime numbers in a not random way, but in a way that everyone would know, then there is no confidentiality at all. So you need to choose something. In RSA, it would be a big prime number, so you have to choose them randomly. And usually it is done in a pseudo-random way. So here the marketing says this is better. And in Korea, this kind of marketing functions. Unfortunately, I'm not sure it's the same here. We are trying, of course, to convince Swisscom to also now commercialize these quantum phones, and so far we have not been successful. But we are continuing.
Thank you. There was another question? No? Okay. No other question? Okay, so let's thank Nicolas again.
Thank you.
So we reconvene here at 4 o'clock for the last session.
Alain, I wanted to tell you how happy I am to be here today, and I would not be here if you did not call me. In December 1995, I think you remember, I really wanted to go back to France from the US and work on Bose-Einstein condensate, and you called me and say, let's do it. And and yeah, the first thing you told me is, why did not you call me before? So, okay, yeah, I should have, but I do not regret that, and that's been almost 15 years of great work in your group and great collaboration. And I have one anecdote that I wanted to share because it's really related to this session. So we worked on this like electromagnet for Bose-Einstein condensate. That was a big thing. So actually, that's my first patent signed with you, and I think it's not your first one. I saw that you had a patent before this one on optical pumping for magnetic detection, and it's actually this optical pumping cells for magnetic for magnetometry, and nowadays it's not vacuum cells, but it's NV centers. They are. It's a quantum technology of today. It's used for magnetic imaging. It's used for navigation. Nice results recently. So that shows that you were already pioneering also the thought of like putting this quantum technology into the realm of business development. As a matter of fact, and Bruno will certainly speak about that, you organized a meeting after we got the BC with Hervé Arditi, who must be in the assembly, myself and Bruno, and you tried to convince Bruno that we should start a company on quantum technology. He did that 10 years later, but you actually, I think, put the little... yeah. Okay, so that was just, and again, congratulations. I think it's a well-deserved prize that you received, and I'm very happy to be here today. So the first presentation of this session will be by Antoine Broès, who is one of the founder of a very well-known company nowadays, Pascal, quantum based on Rydberg atoms. In 5 minutes.
Thank you very much. So good afternoon, everyone. The first thing I really would like to say is that I'm extremely honored and and happy to be here among this list of very, very distinguished speakers, many of them which I know that I've known for many, many, many years. And the first thing I should also say is that it's a very emotional moment for me to be here, because essentially, as far as I remember, Alain has always been part of my scientific life. So we met 30 years ago. I was still a first-year student at the NS Cachan at the time. And you gave a public lecture, so I'm not going to give all the details. It's a private between you and me. In a place close to the Invalides in Paris. We both were trapped in this, in a sense. And so that was the first time that I heard about the Bell inequality, something I had never heard about before. It was just mentioned by Roland Omnes, who was teaching quantum mechanics at the university at the time. And then 2 years later, I was preparing the aggregation, so which is very French stuff. And we had to prepare lectures on the photon. And you came and advised us how to understand the photons. And then a whole realm came to life to me. Quantum optics, manipulation of individual atoms. I mean, all these rebirth of quantum and atomic physics, which I found a super dull topic when I was a student. So I was totally amazed that no one had ever talked to us about that. And so that completely redirected my studies, and the reason I'm here today is because of this very particular day during this preparation of the aggregation. So then you proposed me to do my military service and my PhD, and since then you've been a constant support, which I'm extremely grateful about. So I'm the first speaker in this session about quantum technology, and as a matter of fact, as you will see, it will allow me to be in a superposition of being a fundamental physicist and looking a bit towards the application, although I'm not the one who will look at the applications. So it's going to be about the manipulation of individual atoms from there to the quantum simulators of Pascal. And so let's start with a kind of picture which looks pretty dull. It's dots that you can print on a piece of paper. They're kind of arranged in a square. The dots do not even have all the same size. So it looks totally uninteresting until you realize that actually each of the dots is an atom. So these atoms are all trapped in an optical tweezer. So it's a laser, as the one I have here, that you focus over a size of 1 micrometer, and the atoms are going to be trapped, are trapped here. The reason why we see them is just because we see them the same way I see you. So there is light bouncing on you and scattered, and that arrives to my eyes. So it's exactly what we do. We shine light on each of these atoms, and this light is scattered and collected by a camera. So this is exactly what we do. Why do we have many of them? Because we use diffraction in the exact same way that when you look through the shades in your living room, for example, and you look at a lamp in the street, you find these kind of small spots here, which comes from the diffraction by the shade. And essentially, each of the spots corresponds to a trap. So we do that here in the lab by placing in the beam that creates these optical tweezers, these very tightly dipole trap or optical trap. We place what is called a spatial light modulator. And so essentially, by just inputting the correct phase pattern on this guy here, on the phase modulator, we can get the desired pattern we want in the focal plane of the lens. And so we can do that and arrange atoms in circles. We can arrange them in triangular arrays. We can arrange them in totally random things. It's random until you realize this is a pixelized version of the Mona Lisa. You can even portrait blinking Nobel laureates. So these are not made by artificial intelligence, but by intelligent and talented PhD students in the lab and postdocs over the last few days. So this is really atoms that you see here. And we can also arrange them in 3D. So this is this iconic Eiffel Tower, and something a bit more interesting from the physics point of view, which is this Fullerene-like structure. All right, so each of these atoms now can be considered as a two-level system. So essentially, what are those two levels? Well, of course, there is a nucleus, there are electrons. So you can think of those two levels as different trajectories of the electrons around the nucleus. So there is a low orbit, there is a high orbit. You can also think of it as the equivalent of a spin. So essentially, having a spin up or a spin down, the same way an electron carries a spin. It's just that there is no spin really in this thing. Very same way that each of these spins carry a small magnet. So actually, all of these atoms correspond to small magnets that can be up or down. And so if you choose very correctly those excited states here, so this particular orbital trajectory, you can make it extremely large. So with a laser, you excite the atoms to an excited state, for which the orbit of the electron is on the size about 100 nanometers. And I remind you, the COVID-19, which spoiled our life for 3 years, is actually about of this size. So it would fit inside the orbit. But more interestingly, each of these atoms, because they have a large orbit, actually there is a large separation between the electron and the nucleus, therefore there is a dipole. And this dipole can be gigantic if you choose well the state, that are called Rydberg states, those highly excited states. And they can enhance the interactions between nearby atoms by 100 billions. So exactly now what I have is that I have an ensemble of atoms, each of them being like a small magnet, and they can interact at a distance which is several micrometers, because the typical distance between those atoms are several micrometers. So why is it interesting? It's interesting because it realizes what are called spin models. So essentially, you place on any pattern, you pin spins, and you have some kind of interactions between those spins. And the kind of popular interactions people have written is so-called Heisenberg Hamiltonian, but there are many of them. And as Thierry Giammarchi who said, why are those spin models interesting? Because they are kind of the Drosophila for the physicist of many-body physics of many elementary model of many-body physics. So essentially, the point with this is that they are interesting because they are super hard to solve in many different situations. In the most general case, they are super hard to solve, especially if you have more than about 50 particles. And so it's a problem because actually there are many situations where spin models play a role. So you can explain the magnetic properties of some alloys, of magnets. You can even try to use them to understand transport through, for example, organic polymers. You can also, in some part of the phase diagram, try to understand the behavior of superconductivity. This is actually assumed to be so. And so it's so hard, actually, to attack directly the problem that this approach of building a machine which directly implements this spin model is very fruitful. So essentially, what we're doing in the lab, by placing the atoms in this array and making them interacting as well, is we create artificial systems that we can interrogate, probe, and manipulate. So this approach is called now quantum simulations. And it's quantum simulation of strongly correlated matter. So this is when the interactions between the components become the dominant energy scale. This approach was introduced and proposed essentially the way I've just presented it by Richard Feynman in 1982, and since then it has been a constant drive for the field. So the thing is that those machines that realize a quantum spin model, they can do more than just looking at problems that, after all, may only be of interest to certain theorists or a subclass of physicists. Take, for example, the case of what is called an optimization problem, so combinatorial optimization. And I take here an example of a collaboration that Pascal, which I have not talked about yet, and EDF, just on the other side, had together. They had the following concrete problem, which is that you are, let's say, in a city hall, and you have a fleet of electrical vehicles, ambulance, firemen, the policemen, and you only have, and they're all electrical because we know this is the future, but you only have a finite number of plugs. So you want to optimize the time it takes to load this fleet to refill this fleet of electrical vehicles, but of course you cannot have all the firemen plugged at the same time, because if there is a fire, then you cannot act at this moment. So what do? You're going to actually write what is called a cost function, which will link two partners. For example, this car I with the plug J. But you don't want, as I said, that all the firemen, the fire trucks are filled at the same time. So you're going to impose an energy penalty on some of them to make sure they're not going to be connected. And so essentially, when you minimize this cost function, you have the solution to the optimization problem. The problem, of course, is, it's not a problem, but it's, if you look closely at this Hamiltonian, it's exactly a spin Hamiltonian. So you see that finding the ground state of a machine which implements this kind of model, which is to say the model I just presented, the system I just presented you before, directly found the solution of the optimization problem. There is a few but, though, is that if you want to do better than what people know how to do classically those days, you need to handle a few thousand of particles. So we're not there yet, but the good news is that it's not 100 billion. Okay, it's much less than that, and so that looks like something achievable. The second problem is that you have some kind of connectivity between the cars and the plug, so to say, and this may not be easy to implement on the real system, but people are working around that. Second thing is that those machines that implement spin models, they're actually machines that prepare quantum states. And those quantum states, they may be useful for something. And we've heard about metrology this morning, but they can be useful for what is called quantum metrology. So you all know, and Bill reminded us this morning, that the second is defined as an hyperfine, based on the hyperfine transition of the cesium atoms. It turns out that if you look at what is the ultimate precision that you can get with these clocks, is given by the inverse of the square root of the number of atoms that you interrogate. But now it turns out that if you use the states prepared by those machines, there is a way to generate correlations between the atoms in a way that you can beat this 1 over square root of n, which is only valid if the atoms are totally independent. And you can even hope to go towards something which is on the order of n. So it means that if you have 1,000 atoms, you've improved by a factor 30 the accuracy of your clock. And last, of course, this is the holy grail of the whole community. If you manage to control well enough those engineered machines implementing spin models, they become, and they may become, a universal quantum computer. So there is a lot of promises here. So those are the machines that can tackle problems by changing their complexity class. And essentially, you can attack problem of factoring, searching algorithm, to name just a few. But of course, this is a much longer term. So this is based on all these possible applications and all these promises that we embarked Alain, on this adventure trying to go towards an industry-grade simulator. So that's something we started in 2019. We had started to discuss that a bit earlier, especially with Christophe Jurzak, who was back from the US and said, well, what are you doing in Europe? I mean, there's nothing going on with quantum technology. Well, it has already started in the US. And so he talked to Alain, and Alain said, well, why don't you talk to those guys? So Thierry and I. Yes, and all right. And so it didn't took longer than just a restaurant in a meal, a very good restaurant close by, actually, to convince Alain to join the adventure and to start this company with, of course, a lot of support. So the role of Alain from the very beginning, and that was actually on the first version of the website, is this official title is Quantum Guru on the website, and that is his role in the community. So I don't know who came up with this idea, but me neither. All right, and so what is the company doing? They're trying to take the mess we have in the lab, which kind of works, but trying to make it nice, so to put it in a kind of a shiny box. Of course, you hope that it's not only the box which is shiny, but what is inside works well, or at least much better than what we have in the lab. So that's really the goal. So that's the first point. There is a whole engineering aspect to this. Let's transmit what we know to do not so well, which is engineering, to people who are professional for doing that. And the second thing is to explore applications that we as academics are not necessarily even aware of. And so Pascal has already started to do that. So there are just one example I've given you about this fleet of electrical vehicles, but there are also a few other ones that they've explored recently. So quantum machine learning, so some kind of algorithm when you can decide whether a drug can be lethal or not for a mice or whatever. So it's based on machine learning technique, and they've done some kind of elementary demonstration of that with a small-scale machine. Also to look at application in finance. So here we have to be very clear. We have to be modest in what we're trying to do. The point is that we are at a stage where we're trying the engineering, trying to see whether we can do better than in the lab. And second, we are trying to see whether a concrete problem that people have in real life can be mapped onto something that you can apply on the machine. We are not beyond this stage, or no one is, no matter what you may read in the news. All right. I should say that based on this very same technique, there are actually four other companies. So 3 in the US, Quera, Atom Computing, and Inflection, and there is one which started at the Max Planck Institute in Garching in Germany. So now, what I'm going to do is to go back in history and try to tell you how we get there. So all this is part of the second quantum revolution. We've heard about that this morning. So there are essentially 2 ingredients for the quantum revolution to be efficient and effective. You need to have entanglement, and you need to be able to manipulate individual atoms. And so essentially, those are the 2 things that Alain showed us how to do, and he did that with photons. So the first thing that Alain had to do to violate Bell inequalities or to build his experiment was actually to start from a photon source. So we've seen this drawing already many times. So you excite an atom, there's calcium, it can decay between 2 photons, and those 2 photons can be correlated, and which is to say entangled. And this is with that Alain demonstrated the violation of the Bell inequalities, which are the signature of entanglement. But there is a second important thing that you need also to show. It turns out that this source here also emits individual and single photons, and that's exactly what Alain did during the PhD of Philippe Grangier here. He demonstrated that this could be a heralded single photon source. So essentially you have pairs of photons, so one can trigger a detector, and you know for sure that on the other side you've got one and only one atom that you can use for quantum optics experiment. So essentially now we have a new platform, and let's try, we didn't have it at the time, but essentially you want to extend that to atoms, so simply follows Alain's path. Demonstrate single atom manipulation, demonstrate entanglement with this system. And of course it's hard, so you hope for support. Alain had some support at some critical moment, and we got support from Alain, but from many other people when we tried to do that. So it all started at the Institut d'Optique by what is now considered a very landmark experiment in this field. This is the experiment done by Philippe, and there were like 2 bright students, and one, Georges, is the CEO of Pascal, and Nicolas Schlosser was here this morning, also participate to this. So it started with what is called the MIGOO. The MIGOO is microscope of grande ouverture. It was done in the old building at the Institut d'Optique, and this is this objective that could focus the light down to 1 micrometer, or put in the vacuum, and which is like something 30 centimeters long, all built at the Institut d'Optique, machine engineered and polished for the lenses at the Institut d'Optique. And with that, Philippe and Nicolas and Georges could observe the first individual atoms. So I just sweep under the rug all the detail, but you got on a CCD camera, essentially this kind of telegraphic signal that you observe, and essentially the zero background or the low background means no atoms, while a sudden jump signs the fact that an atom has entered in the trap, and you never see 2 jumps, which is that you never have 2 atoms at the same time. So this is exactly a heralded single atom source, in the very same sense that Alain and Philippe did the heralded single photon source. So you don't know when the photon is going to arrive. Here we don't know when the atom is going to enter, but as soon as it is in the trap, it waves at you saying, I can send you photons, I'm here, you can start the experiment. And this is exactly what this source is about. So shortly after, I joined Philippe's group, and essentially, we tried to use this kind of diffraction I was mentioning. So that was my first project in the group, was to try to demonstrate that we could trap in elementary arrays using a spatial light modulator, small arrays of atoms. And here, I'm very happy to mention Lionel Jacobovies. I don't know if he's still around, but essentially he was, you've heard about him this morning, and you saw him in the movie this morning. He was in charge of the lab work, and it turned out that we had no experience about the spatial light modulator, but Lionel had devised lab work for the students which were using those. And that was extremely helpful for us, so I'm very happy to say that a strong part, a key component of what we're doing now came out directly from the lab work for the students at the Institute. Another very important thing we had about at the same time, I was coming back
from my postdoc with Bill. And Bill had set up a collaboration in the context of some funding agencies called the IARPA, changed name many times even during the project. And so that helped us building a second experiment and also having all the necessary thinking about this system. So we built a setup which was supposed to replace this complicated lens in vacuum by just a single asphere lens, the very same you have in any CD players, essentially, and that worked well. So we built that with Yvan Sortet, who was postdoc at the time. And the second thing we did is to show that if you have encoded what is called a quantum bit, so a quantum superposition of the two states E and G I was mentioning before, you could move the tweezer around and still keep the coherence of the qubit. So that was also something at the time which looked a bit esoteric, but which now essentially all groups in this field are using. At the same time, while we were building this apparatus and trying to fiddle around with individual atoms, there was a good idea which came out. But it didn't look like such a good idea at the time. It was one out of the many proposals that people were putting forward in order to entangle atoms in this thing. So this is a protocol between atoms. So this is a protocol that was designed in particular by Michel Lukin and Peter Zoller, although we have a tendency to forget the other names, which are also important on these papers. And it works in the following way. So it reused this idea of Rydberg that I mentioned to you earlier. So you just assume that your atom is a two-level system, ground state Rydberg. And now you can excite it with a laser. And you look at the consequence of having two Rydberg atoms interacting very strongly with each other. So if we just look at the energy spectrum of two atoms, we have three states, actually. Either the two atoms are in the ground state, or one is in the Rydberg, the other is in the ground, or vice versa, or the two atoms are in the Rydberg state. When the two are in the Rydberg state, they will interact, and they will interact very strongly by this enhancement that I mentioned to you of 10 to the power 11. And so it means now that if I tune my laser for the excitation of one atom, I will be out of resonance with the excitation of two atoms. Therefore, there is a blockade of this excitation. But the most important thing is that if you don't know which of the two atoms you have excited, you excite a superposition of the two. So essentially, you produce a state RG plus GR, which is exactly the entangled state that Philippe and Alain were using to violate Bell inequality. So this led to this idea that this is a mechanism that may be useful for gates. And soon after, indeed, people tried to look at this effect of the blockade, but they were looking at it in a random cold atomic law, so random distribution of the position of the atoms. And so there is a lot of bias that can mimic the effect of the blockade. So we're actually interacting at the time, going to lunch very often with Pierre Pillet, who was in Laboratoire Aimé Coton, next door to the Institut d'Optique at the time. And who is a pioneer of this Rydberg physics with ultra-cold atoms. And we kept telling us, but you have the two atoms. You should be able to see the blockade directly in the cleanest, most pristine case. And so we started the collaboration. And really, this is a copy of my lab book, where I did all the calculation. And this is really a back of the envelope calculation. And all started on this. There is nothing more than what is on this page. You got the van der Waals interaction, the strength of the interaction for typical principal quantum number, the possibility to add microwave, the possibility to polarize the dipole. So essentially, everything is summarized here. And all the parameters we had identified at the time, the whole community is still working with it now. It turns out that, of course, to build an experiment, you need money to buy at least the lasers. And so Michel Leduc, at the same time, had developed this network of labs around Paris called the IFRAF. And in this framework, there was the possibility for young researchers to apply for money. And so that's what we did with Daniel Compara, who is a researcher in Pierre Pillet's group. And we applied for this, saying we're going to entangle two atoms by Rydberg excitation. And we're asking for an amount of money, which by now standards is not so much. But for us, it was an absolute fortune. So it's 150 kilo euros to buy the lasers. And we based all our feasibility on the experiment on this calculation, so really a back of the envelope, and this paper from Mark Safman, who took it seriously as early as 2005. And so we did the experiment. So essentially, we have two tweezers separated by 4 micrometers, try to excite them with the laser, and this is the kind of curve that we had seen. So essentially, this is the probability of exciting either the two Rydberg atoms as a function of time, only one when it is alone, or only one when you have the two of them. And so essentially, you see that it's very difficult to excite the two atoms at the same time. This is exactly the blockade. But you also see that if you have two atoms, it oscillates faster than if you only have one atom. So this is a Rabi oscillation for those of you who know. And it turns out that these oscillations exactly signs the fact that you have a superposition of having one atom in the Rydberg, the other one state, and the other one in the ground state, or vice versa. It took us a bit longer to demonstrate that the state is indeed an entangled state, because there was a problem of this phase here which could fluctuate, and that kills the coherence from the entanglement. So it took us about a year, and so we managed, in ways I'm not going to describe, to actually add the first entanglement of ground state neutral atoms a year later, with a fidelity which by standards is extremely low, but that was again at the very beginning. And amazingly enough, for us it was kind of an important result, but we had a hard time to convince the referees that it was actually an important result, as is not unusual. And so at some point, after many resubmissions, we used kind of some authority argument. It turned out, and once again there are some kind of details, that we had some losses on one of the two atoms during the experiment, and we had to correct for that. And the referee was strongly disagreeing about that. So we just use this. Instead, we have used and explained the procedure to take into account pairs of atoms present at the end of the sequence, widely used and accepted by the physics community. And there are two references, and they are essentially those ones, because this were exactly the one and the procedure that Closer and Alain in his first experiment used before he had the famous PBS that Philippe showed us this morning. So that's exactly what we did, and we corrected in the same way. At the same time, Mark Safman, also in the US, did this demonstration of the entanglement between two atoms. And so then there was the possibility, of course, now to start from scratch. We had done the proof of principle demonstration, and you have to go beyond that, the proof of principle demonstration. So we applied for money at the ERC, which, and this is the figure that was in the proposal, and that essentially combines all what we knew what to do at the time. So the spatial light modulator, the moving tweezer, the arrays of photodiodes, and so on. And it turns out that the chair of the panel was Massimo Inguscio, and at the time, and he trusted us. And so we got the money, and we could build the experiment, which now is becoming a standard design, and the experiment is called le SHADOC. Contrôle holographique d'atomes pour la démonstration d'opérations quantiques. And so we build the machine according to SHADOC principle, of course, and that was the postdoc Alain Vernier at the time who built this. Who drew this picture. And so we have the machine now running. So this is the inner core of the machine, and this is a more artistic view of exactly what I showed you before. Combines all the tools we had developed over the years, and this machine has been kind of successful, and has kept busy quite a fair amount of people. So I put them by chronological order, hoping I have not forgotten anyone, starting from Luca and ending with Bastien, who just joined us. And it also kept a lot of theory colleagues and experimentalists very busy over the years. And this is the list of collaborations we have ongoing. And so the thing about this machine is that now it operates with a number of atoms, which is about 200, so up to 200. So essentially, now we explore many-body problems in regimes that are totally impossible to calculate exactly for the theorists, at least in the situation we're exploring. So we are really in a regime which becomes interesting from the point of view of many-body physics. And so this is now a very popular platform, a bit too popular in my views. There are more than 100 or 150 experiments in construction along the same lines. Of course, there are many variants, but still. And now, what is the next step towards that? So the next step is really, we've heard that several times already, is how do we characterize entanglements in large systems, so beyond 2. And this is still a matter of debate. But it turns out that this is an important debate because if you take randomly a state of a many-body system, it's going to be entangled. Most of the states of a many-body system are actually entangled states. So the question arises of how to characterize this entanglement in a practical way, how to measure the entanglement in the system, and also, of course, a very important thing, and Eric pointed that out, I mean, is there a larger size to an entangled system? So if this is the case, the quantum computer is at stake, at risk, but okay. And so how can we attack that? Well, we can attack that by performing experiments and using the Alain Aspes method. So what is the method? Essentially, try simple. Try with some kind of elegance, an experiment which is going to show something. An experiment which is pedagogical, because always think that at some point you may want to convince the other physicist, that you may want to convince or to show that as an example, a textbook example for students, or you may have to talk to a large audience. So simplicity, elegance, and pedagogy, that's the first thing when you build this experiment and you design it. Should also never forget that naive questions are often very fruitful. And naive, in quotation marks, of course, doesn't mean stupidity. It means naivety and freshness in the way of asking the question. And it's especially important because what is obvious is not always true. And this is exactly what this debate between Einstein and Bohr told us. The obvious vision of the world by Einstein is not the correct one. This is the one of Bohr. And finally, be open. Be pragmatic. Most developments have not been anticipated. The quantum technology for sure, the creation of startups at some point for sure. And so with that, I'm at the end, so the only thing I can say is a big bravo. I mean, there is not more to say for your amazing scientific career. On a very personal level, a very big thanks for having trusted me 28 years ago, and there was no real reason to trust me, for having been constant support when I needed it, and ever since then, and for having been a wonderful guide, a wonderful mentor, over all those years, and for your friendship over the last 25 years. So with that, thank you very much.
Thank you, Antoine. We are a little bit short on time, so while Pascal is actually setting up for the next talk, we can have a quick question, Bill.
Okay, I'll shout it and we can. Okay. So you mentioned in passing that there might be a larger size to a quantum system, and this would be terrible for quantum computers. Could you say a little bit more about the idea behind what might limit the size? I mean, I know about these holographic arguments, but I don't know if that's
I'm not
what
even thinking that deeply. I'm thinking, is there a moment where the decoherence kicks in so rapidly that we cannot grow the size? So this is kind of, of course, you try always to minimize the coupling of this quantum system to the outside world, but it's still scaled with n.
Right. So you're not thinking of some fundamental limit.
No, but there may be. In which case, it's even more interesting because then, but I have no idea where they are. I'm not even sure I know how to ask the question. So.
Okay, so thank you for the introduction. I'm going to present work both from Candela, of course, but also from my lab, the Center for Nanoscience and Nanotechnology. And I must say it's a bit intimidating. It's an honor, but it's also intimidating to be here today. And maybe even more because I am not from the AMO community. You can read it on the title of my lab. I'm coming from the solid-state physics community, and I'm coming from there because in École Polytechnique, I didn't only have Alain as a fantastic teacher, but I also had Claude Weisbuch, who's somewhere around in the room. And you have to choose at some point. And I chose solid-state physics, but we will see that in the end, maybe I ended up combining both of my favorite topics. So I work in the world where you have big machines in a clean room. You grow crystals. You can pull stacks, build stacks of different materials and build mirrors with them. We fabricate artificial atoms. These are semiconductor quantum dots. And these artificial atoms, I will explain that, but we all can also carve their environment at the micron and nanoscale. And you can define optical cavities. So you can see here Bragg mirrors, and you have a confinement in the lateral direction as well. So with all these tools, somehow, our dream is to be able to contribute to the efforts of quantum technologies, where, of course, you can, and you have seen it and you will see it, you can develop application with this kind of setups, with with bulky optics. But if we could, at some point, find a way to put everything in a micron-sized device, it would be really cool. So this is really our goal. And the title of my presentation is Single and Entangled Photon for Quantum Technologies. So I have to discuss a little bit why we are interested in these particles for quantum technologies. There are obvious motivations for photons. Quantum networks, where you can think of different architectures, but in most of them, you think of single photon flying from one quantum memory to another. Or if you don't want to use quantum memories, you would like maybe to build very large states of flight with many entangled photons and develop an all-optical quantum network. There is also a lot of motivation in the worldwide community to build quantum computing platform with photons. This is a non-exhaustive list of the startups that are developing this kind of computer. And they have a global architecture which looks like that. You have single photon sources on one hand. You have some kind of integrated photonic circuit to do some kind of processing. I'll come back to that. And detectors on the other hand. And this is a modular platform. So you can, I like this because you can actually combine the best of each technology to build something as efficient as possible. We love photons because they don't suffer from decoherence in a transparent medium. Single qubit gates are very easy to implement. Eventually, it is a natural platform to do distributed quantum computing, etc., etc. But of course, there is the elephant in the room, is how do we implement photon-photon gates? And this is really tricky. And actually, there are many roadmaps, but I will cite two extreme ones. The first one has been proposed more than 20 years ago by Kning, Lapham, and Milburn, which makes only use of this Hong-Mendel effect that we were discussing this morning, where two indistinguishable particles exit together out of the beam splitter. And you can use that to implement gates with detectors, and you can build on paper a universal quantum computer. We all know it doesn't scale. And so this will be used only for small-scale practice exercise. If you want to go towards large scale, there is a scheme that has become very popular in the community, which is a measurement-based quantum computing platform, which was introduced by Professor Hans Priegers in 2003, where instead of starting with single photon, you start with entangled photons. And the larger, the better. And because you start with a large state of entangled photons, you don't need to implement photon-photon gates anymore. You just need to make single photon gates and to relate the quantum information. So this is basically the motivation for this optical quantum computing platform. And this is the outline of my talk. I will, in the very first part, try to describe how we fabricate now very efficient single photon sources in semiconductor devices, then give you a glimpse of what we are doing at Quandela on the quantum computing platform, and then go to 2 photons and more. And if, Alain, you recognize something here, you're right. This is the outline of your MOOC, quantum optic 1, single photons, quantum optics 2, 2 photons and more. And I'm really happy that I am just going back to your first scientific love, maybe, of single photons with this talk. So single photon sources. Single photon sources. Although there is not standards yet for single photons and light and all that, I won't enter the debate of the Candela, but we need still to have some kind of standards to compare sources between different technologies. So on paper, the ideal source we want is an on-demand, which means clocked, source of light with pulses, and in each pulse we have a single photon, no more, no less than 1. And to implement the Hong-Mendel effect, we need them in a pure quantum state, in all degrees of freedom, which means that we need indistinguishable photons. It's another way to say the same thing. In real life, of course, we will never have 1 photon per pulse because there is always the possibility to lose a photon. One of the metrics that we have to look at is the probability to actually have 1 photon in each pulse. And then there are different kinds of sources, and Antoine referred to them a little bit earlier. There were heralded single photon sources, and actually this first source that was demonstrating the anti-bunching in 1986 by Philippe and Alain was an heralded single photon source. It was not an individual atom, it was a cloud of atoms which was weakly excited. So, and to get a single photon, they needed to detect the first photon from the cascade to announce the presence of the second photon. So it's an heralded single photon source. Later, in history of this field of entangled photon pairs, there was another type of source that were developed. So I'm not sure about the history here because I'm not fully from the community, so I'm a bit confused about orders of things. But this is typically the situation where you take a nonlinear crystal, we create this kind of power injection conversion in a nonlinear crystal, and you can get entangled photon pairs, but you can also get heralded single photon sources. So you shine a laser on a crystal, you create photon pairs. If you have a detector on one hand, then you have the project, you remove the vacuum from this state, and you create a state here in which in the limit of eta very small is very close to a single photon state. But it is in the limit where eta is very small. So eta is the probability in the first place to have a 1 photon pair. So there is some kind of intrinsic limitation in this technology which can be overcome through massive multiplexing. So there are different kinds of sources which we call on-demand single photon sources, and just play with a single atom to generate 1 photon at a time. And this is what we do with these semiconductor devices that you can see here, and that are electrically controlled. So we are playing with indium gallium arsenide quantum dots. These kind of quantum dots have been pioneered in France by, notably in France Télécom Lab, notably by Jean-Michel Gérard and Jean-Yves Marzin. And they've been shown to emit single photons since the early 2000s. So they emit single photon, but in all directions. So we need another tool, and we use cavity quantum electrodynamics to direct the light in one direction. So we put the dot at the center of this cavity, 2 mirrors interferential on top and bottom, and it has a pillar shape. And this implements cavity QED in the bad cavity limit, so we just accelerate the spontaneous emission. And with that, you can have a very high probability for the dot to emit the photon in a given direction. So implementing this and actually developing a very critical technology to do that 15 years ago now, we needed to find a way to put the dot exactly at the center of this cavity. And this we invented in 2008. We were able to fabricate very bright, on-demand single photon sources. You press a button and you have a photon with a probability of 80%. So we were very happy with that. The quantum optics community started to knock at our door to say we want those sources, but they wanted higher indistinguishability, better purity. So for that, we had to work harder, and especially to remove all the noise around our emitter. So we had to remove first the charge noise. There is always a possibility of a charge being trapped in and out of a trap and making some fluctuating electric field. So we had to change the shape of our device to be able to apply a voltage and use a diode structure that just sweep away the charge from the dot. Then we had to adopt the tool of atomic physics. It's obvious for you to do Rabi oscillation with a resonant laser, but when you do that on a micron scale device, you have a lot of scattered light, and it's way more difficult than you think. But we could do that when we had a good mode matching between the cavity and the laser. And last but not least, we need to remove the possibility of having mechanical vibration spoil our photon. So this also happened thanks to the Purcell effect. We accelerate the spontaneous emission of our emitter. So we reduce the time it has to interact with the phonon bath. And by combining all that, so we strongly suppress phonon psi bonds. These are orders of magnitude here. In 2016, we did this Anglo-Mendel experiment, and for the very first time, when we look at the close correlation between the two detectors here you see at 0 delay we had no signal, and we had highly indistinguishable photon with 99.5 indistinguishability, which was a beautiful surprise for us. So I'm telling you the story of my team, but of course this is a collective work in the quantum dot community. And if I summarize on this map of single photon source in terms of brightness, log scale, indistinguishability, the ideal source is there. Heralded source, if you don't multiply them, you're stuck in this area, very high indistinguishability at low efficiency. The quantum dot community was in this region in these years, and since 2016 we are on this path, going up for very high indistinguishability. It's very important if you think of building in a quantum computer, this fact that we have a times 30 increased probability of getting a photon when you want it, because if I want to play with n photons, then it scales exponentially. And this is when all the quantum optics community developing optical quantum computing knocked at my door. They wanted our sources, and this is when we created Quandela. So we created Quandela in 2017 with Valérie Angès and Nicolo Somaschi, and as a company developing single photon-based quantum technologies. And Alain was really kind to accept to be on the board at the very early stage of this adventure. This is a picture at the very beginning of the adventure with Benoît Deveau. It's cut here. Okay, so a lot of engineering, like Antoine said. We had these devices, electrically controlled. 5 years of crazy development to fiber pigtail them, so to align a fiber with nanometric accuracy on top of the device at room temperature that pertains at 4K. This is really something. And finally, we are able, I mean, it's now possible to buy this kind of standalone single photon source, where you have the cryostat, the source, the lasers, the controls, etc., in this rack. And we are happy because we started the company for that, and we have actually sold sources to the leading groups in optical quantum computing worldwide. And I want to point here that there is a buyer who is not doing quantum computing. This is a PTB, so maybe this fact that the Quandela is so hated can be solved with another Quandela. I don't know what they're doing with it. It's interesting for us to see that. Then we decided that we were actually in a good position ourselves to try to build small scale and then maybe try to scale up quantum information processor. So you will see here a paper that we just put online last week describing Quandela Cloud, where we have put online a 6-photon universal quantum processor. So it starts with a source. The photons are generated by just one source, and we have a time-to-spatial demultiplexer, fiber delays, and they all arrive at the input of this universal chip that can implement any arbitrary unitary transformation of the photon. And you have detectors, and then you have all kinds of controls. From an academic research point of view, this is really a pleasure to have this kind of figures. This is the average value of the single photon purity and indistinguishability over 13 days. And I'll show you over months, because now it's been online for months, where you have very high value, very stable in time, and these fluctuations are actually coming from the poor air conditioning in the room. These are the 2, 3, 4, 5, 6 photon rate at the end of the chip. And well, the 4 photon rate is, well, 3 orders of magnitude higher than any previous demonstration put in the literature. And 5 and 6 have never been done on chip. So we are very proud of this, because with a 6 photon rate of few hertz, we can do stuff. We can do measurement at a reasonable rate with 6 photons. They, not me, nothing to do with that. They had to develop a full stack of control and software and a language to pilot this computer. So there is a Percival user here at the end who wants to do something with a photon. It can be based on a photonic circuit. It can be based on gate, or you can just implement unitary transformation, enter that to the cloud, and then there is some control process with machine learning enhanced algorithm compensating for the imperfection in the hardware and the QPU here. And I will not show you much, because we have shown 6 applications in the paper that we posted online last week. One of them is variational quantum eigensolver. I chose this illustration. It's only with 2 photons, but because it's a combination between a quantum processor and a classical processor, where you have a feedback loop, you vary parameters, you look at the output and come again, and you can calculate like that the H2 molecule energy level. And they could demonstrate, of course, this is something trivial to calculate with a classical computer, but they could achieve an estimation of the ground state with a very, very small inaccuracy compared to the previous year. There is something also called boson sampling. We send photons in a network, and because they are interfering at each beam splitter, it's equivalently described by permanent in math, and permanent are very complex to calculate. So we did the very first 6-photon fully reconfigurable boson sampling experiment with Acela with a very reasonable rate, and etc. Of course, we need to work more and to go beyond this 6-photon, etc. So I'm finished with this first part with single photon and linear processing to some extent. And I want to go to 2 photons and more, because this is what we need to scale up eventually, this quantum computing platform. Okay, so the first entanglement that was shown, and I hope I'm not saying something wrong here, is based on the radiative cascade. You have calcium atoms, you bring them in this excited state, and these 2 photons are entangled in polarization. Well, it happens that we have exactly a similar structure in our quantum dot system, and we fabricated a bright source of entangled photons the same way. So our cascade is the following one. We start with an empty quantum dot in the ground state. We can excite one exciton, one electronal pair in the quantum dot, or 2. And the energy levels are like this. You have a single excited state here, but the intermediate state here is 2 states because of the spin degree of freedom of the electron and holes, and a single ground state. And so basically, if you put your system in this excited state, you have generation of this Bell state here. Something important is that these 2 photons are emitted at different wavelengths. So if you want to make a very efficient source, you need a cavity that collects the photon at 2 wavelengths. This is more tricky. So the way we did that was to build a photonic molecule. instead of using just a quantum dot in a cavity, we use two cavities. So we have the dot in one, and then we bring progressively the other one, so that we have two parameters, the diameter and the distance between the pillars, to tune the energy level. You can see here it's really like a photonic molecule with bonding and anti-bonding modes. And with that, we could tune the levels of the cavity to the photon wavelength. And with that, we could demonstrate in 2010 it was the brightest, until very recently, 2019, it was the brightest source of entangled photon pairs with a reasonable fidelity. We were collecting 35% of the photon at the time. Now it's been brought to, I think, 90%. And in terms of concurrence, this is not a beautiful entanglement concurrence. I think it was 0.3. Now groups like the group of Rinaldo Trotta in Rome are able to go routinely above 90%. Okay, this is beautiful, but it's limited to 2 photons. And we really want to untangle many, many photons to be able to implement this measurement-based quantum computing scheme. So for that, there is another way to generate entanglement. I'm very happy to say that we finally managed to do it this year, which is based on untangling a spin and a photon. So the scheme is as follows. Now we start with a dot, with an electron in the ground state. And the electron has a spin 1/2, so it can be spin up or spin down. And in the excited state, here you have now 2 electrons, 1 hole. And actually, the optical selection rules tells you that if the spin is up, it couples only to right circularly polarized light. And if the spin is down, it's coupling to left circular polarized light. So you see, a way to get entanglement is to prepare your spin in the superposition of up plus down, to excite both transitions with a linear polarization. And after spontaneous emission, you get spin up right plus spin down left. This is spin-photon entanglement. Spin-photon entanglement has been demonstrated a decade ago with different variations of this. But it was really beautiful. But what we wanted to do is go beyond that and continue. So if we start with this state, then I can do a pi over 2 gate on the spin. Spin up goes to spin up plus spin down. Spin down to spin up minus spin down. If I just factorize up and down, I get this up V plus down H state, and I can re-excite my system. If the spin was up, I have a right photon. If the spin is down, I have a left photon. This is a spin-photon-photon linear cluster state. And on paper, now, you can continue, as long as your spin doesn't decohere. So we were very happy to do this very first kind of experiment for a quantum dot in the cavity to collect efficiently the photon and also have indistinguishable photon this year with our devices. So it's exactly the same device. And actually, our measurement is limited to 3 photons because this is exactly the same device as before we moved the lab 4 years ago and stopped the clean room. So no technological development for 5 years, well, 4 years. So the spin coherence time is limiting us, but still we managed to implement this scheme. What I like really much is that you can do that by just having a very small magnetic field in the plane, the magnet. You excite your system, the spin is not initialized, you detect the first photon, you know it's up. Then you have the in-plane magnetic field that makes the film precess. You have up plus down here, and you synchronize your second excitation. And this creates spin-photon entanglement. And then you can continue, you add a third pulse, and you can create this linear cluster state here. So we did that for the first time. You can see here the coincidences, 3 photon coincidences, showing a spin-photon-photon entanglement fidelity only above 60%. Still, it's kind of the state of the art for this kind of solid-state system. And also, in terms of photon rates, single photon, heralded spin-photon entanglements, it's 1,000 or 100 times larger than anything that was done before. And we need to optimize this further. Obviously, we cannot work with that, but the spin coherence time I had in this measurement was few nanoseconds, which is very bad. Our photons are 200 picoseconds. Just now in the lab, we are now doing spin echo techniques, and we gain a factor of 10 in the coherence time. But we have colleagues in Cambridge, we have shown that the possibility to bring that to few or even 100 microseconds. So if we get there, then we have many things we can do. Okay. So this sources will soon, hopefully, fuel the Quandela computer, and we'll start playing and trying to implement this measurement-based protocol to understand how it works and what we need to do. I want to go back to some kind of fundamental physics here, because I feel so lucky that with this adventure between the lab and Quandela, all the technological progress we make on the Quandela side feed the research side, and I want to tell you about these different ways of getting entanglement just with a single quantum dot that was published last year. It's entanglement by sequential excitation. And I find it beautiful because for me, it opened my it enlarged my understanding of spontaneous emission. So now I take my two-level system, I excite with a pi pulse, and I consider what happens during spontaneous emission. And during spontaneous emission, I can consider the full system, the atom and the emitted field, as a closed system. And what happens is that the atom and the fields are untangled. And so you have this kind of state during the spontaneous emission, where the atom is excited and it has not yet emitted a photon, plus it has emitted a photon and it is now in the ground state. And you have this kind of coefficients here, and you can mentally think of what happens halfway through spontaneous emission. You basically have this untangled state between the atom excited state, it has emitted no photon, or atom in the ground state, and it has emitted a photon. And the beautiful idea, what was brought by Juin, who was a PhD student in the group of Christophe. I cannot find his last name now. It come back later. It's because of Christophe Solomon who is in the room. I'm sorry. Short circuit. It happens. He suggested that when we should re-excite a second time at this moment, the atom, and we are implementing a gate now. If the atom was in excited state and had not emitted a photon, we bring it back to the ground state, and it will never emit a photon. If the photon is in the ground state and has emitted a photon, we bring it again to the excited state, and it will emit a second photon. So basically, at the end of spontaneous emission, you have, from the field perspective, this photon number, entanglement, distributed in two time bins, 0, 0, plus 1, 1. And actually, we could show this experimentally with our system. I just want to show you, I know you helped, but I'm almost finished. By just exciting twice our system. If I excite once only, this is a time trace of the signal. It has a rise and a decay, and it's just a single excitation. If I excite with two pulses, which are very close in time, I bring it up, it starts emitting a photon, and I bring it back, and it cannot emit photons anymore. If I increase the delay between the two pulses, it has more time to emit a photon, etc., until I have a moment, this beautiful moment, where it looks as if it's exactly the same signal, but actually it's not. If I do some photon correlation measurement to look at the photon statistics, it's basically a superposition of 0 and 2 photons. And actually, to show entanglement, we could do some kind of interferometry or some kind of self-homodynamic measurement. To access the photon number coherence, we could also visualize the time bin, and we could demonstrate that we are generating a state close to this Bell state here, 0, 0, plus 1, 1. So with this, I think I'm done. I want to thank, of course, the teams, both on the C2N side with my long-term collaborators here, and students, and the teams at Quandela, all the collaboration that I have benefited from, and funding, of course. And I want to finish with a special thanks to Alain. So I've never worked with you in the lab, but well, you've been my teacher also at École Polytechnique. You've been there for me in different situations. Not the least of it is Quandela Scientific Board. This was the latest board with a new, very high-level scientific personalities. But I want to also stress that Alain, we are celebrating the fantastic scientist today, is also taking part in the science politics, right? To make sure that the community and the fundamental science goes on, etc. And we are all witness of that. Of course, he played a role in CIRTEC. He played a role in the National Quantum Initiative. And at the level of Saclay, of course, with the creation of the Quantum Center. And also, and I think Jean-François agrees with me, we are very happy that he also supported us in the creation of Artec. So thank you very much, and thank you for your attention.
Thank you, Pascal. So again,
good afternoon, everyone. My name is Bruno Deruel, and I'm one of the founders and the former CEO of a startup company named NewQuant, which is today the quantum systems division of the Exail group. So things have changed over the last years. First of all, Alain, I'd like to say it's a big emotion to be here today to celebrate your Nobel Prize. I want to thank you for giving me the honor to talk today. It means a lot to me. I also want to say it's a funny sensation to be in front of you, Jean, Nathalie, Chris, Philippe, and it reminds me of the day when I defended my PhD thesis in 1999. So you tell me if I have improved over the last 25 years. Okay, so I'm here to talk about the creation of NewQuant, a startup company that was founded in 2009 by Philippe Bouillet, Arnaud Landragin, who's in the back of the room, and myself, with the objective to launch on the marketplace a quantum gravimeter dedicated to geophysics applications. So I thought this title was a pretty good teaser for my presentation. I guess this raises many questions, the first one being probably how can you bring a cold atom experiment on the top of a volcano? And the second one, why the hell do you want to do that? And I'm going to try to answer these questions. So the outline of my talk is shown here. So I will start by explaining the operating principle of a quantum gravimeter. I will then tell you the story of NewQuant and the path we have followed in order to develop a quantum gravimeter that can be deployed on the top of a volcano. I will explain a couple of applications of these quantum gravity sensors. And eventually, since the reason why we are here today is Alain, I will say a few words about the role Alain has played in this project. So let's get started with the gravity measurement with cold atoms. Well, you have to know that it is at the same time highly simple and highly complicated for non-physicists, okay? It's highly simple because basically it's a Newton experiment. I take an object, I let it fall in a vacuum chamber, and I measure the vertical accelerations experienced by this object during the free fall. And it is complicated because the object we are using is a cloud of laser-cooled atoms at temperature close to the absolute zero, and because we are using the laws of quantum physics to measure this acceleration. So the measurement sequence is shown here. It's very simple. We start by trapping and cooling the atoms using a magneto-optical trap and optical molasses. Once we have enough atoms into the atom cloud, we turn the laser beam off. Like any other microscopic objects in vacuum chambers, the atom fall, and during this free fall, we interrogate the atom cloud in order to measure the vertical acceleration they experience during the free fall. And of course, it's not a time of flight measurement, okay? So the key tool to perform this gravity measurement is the stimulated Raman transition. So I consider here a two-level atom in the ground state, and I'm going to shine on this atom two counter-propagative laser beams. First one with wave vector K1, second one with wave vector K2, and I call Kf the difference between the two wave vectors. If the laser frequencies are properly chosen, the atom is going to experience a stimulated Raman transition with the absorption of a first photon towards a virtual intermediate state and the stimulated emission of a second photon so that the atom is transferred from the ground to the excited state. When the atoms are in free fall, of course, they are accelerated towards the ground. This means that since I have counter-propagative laser beams, this Raman transition is going to experience a Doppler shift that I can very easily calculate. This means that if I want to induce this Raman transition during the free fall, I need to chirp my laser frequencies. So this is what I get when I try to measure the probability of transition between the ground and the excited state when I scan the chirp rate. I see a resonant feature that corresponds to my Raman transition, and you see that I can determine the peak position of this transition, can determine the chirp rate. I know that this chirp rate is proportional to g, and I can measure gravity. As you can see, this is not a very strongly resonant feature, and with typical pulse durations, you see that the spectral width of this resonant peak is a few megahertz per second compared to a peak position 25 megahertz per second, so you easily understand that you are not going to end up with a very high performance measurement. And you need to do better than this, and this is where quantum physics is going to help. So let's get back to the stimulated Raman transition. So I still have my two-level atoms in the ground state with an initial momentum p. What's interesting is that during this Raman transition, I have a conservation of the momentum. This means that the atom is going to absorb the momentum corresponding to the first photon and release the momentum corresponding to the stimulated emission of the second photon. So this means that after the Raman transition, the atom is in the excited state, and its final momentum is p plus h bar kf. So of course, if the atom doesn't experience this Raman transition, its internal and external states are not modified. This Raman transition is a coherent process, which means that after the Raman pulses, I have a coherent superposition between these two atomic states. And if I calculate the details of the atom-laser interaction, I see that the atom is going to experience Rabi oscillations, and depending on the duration of the laser pulses, I can adjust the balance between the two atomic states. If I have a pi/2 pulse, I have an atomic wave splitter, and if I have a pi pulse, I have an atomic mirror. The last information you have to know about this stimulated Raman transition is that the laser phase is going to be encoded on the atomic wave functions. And this is interesting because this is going to induce a spatial dependence of the phase, a spatial dependence on the atomic phase. So now that I have an atomic wave splitter and an atomic wave mirror, I have all the tools in order to build an atomic Mach-Zehnder interferometer, and this is what I have represented here. So you see again, I have my atoms in the ground states, and during the free fall, I am going to shine on this atom cloud 3 laser pulses separated by a time interval t. The first laser pulse is going to split the atomic wave packets. The second laser pulse is going to reflect them. And with the third laser pulse, I'm going to recombine coherently my atomic wave packets. And you see that with this concept, I have the possibility to build an atomic interferometer in which the atoms are delocalized. I really exploit the wave nature of the atoms, and that recombine together. And what's interesting to know is that since I have a spatial dependence on the atomic trajectories, this means that the atomic wave packets along the two arms of the interferometer are going to experience spatially different phase shifts. And you see that at the phase shift between the two arms of the interferometer at the interferometer output are proportional to G. Of course, in the spatial domain, okay, I have plotted here the vertical position versus time, but in the spatial domain, everything happens along a vertical trajectory, and I only have vertical separations. So that's the method. So from a concrete point of view, during the free fall, I'm going to apply 3 laser pulses to the atoms. I also need to compensate for the Doppler effect and apply a frequency chirp on my lasers, and this time, when I plot the probability of transition between the ground and the excited state, I see some interference fringes. And you see that these interference fringes provide me now a very narrow spectral feature. I can now very easily determine the position of the center fringe, and I now have the possibility to measure G with a very high resolution. So this is how quantum physics helps to measure gravity. So now, this was the theory. We're done with the physics class. Let me now tell you the story of muquants. So, of course, we're dealing with quantum physics, and everything we have done with muquants lies on a very solid scientific background. Everything started with a theoretical proposal by Christian Bordet in 1989, to manipulate wave packets with stimulated Raman transition. So that's a physical later paper. It was published in 1989. And it took 2 years to Mark Kazevich and Steve Chu at Stanford University to perform a first experimental demonstration of this concept. It was in 1991. So of course, after that, a lot of research has happened. But I really want to highlight the work conducted at CERN by Sébastien Merlet and Frank Pereira with the development of this transportable cold atom gravimeter. And clearly nothing would have been possible without the research they have conducted in order to understand the details of the metrological aspects related to these gravity measurements. And really, this work has allowed us to really understand the potential and the competitive advantage offered by quantum gravimeters compared to a classical one. I also want to highlight the work done by Arnaud, Philippe, and Baptiste Batelier with the ICE project, which consisted in developing a quantum accelerometer in microgravity environment for the test of the equivalence principle. And during this project, they have really conducted very interesting technological developments, especially regarding laser technology based on frequency doubling approach. And I think they have that work was really helpful in order to identify the best solutions that could meet the level of performances, compactness, robustness, reliability that are required for an operational utilization. And then Philippe and Arnaud woke up one day in 2008 with a great idea, the pyramidal reflector. So I think they immediately realized the potential of application behind this idea, and they quickly filed a patent that is a property of CNRS. So the principle is shown here. At the top of my vacuum chamber, I am going to place a hollow pyramidal reflector. And you see that thanks to these configurations, the atoms that are inside the pyramid are going to see 6 laser beams corresponding to the reflections on the inner sides of the pyramidal retroreflector. And you see that with these configurations, I can now implement a magneto-optical trap and optical molasses. When the atoms fall, they leave the pyramid. I only have the vertical pair of laser beams that is required for the implementation of the matter wave interferometer and the atomic detection. So after this patent, Philippe and Arnaud made the decision that, so you see that with this architecture, it ends up in a very significant simplification of the optomechanical architecture of the setup, because in a normal cold atom gravimeter, well, typically 10 laser beams are required, okay? 6 for the MOT, 2 for the interferometer, let's say 3 for the atomic detections, whereas with this approach, we can implement the measurement sequence with only 1 laser beam. This means 1 collimator, 1 fiber, 1 vertical alignment, and this opens the door to an industrial product. And this is what has really motivated Philippe and Arnaud to launch a startup company. So at that time, I was a program manager for advanced research project at the French Ministry of Defense. And well, Philippe and Arnaud came to my office to ask for fundings. And the presentation was so good and the project so inspiring that at the end of the meeting, I proposed them to join the project, and I was appointed CEO of the company. So in 2010, I resigned from my position. I was very lucky to be recruited by Alphanov for the incubation of Muquans, and we started thinking about the creation. So of course it was about defining the development strategy, acquiring a better knowledge of the market, preparing the company's articles of association, and of course trying to have a better idea of the product we wanted to build. And we came up with this. So this is an artist view of what we had in mind at the beginning of 2011. So again, that's not the result of a design study, okay? That's an artist view. I'm the artist, okay? Not necessarily proud of that. Alain repeated the importance of images for a project. Well, that's the beginning of something, okay? I don't know how serious it is, but this is what we wanted to build. And in 2011, the company was created. We were able to hire our first collaborators, and the real work started. And it took us 2 years to develop this first generation prototype. So you see we have our vacuum chamber here, which is already very compact. This is where the atoms are trapped and manipulated. Laser, okay, here I am again. We have the laser system here, so you see we were able to remove the optical table, and we have the drive electronics. So of course, we were very far from a solution that can be delivered to a customer, but you can really already appreciate the level of compactness that we were able to achieve. And also, it was the opportunity for us to validate our technological choices, because with this prototype, we were able to come close to the objectives of performances we had. So at the end of 2013, it was a go to launch the manufacturing of the first serial unit, and we were very lucky to have a first customer with a network of French geophysicists, RESIFs, that were ready to take all the risks and that accepted to place an order. And so after 18 months, we were able to deliver the first serial unit, AQG A01. So you see that's a real product, okay? It can be transported. It can be automatically operated. It can provide continuously for several months measurement gravity value with a very high level of performance, 10 to the minus 9G. And for your information, this instrument is still working today. So that was, of course, a great satisfaction. But also, we were aware that it was only a milestone into the development of the company because this instrument faces very severe limitation. It can only be operated in a controlled environment, not outdoor, and you understand that for geophysicists, it's not going to be good enough. So in 2017, we started a full redesign of the instrument, and we came up with the field absolute quantum gravimeter. So you see that compared to the previous one, it looks about the same. We have a simplified connection here, but the architecture, the mechanical, electronical architecture of the instrument is completely different in order to make it compatible with an operation of a large temperature range, make it accommodate environmental perturbations like dust, sand, mud, humidity. And so now we have an instrument that can be operated outdoor, that can provide very high performance gravity measurements, okay? We can measure gravity at the level of 10 to the minus 9G. This means little g with 8 digits. And it can provide these measurements over months continuously. I'm sure that most of the students who are in this room are going to find it funny, but one of the competitive advantages we have compared to other instruments is that our customers find it easy to operate. I know that's a little bit unexpected for a cold atom experiment, but we have done, I think, we have done a huge effort in order to hide the technological complexity to the end user so that from a practical point of view, he only has to plug a couple of cables, one optical fiber, align the sensor head to make it perfectly vertical, and then run the measurement software. I am not claiming that we have reached the ultimate limits of the technology, okay? We have plenty of ideas in order to improve further the performance, make the instrument compact, and we are working on the development of a new version, which is shown here. So, seriously, this slide is really to show you that we haven't abandoned the objective we had in 2010. Of course, we're not there yet. We still haven't built the gravimeter of our dreams, but I'm sure the technology is capable of doing it. And we still have this objective. And I hope that in a future conference, I will have the possibility to bring a gravimeter with me. Okay, now I would like to say a few words about some of the applications of these quantum gravity sensors. And we are going to come back to the physics of Newton because, as you know, gravity is determined by the masses that surround us. So you easily understand that for anyone who's interested in the underground density repartition, a gravity measurement is going to provide useful information. And I think that the monitoring of volcano is a very emblematic object, a very emblematic example of this technology. Because, of course, you easily understand that fluctuations of magma underground are going to generate some variations of G at the surface of the volcano. And you can really easily feel that there is an interest to monitor gravity at the surface of the volcano in order to detect some precursor signals that could allow us to anticipate some volcanic eruptions. So it took us 2 years to do it. 10 years, sorry. I wish it were 2 years. So it took us 10 years, but in July 2020, we were able to deploy our B03 unit close to the top of Mount Etna. Why was it so long? Well, you have to remember that this is a cold atom experiment. We're dealing with ultra-high performance measurements, and also because the environmental conditions are a nightmare. The volcano is shaking all the time, and the gravimeter is exposed to a seismic noise that is orders of magnitude larger than the sensitivity we want to achieve on the gravimeter. The gravimeter is exposed to huge temperature changes. It is exposed to a corrosive and a dusty atmosphere. And eventually, you understand it's not easy to bring some electricity close to the top of the Mount Etna, which means that the power supply is very unstable, and sometimes the instrument can remain off for several months. This means that you need to maintain the vacuum without any power supply to run the ion pump. So that's the kind of operational constraints we had to deal with. In spite of that, well, we were successful in deploying a working instrument, which is now in the hands of a team of geophysicists led by Daniele Carbone at INGV, who are analyzing the gravity data provided by the instrument on a daily basis. So this is the kind of measurement that we can perform with the gravimeter. So these are data that were obtained between June and October 2021. So you see the black and the red curve correspond to the gravity value. So you can see that gravity varies by about 40 microgal, which corresponds to 4 times 10 to the minus 8 G. So it's a very small signal. Okay. So this corresponds to the fact that the magma reservoir is emptying. You see that we have some emissions of lava fountains here. So I guess your big question is, well, based on this, can we anticipate a volcanic eruption, which is really the big question? Well, first of all, you have to know it's the first time that a gravimeter is deployed on the top of a volcano to perform long-term continuous gravity measurements. And they have already done good progress, but the answer to this big question is not yet. This is still ongoing research. That's a very complex geophysical system. The geophysicists still need time in order to refine their models. That's the beginning of something very interesting. We have also the project to deploy an array of sensors that will allow to perform gravity maps, and this is an ongoing work. The second example I want to mention is civil engineering, and we had the objective to use gravimetry in order to detect cavities, voids, tunnel, or sinkholes. I'm sure you have seen some videos where we see a road collapse. Well, that's the kind of thing we could prevent by using a quantum gravimeter. And for this purpose, we have developed a differential quantum gravimeter that allows us to perform a simultaneous measurement of gravity, G, and its vertical gradient, dg over dz. And we can show that this measurement of the vertical gradient is going to allow us to acquire a much better sensitivity to small density variations at small depth. And in order to verify this, we have done a quick experiment in the parking lot of Institut of Optics, and well, we have moved our prototype over a 1 meter cube cavity buried 0.5 meter under the surface. And as you can see, we can very easily detect this cavity. The signal is in very good agreement with our theoretical prediction. And so that was a very good, a very convincing demonstration of feasibility for us, and we are now in the process of developing an industrial version of this differential quantum gravimeter. So the end of my talk is approaching. It's now time to say a few words about the role Alain has played in this project. So Alain, it's not about the money you have invested in the company, but thank you for this anyway. So I will start with a family tree. So we have the baby, Juin. Well, you know its fathers, so Arnaud, Philippe, myself. And you have to know that the three of us are former collaborators of Alain. So Arnaud and myself were PhD students in the atom optics group at the end of the 90s. I was instructed to acknowledge support of DRET for this PhD, for the funding of our PhD. And Philippe has been a collaborator in Alain's group before he became a director of LP2N. So Alain is the grandfather of Juin. This means, Alain, that some of your genes are inside the company. And the first one is probably passion. We all know how passionate you are. And I think beyond everything else, this kind of project is really a matter of passion. It's really the most powerful engine you can find in order to solve all the difficulties that you are facing on a daily basis. The second one is fighting spirit, perseverance. I have to say today that the Muquans project has been terribly difficult. It's difficult because we're dealing with cold atoms, with quantum physics. We have to struggle on a daily basis with highly complex experimental setups, and it's only a matter of one tiny little defect in the system, and it screws everything up. And so in order to develop a gravimeter cold atom experiment that can be deployed on a volcano, you need to work very hard every day for many years. And this is something that I have learned in your lab when we were spending our nights trying to achieve BEC. So we know it's complex physics, and we need to be very brave in the challenge that we have to address, and that's a lesson that was very important for the management of Muquans. The last example I want to mention is a team spirit. I remember that you taught us it was very important to treat everyone respectfully in the group, of course, in the administration, the mechanical and electrical workshop, to value everyone's contribution. And that's also a value that we have tried to cultivate in Muquans. I think we have been very lucky to find collaborators that share this value, and everything I have shown here was really obtained only by joining our efforts. So that's something very important. In today's world, I think we tend maybe to value some individuals, but for this kind of project, it's really the result of a collective effort. So this last slide is to say thank you. The first people I would like to thank are my collaborators. Again, they have been exceptional from the very beginning, and everything Muquans has produced belongs to them. I would like to thank Philippe and Arnaud for their support, for trusting me with the management of the company. Scientific collaborators at CIRT, Institut of Optics, LPL, RESIF, of course, all the institutions that have supported us. And also, thank you, Alain. I perfectly remember the first day we met in 1992. So at that time, I was a young student. I was very impressed when you came to talk to me and offered me to join your group. I wasn't aware of it at that time, but I think this is a meeting that has probably changed my professional life. I think working with you has been an extraordinary experience. I learned a lot. And also having your name on my resume has opened many doors. And thanks to you, I had the opportunity to live extraordinary adventures. So thank you for that.
So maybe Antoine and Pascal, you can also rejoin on the scene. So you had half an hour to prepare your question. So please, what is your question on the other room? Yes. Oh, we don't hear you. Okay. Come on, you had one day to get this working.
Thank you.
Yes.
Yes, I had a question to Mr. Brunel, Desruel, sorry. I was wondering, I mean, what type of demand do you have for measurement of gravity, and apart from the volcano, do you have new projects that are coming up concerning, well, measurement of gravity?
Well, that's a very good question. So, of course, we are dealing with very specific applications, and we don't have a mass market because, well, only a few specialists on Earth need to get a very precise knowledge of gravity. So we have applications in the field of geophysics, but also in the field of navigation. So that is one of the reasons NuQuant was acquired by IXBlue. So clearly we are addressing niche markets, but I think that the market is large enough in order to develop the activity and be in a position to offer an interesting job to several dozens of physicists and engineers. So that's what we have in mind for the future.
Thank you. Okay, you come next. Serge, you have a question? Maybe Serge, and then Bill.
Yes. I have a question for the gravimeter too. How do you compare the performance of this kind of gravimeter with the ultra-precise atomic clocks, which can see changes in the gravitational field with a very high precision?
That's a very good question, and that's still well. It hasn't been done yet. First thing you have to know is that the gravimeter is sensitive to the acceleration, whereas the clock is sensitive to the gravitational potential. So we are not measuring exactly the same thing. So that's one of the objectives we have, where we want to measure the gravity field, have high-performance atomic clock, and compare the signals in order to see how they can correlate and what kind of information we can extract to this combined measurement, but I don't have the response yet. Yeah, of course, we can measure the vertical gradient, but the question is about using optical clocks to measure the gravitational potential. No, it's not good enough. Typically, the change in frequency you can expect. So when you have a 1 meter difference, so the frequency difference in an optical clock corresponding to gravitational potential difference of 1 meter is 10 to the minus 16. Okay, with the clock we are working on, well, the long-term stability we are dealing with is 10 to the minus 15, so it means 10 meter. So clearly, if you want to have a convincing experiment, you need an optical clock. So I would be extremely motivated to do that. It's just a matter of time and money to make it happen.
And would it work on a volcano? If you have 2 or 3 clocks, would it be easier to
one of the difficulties, having a clock is good, but you also need to have a way to compare the frequencies. So you need the clock, and then you need the frequency comparisons with another optical clock, which means you need to have a frequency transfer network. So we have the solutions, but it means you need to deploy a fiber and then compensate for the phase noise, and it's doable, but it's a complex scientific project.
Thank you. So I cannot hold Bill for longer, so please do.
So first, my colleagues at NIST would be very upset with me if I didn't point out to all the speakers today and to all the people in the audience that the unit Hertz can only be used for periodic phenomena, not for rates that are stochastic. Okay, enough said about that. Now, my question is for Pascal about these wonderful quantum dots for photons on demand. So this 99.5%. So I want to make sure that I've understood what that means. So does that mean that on 2 successive demands from the same quantum dot, that they will be the same to that level in a Hung-O Mandel? Now, what I'm wondering is, what if you had 2 quantum dots?
Sure, this is the next challenge. This is the next challenge. Right now, we have that. I mean, the state of the art right now for 2 dots is above 90. I'm going to be wrong. 92%.
Okay.
Still not in the cavity, so we're working on that.
Yeah. So, sorry to keep going, but I love these dots so much. So, what is the probability that when you push the button, you get a photon?
Yeah, so in the fiber, right now it's 30%. At the output of the device, it's 55%. And so we have a lot of engineering in between the two.
Okay.
And so this is why the fiber pigtailing is, is a key point. And, and on paper, we have a roadmap to go to 96%. And then beyond that, we need to work.
Now, what I'm wondering is, going from the 80% where when you first started to this 99, was there one particular feature that was the dominant thing that you had to fix, or was it were all the points that you gave us similar?
For the indistinguishability?
Yeah, for the indistinguishability.
Yeah, it was really it's a combination of the three I mentioned. It's really you need to kill as much as possible the charge noise.
Yeah.
To do real coherent control of your two-level system. Really, this fundamental suppression.
Yeah, so they were all significant contributors to this.
They are all playing a role, and if you don't do all of them high enough, you easily drop to 95%. This is what we have right now in Quandela, because we had played too much with some parameters and dropped a bit because of that.
Yeah.
Thank you, Will. So Isabelle had a question.
Yes, it's again a question for Pascal. Yes, I like the idea of making two photons by stopping the spontaneous emission. But my question is, I would expect that those two photons they will not be indistinguishable.
Of course, no.
Yes, because one is nice exponential with, and
but
the other one
they are in two time beams, so you have to define a mode. So they are in different temporal modes.
Yes, I understand, but this you can take a delay line and you can forget about this. But I expect that just...
I think not in this scheme. I think not in this scheme. It is precisely the case that we are untangling different temporal modes of the spontaneous emission. We are untangling different temporal modes during the spontaneous emission. So we cannot compensate for... I don't think we... Yeah, I don't think we can. But this is, this is where we need a bit more of theory. There is a lot of theory going on in this because you need to really describe the spontaneous emission process and calculate the state of light.
Yes, that's it. I would expect the state of the first photons to be not the same as
the second one. It's true. I agree.
Okay.
But the idea is that still you can create different wave packets like that, and then you can do some kind of interference and teleportation and stuff like that. And you can split your photon more than in 2 bits. They have actually some ideas doing some Fibonacci sequence to create even weirder state of light. Although our emitters are a bit too fast, so we are fighting with the limit of the detectors. Our photon are too short. Actually, I think it's an idea that would be better done in real atom where everything is slower and it's easier to detect the different slices of time.
Okay, so Massimo, you had a question also?
Just a suggestion, following the question of Serge. Instead of going to Etna, you should go to the Fréjus tunnel under the Alps. And there are a couple of optical clocks transportable, which are connected to the absolute clock in Torino. And so you could compare in a clean environment.
Okay, right.
This could be.
Okay, thank you. So even the chairman has an authority above him, and if I... So can I let Philippe speak, or... Yeah, so please. And then, so last question by Philippe, maybe Philippe.
Well, it's a question to both Antoine and Pascal. Okay, you know that I'm sort of involved in the whole kind of European business now, and the question I always get in Brussels is, okay, fantastic things, but when shall you get the quantum advantage? So sorry for asking this question. It was asked to me by Claude Weisbusch also just now.
Yeah,
so please, Antoine.
Okay. My answer to that is that it's irrelevant. The answer to that is that to a certain extent it's partially irrelevant. If you discuss, no, but in the context of the industry, if you discuss, first you have to define what is quantum advantage, and that's a moving target. As long as, as soon as people do some improvement on the algorithm, and for example, I showed you 100 atoms, people couldn't do any simulation of the dynamics of this system a year and a half ago, now they can, up to 200. So this is moving forward. So, you cannot say that this is okay.
The second thing is that quite often people have in mind with the quantum advantage the change of a complexity class. You go from exponential, but that's only relevant for computers. It's not something which is relevant for a NISQ machine in a sense. And the third thing is that if you discuss with people from the industry, they do not care whether you change from exponential to polynomial. They care about the fact that if you have a hard calculation to do, a hard problem to solve, the constant in front of the exponential go from 0.9 to 0.985. That's enough for them. And they're totally agnostic in the sense that it may be that on certain niche problem you have a quantum advantage at some point. It will trigger more classical developments, and then they will overcome the quantum, and it will be, in a sense, quantum is offering a new type of solutions. But it's not, I don't think, at the moment, this is something where we can claim we have a definitive quantum advantage that's going to overcome any classical things we have. I think we have to be very honest with that and stop talking about quantum advantage, which is spoiling the whole business, honestly.
Okay.
But I mean, people in the US already have stopped talking about this. And as usual, yeah. And so in a sense, in the EU, they're still living on what people were discussing 3 years ago, and now we have realized it's not as relevant, so.
Yeah, I mean, I will not answer exactly the same way, but I think it's as if we were asking the people making the first airplane when they will shoot to the moon. It's too early to say, it's too early to ask, and I think on the way there are very interesting applications that will come on the way. From a computer scientist perspective, some discussion that I have heard that if you think of machine learning, for instance, machine learning is really heavy on the resources, and it appears that there could be that using a quantum processor, even a small scale, could narrow down the search parameter volume. And if you could just split the task between something which is really a NISQ platform, but narrow down the search parameter and then finish with a classical computer, already people will be happy. So I think my perspective is really on step-by-step adiabatic progress, and advantage can be a small thing in a very specific case that still makes sense. And of course, then you can shoot the moon. But,
yeah, thank you. So unfortunately, time flies. So thanks again a lot. And so before giving the floor to the star of the day, Alain, I think on Alain's request, Serge will say a few words.
Yes. Dear Alain, it's a pleasure for me to say a few words here. I am sure that you have been very happy with all what we have heard today, not only because it has given us by just reminding of all the fields to which you have contributed to explore a wide spectrum of activities in our field of physics, but because also I think it illustrates what makes this physics the physics that we love. The spirit of it, the fact that it's a small-scale physics, a physics that you can do on a tabletop, even if the tabletop becomes more and more difficult to handle, but it's still a tabletop. It's small groups. It's groups in which the students and the mentors participate at the equal footing, in which we can discuss at the same time the theory and the experiments, which is not the case in high-energy physics. And also it's a field which combines fundamental aspects and applied physics, as we have seen during the development of this day. And I think there is one thing which made all this possible, and I'm sure you will agree, it's the laser. Without the laser, all what we have discussed today would have been impossible. And so we owe that to Einstein. Not only the discussion about the EPR issue, which is, I would say, the dark side of Einstein concerning quantum physics, but the fact that he was the one who pioneered, by stimulated emission, pioneered the laser. I remember when I was a student myself, all my colleagues, students' colleagues who were going into particle physics, high-energy physics, were looking down on me, saying that I was just looking at spectral lines, that this was well-known old physics, that we are just tabulating numbers. And I think that he would have been right, they would have been right if the laser was not invented. And in fact, I started at the time when the lasers were just on the horizon. We could not figure out, we could not imagine all what we could do with them. And what we have witnessed today, the fields to which you have contributed beyond the EPR and the Bayes inequalities have illustrated that very well. I first heard about you in the 1970s from Claude Cohen-Tanuji, who was my mentor. I had finished my PhD and I was starting as an independent researcher at Laboratoire. It was called Laboratoire de Spectroscopie Hertzienne at that time, the Kastler-Brossel lab. And one day he came and he said, you know, I just met a young guy from Orsay who wants to do an experiment about correlation of photons, cascading, entangled photons. And I said to Claude, look, first of all, in your lectures, you told me from the beginning that in the ground state of hydrogen atoms, the spin of the proton and the spin of the electron are entangled. And that's obvious. And we also learn the rotations in quantum physics. And you told us that when you have a spin pointing in one direction, and if you measure it in another direction, it's a spin 1/2 rotation, and we have all the formulas. So what is the point? And Claude told me, yes, but this is true because the particles are very close to each other, and as Nicolas said, you don't know if this will hold at 12 meter or larger distance. I think what Claude liked in this experiment is the fact that it was possible to answer by an experiment a question that his two heroes, Einstein and Bohr, was debating about. And so this was certainly the deep point here. And I want to say that you said very often that this experiment was possible because you had a position which was secured, and Bell had told you that you should get into this kind of physics only if you had secured a position, because I am sure that if you had applied for a grant, even an ERC grant today, the question which would have been asked immediately would have been, what is the use of this? What will be the application? And 40 years ago, you would have been absolutely unable to tell all what we have listened today about. So I wanted to remind you of that, the fact that the research has changed a lot during the last decades, and not for the best. I think it will be difficult today to present a project like the one you had 40 years ago, which would have been accepted without any discussion of the kind that I'm just talking about. And I want to conclude coming back to Claude. Claude was unable to come today because of health problems, but I'm sure that he is with us today, and he thinks very strongly about all what you have done, and you know that. Claude was a physicist, as you know, all who have attended his lectures know that he is a physicist on the shut up and calculate side. He did not go very often into this discussion about the fundamental aspects of quantum physics, but he has an mind which is open enough to feel and to understand deeply that this question, if this question can be addressed by experiments, then one should do it. And there are other open questions which were discussed here today about the fact whether there will be a breakdown of quantum physics at some point, the connection between quantum physics and gravity. The question is, what kind of experiment can we do in order to test nature? And it's not clear, but my feeling is that the experiment will come from our field of physics by increasing the precision of measurements and not by the brute force of bigger and bigger accelerators. So we are in a very interesting competition between low energy physics, which try to push the limit of precision, and high energy physics, which is, I think, in a corner. And you participate a lot to these developments, and I wish you good luck. And I want to congratulate you again, and also to congratulate Annie, who has supported you. And I use the word support in the English sense of it during all these years. Thank you, Alain.
Normalement, j'ai pas besoin de micro. Levez-vous, parce que là, du coup, la présidente pourra prendre sa place. Voilà. Et comme ça, j'ai pas besoin de faire de l'acrobatie. Il ne faut pas te casser une jambe. Ouais, ça ne serait pas le moment. Estelle, il faut en profiter. Et Rémi aussi. Allez-y, allez-y. Well, Serge, I'm very glad of these words that you said. it was not clear whether I should introduce you, but he said, no. But if I had introduced you, the few words would have been first on our common passion for photons, and second, about Claude Cohen-Tanuji, although we did not interact at all in the same way. You were a student of Claude Cohen-Tanuji, was your mentor, and I knew Claude Cohen-Tanuji only after achieving what I got the Nobel Prize for it, but he had a strong influence on me because I studied quantum physics in his book. I did not receive any good course in quantum physics, and I studied quantum physics in his book. So in that sense, I'm also his student. And of course, then there was the cold atom, fantastic event, etc. So, you know, it's embarrassing to have to conclude a day like that when you don't know exactly what will happen. So I will make a hybrid presentation. First, I had prepared a scientific presentation, which is the lecture I gave in Stockholm. But of course, I'm not going to do all of it. I will extract only a few things out of it. And you know what I will extract, Nicola? Okay, I find where is. Okay, so what I will extract is the fourth paragraph about quantum non-locality. Because, you know, Nicola, not only I pronounce these words in front of the Nobel Committee in Stockholm, but if you remember, we were in a quantum symposium in Malmö in August 2022. And I hesitated for a long time. And finally, I had put in my title quantum non-locality. And in spite of that, they gave me the Nobel Prize. So okay, so let's go to it. The first point that I want to do, we have all understood by the excellent talks that we have that in the EPR situation with the photon, there is a strong correlation between the two particles which are far away from each other. How can we have such a strong correlation? And so, of course, when you find this correlation with the calculation, the first reaction is to say, let us look into the calculation. Can we make an image from that calculation? And as is written here on this transparency, if you look at the efficient calculation, okay, the very good one, which gives you a result in 2 lines of calculation, it's very efficient, but no way to get an image. Why? This is one of my preferred sentences, because it happens in a Hilbert space, which is a complicated space, which is totally different from our space. But, as Asher-Perez said, experiments do not happen in Hilbert space. They happen in our space. And so that's the citation of, do I have a pointer here or not? The green one? Ah oui, voilà. Hop, on a déjà changé. Bon. Je ne maîtrise pas la technologie. Okay, yes, I like very much the sentence of Asher-Perez. You know, Asher-Perez was really on the side of shut up and calculate and efficient. But anyways, this is a strong statement. And about non-locality, there is one way of doing the calculation to try to build an image in our space. And that way, I must say that these Cohen-Tanuji approved, okay? I only use the postulates which are in the book of Claude Cohen-Tanuji. So the idea is we are going to do first the measurement here and later the second one. And we know that the measurement of the first can randomly give either result +1 or result -1, starting with this state. And then what do? So I go to the Bible, okay? And in the Bible, they say stacked vector projection onto the eigenspace associated to the result of the measurement. So, which means just after the measurement, we project the initial state onto the space depending on the final state. And so, for instance, if we have found x, the projection gives xx. And now xx is crystal clear. It's one photon like that and one photon like that. And so, of course, no mystery that I will find +1 on that side. If I find y, result -1. Similarly, the projection gives y. So this photon is y. No mystery that it is that I will find -1. And so this is an image in our space. It works. I can develop, okay, blah, 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 blah. But, of course, now we have non-locality. The measurement on U1 seems to influence instantaneously at a distance the state of U2. This is quantum non-locality, which, of course, was unacceptable by Einstein. Okay, now I will jump to the fourth section of my talk in Stockholm. Yes, just in passing. This photo, which has been shown in many newspapers, etc. What is the experiment on the blackboard? The experiment of the third experiment, the one which was done with Juin. And I did not select that photo. It's a photo which has been published everywhere. So, Juin, we can be proud of that. Okay, let us continue. Talk. Okay. Just in passing, Nicolas, you know that when I speak of the third generation experiment, I say how much I was impressed by your experiment using the commercial network of Swiss Telecom, and I have to apologize that usually I make a joke. I say, you know, Nicolas can do this experiment because Swiss people are very quiet, and during the night, they don't go on their computer, they sleep. And during that time, Nicolas does his experiments. I have to apologize for this bad joke, but okay. So let us go to non-locality. Let us go to quantum non-locality. So quantum non-locality is, in fact, you can find it in the paper of Einstein. Because Einstein had considered the possibility that we cannot complete quantum mechanics. And the result of the Bell test is that, indeed, we cannot complete quantum mechanics by invoking a physical reality which is shared between the two photons. And so Einstein had considered the fact that this would be the case, that is to say, no local realistic view. But why was he considering that? Because he was making a reasoning ad absurdum. He would say, if this would happen, it would be terrible. But now, today, we know that it has happened. And so what would have been terrible? These are words of Einstein. We would have either to drop the need of the independence of the physical reality present in different parts of space. And when he says different parts of space, he means volumes, space-like separated in the relativistic sense. Or accept that the measurement of the first system changes instantaneously the real situation of the second system. These are two different versions of quantum non-locality. Just a remark in passing, there is another way of saying what we have here, is to say the properties of a pair of entangled particles are more than the addition of the individual property, and this is called quantum holism. And it is very important for quantum technologies that the idea that when you have entangled particles, you can encode much more information in it because of this property. So, the point that I wanted to do in the fourth section of this talk is that quantum non-locality, I would not say that it exists or it does not exist. But I like quantum non-locality because it gives to me intuitions very efficient that I can check by calculation afterwards. And I have two examples of that. I will give only one. The example is the quantum cryptography scheme by Arthur Eckert. We know that the problem of quantum cryptography, or cryptography in general, if the two friends, Alice and Bob, want to exchange information, And the best, and there is an eavesdropper here who is trying to get information. And there is a theorem by Shannon which says that if Alice has a random series of 1 and 0, and Bob has the same series of 1 of 0, then encoding with that and decoding with that, it's absolutely safe under one condition, that the message should not be longer than the encoding series of 1 and 0. And so the problem that they have now is to distribute to Alice and Bob a new series of 0 of 1. And then the solution of Arthur Eckert is to use a pair of entangled photons. And Alice and Bob are going to do measurements. And because of the non-local vision, but it is this vision which is supported by the violation of Bell's inequality, we have to admit that until the last moment, Alice doesn't know, nobody knows if you will get +1 or -1. And until the last moment, nobody knows if you will get +1 or -1. Because if somebody would know, it means that there would be local hidden variables. And because it is at the last moment, there is nothing to spy here. It's not yet +1 +1 or -1 -1. It's still open, so there is nothing to spy. And in my opinion, this is a key of the method of Arthur Eckert for quantum cryptography. And of course, after that, you can do complicated calculation, demonstrate that it is safe, etc., etc. But just having in your mind this non-local image, the fact that until the last moment is not yet decided, immediately tells you this is probably a very nice method. Okay, so this is what is written here. Okay, just to mention that now, our colleague Jian Weipan in China is using that for quantum cryptography as more than 1,000 kilometers. Okay, well, that's China. Okay, so the conclusion is that non-local images of entanglement provide fruitful intuitions for quantum technology. The other example is quantum teleportation, but I will not show you the only fact that I can emphasize is that by thinking in non-local images, it's immediately obvious that you need good quantum memories, as Nicolas has demonstrated long ago. He did a beautiful quantum teleportation experiment by using a quantum memory, which was a coil of optical fiber. Right, Nicolas? Okay, so this was my conclusion in a Stockholm. But you are not done with me. Then I will have something else to tell you. So the conclusion that we have to thank Einstein, Bohr, and Bell for pointing out the extraordinary character of entanglement. Then there were more thanks. There was a thank to the two brave young students whose involvement and enthusiasm were crucial to complete this experiment. And you know the two students, okay? They are Jean and Philippe. Okay. Of course, Gérard Roger and André Willing. André Willing is around. I don't think that Gérard is around. Gérard Roger was a fantastic optics and micromechanics engineer, and André Willing was a fantastic electronics engineer, and they made the experiment absolutely reliable. Many thanks to the workshops of the Institut d'Optique and also of the CEA Saclay, which helped me a lot. The late Christin Imbert, who gave me a file in which the first paper that I found was a paper by Bell, and I knew that immediately I wanted to work on that subject, and then he supported me in spite of many criticism. Now, I already mentioned the book of Claude Cohen-Tanucci, Frank Lalloé, and Bernard Yu, where I learned quantum mechanics, which allowed me to understand the paper of Bell. Also, the lecture of Claude at Collège de France, it is where I learned quantum optics. And it was already mentioned, the support of Annie, okay? There will be more of that in a moment. Can I close it? Because I have to take my computer now. Can I do it, Clementina? If I close it, or do you want? Because I want to read my computer now. Nobody answers. So let us do it. On va voir. I'm an experimentalist. So now, of course, after this wonderful day, I would like to thank not only the people who helped me for the experiment of 1982, which brought me to Stockholm, but as you have heard today, and this was a very important part of the day, there was a lot of talks about other things, about the fact that I was a professor inspiring many students, and the fact that there were more physics than just testing Bell's inequality. And by the way, I decided on purpose in 1982 that I would not be the man doing only one thing in his life, that is to say testing Bell's inequality. It was on purpose that I immediately accepted the offer of Claude Cohen-Energy to join him for cooling atoms with laser. This is wonderful. Okay, so I have a series of remarks that I've noted on my computer during the day. First, it was said that at the beginning of cold atoms, we received help from the DRET, that is to say, the Military Agency for Fundamental Research. And there was things, we promised things that we do not know. In fact, Jean, we promised from the beginning that they would be able to build gyrometers built on cold atoms. It is not us who did it, but the promise was a good promise. And there have been many more things for which DRET supported us, and we did not exactly do what we announced at the beginning, but at the end it was good physics, and I must say that it is a pleasure that I never made reproach that we did better physics than the one we had announced at the beginning. So it means they are smart. So I would like to have a word for each of the speakers of today. Well, Jean, I have not much to add. It was a wonderful time when you were in the lab at Institut Optique, and of course, you spoke about the time of cold atoms with the team with Christophe, Claude Cohen-Energy, and both of us, and then with our two first PhD students, Robin and Nathalie. And what a wonderful time. I don't have to say more. You really said what... my mic, no, okay. Bill, you say that often there are different models between which you cannot test. You cannot make a test to decide. It does not mean that it is not interesting, because different models can give totally different intuitions. Just take the classical example of mechanics, classical mechanics. If you use Newton's law, it's very likely that you don't get the same intuition as if you use a Hamilton formalism or the Lagrangian formalism. So the fact that you cannot distinguish by a test between the models doesn't mean that it is a bad idea to consider the various models. I'm sure that Nicolas fully agrees. Chris spoke about atom optics. In fact, the truth is the following. My real love, as in life, is my first love. And my first love is optics and photons. And so, of course, it was a wonderful time when I learned how to manipulate atoms. But when there was an opportunity to play with atoms as I knew to play with optics and with photons, then immediately I decided that it is what I wanted to do. And so Chris reported many things about metastable helium. There is one point why I wanted to go to build an experiment with metastable helium. It's because I knew that quantum optics with photons had been developed because of the possibility to detect single photons. It's single photon detection and counting which had allowed all this beautiful development, Hambury, Brown, and Ongu and Mandel, correlation of photon, etc. And with metastable helium, we had the same opportunity. When a metastable helium atom arrives on a surface, there is one electron ejected, and then it's just like in a photomultiplier. You can detect single atoms. So this was the reason for going there, and it was a very good idea. And Chris, I have to thank you for all the beautiful things that you have done, including the fact that we are trying to get a Bell inequality with atoms. I would be so happy that I see that in my lifetime. Okay. Anderson localization. I must give credit to Philippe. We decided that it was a good idea to embark into that. And for that, something interesting happened in experimental physics. We had that experiment that was shown, I don't know on which presentation, of an atom laser. It was an experiment which had demanded a lot of effort to be... Qu'est-ce que tu fais? Ah non, il y a une lumière. Ah non, OK. We did a lot of effort to develop that experiment. And when we said we have to work on that, it was clear immediately that with a small modification, that experiment would be the one to do that. Well, by the way, it's the same thing which happened in École Normale with subrecoil cooling. We had starting cooling metastable helium, and one day with Claude, we realized that it was possible to do subrecoil cooling, and it took a few months to do that, because the experiment, which has been started for another reason, was there, ready to welcome ideas. Okay, talking of Anderson localization, it was Vincent already cited Dominique Delalande, but I think that we should say, well, we would have been happy that he can be here today, but he cannot be here for health reason. But we owe him a lot, and so it's important to say it. Well, about that, well, you have to handle me for another time. When I heard about Anderson localization, and we were convinced with Philippe that we could do an experiment with Anderson localization, I did not know why it was interesting. And you know where I found the answer? I found the answer in the introduction of papers of Mott in the 50s. Not in more recent paper. In more recent paper, it's very elaborate, it's sophisticated. You say, what is the real reason? And if you look at the old papers of Mott in the 50s, the reason is very simple. You have a piece of matter here. It's full of electrons. How is it that it is an insulator? Of course, if you have a crystal, you have the band, etc., the gap, everything, but this is not a perfect crystal. And so the question was, why do we have insulator with pieces of matter full of electrons? And there were two answers. The one of Mott, which say because of interaction, you can block the conduction. And the one of Anderson, which say it was a single particle phenomena. Because of quantum interference for this particle, then the propagation is blocked. And so I want to give, well, they don't need me, but credit to these people who really knew what were the problems they were addressing. Okay, Eric, the reason why I wanted you to be here today, and I am grateful that you did this long trip to come here, is because I'm always impressed by the beautiful physics and elegant physics that you do. And this physics, you gave us another example today, okay, of that. And with plenty of side remarks which are very profound, like the one on Berry phase related to gravity, etc., etc. You mentioned the fact that we have to bring to Stockholm a piece of equipment. what I brought to Stockholm is an exemplary of the switch. You have two versions of it in the window here. There is a nice one and a dirty one, the one that I brought to Stockholm to emphasize the fact that we are real experimentalists, bricolants. How do you say bricoler, Bill? Okay. I brought the one which is really dirty, and so you have now in the window of Stockholm close to the Marie Curie notebook and things like that. Okay. Who did I? Bill. Yes, I already tell you all the models. Okay. Nicolas. I already told you. I use the word non-localité. And I think that really you helped me to feel safe enough to say that quantum non-localité can be conceived. I don't know if there is really something real like quantum non-localité, but having that image is extremely fruitful, and you played an influence, you had an influence of me on that. And yesterday night, you showed me a very nice quantum number generator, the one that you cite. People asked, why is it interesting to have such a random number generator? And somebody mentioned my MOOC. I explained with many words what I am going to tell you in a few words. A good random number generator is a machine which will give a result that even the engineer who built the machine cannot know in advance, okay? If I send a photon on a beam splitter, nobody can know if it will be transmitted or reflected. How do I know? If somebody would know, it would mean that there is a hidden variable. And we know that there is no hidden variable because a violation of Bell's inequality. And I think that it is a fantastic reasoning. It shows that it is a fundamental random number generator. Antoine Broes, well, I have not much to add. Your words were so moving for me. But I want to say one thing about Antoine. At the beginning, I had asked him to work on an experiment with metastable helium, and I had made a project to the DRET, telling them that with metastable helium, we would do a probe, you know, a probe of surfaces. Okay. Antoine went to Les Houches, and he came back from Les Houches and told me, look, Alain, I don't know if Eric was, but probably Eric. I've listened to Cornell, Ketterle, or these people. I don't want to do a probe with metastable helium. I want to build a Bose-Einstein condensate with metastable helium. I say, are you crazy, Antoine? Have you heard of penning ionization and that? He say, yes, you know, there is a calculation by a Russian theoretician, Zhora Shlabnikov, well, we didn't know, Shlabnikov, and he says that if we can polarize the atoms, we suppress by 5 orders of magnitude this killing collision. And I say, but you trust it? Yes, I have done the calculation, and I agree, it's 5 orders of magnitude. And after doing the devil advocate for another couple of hours, or maybe of days, finally I told Antoine, okay, go ahead, Antoine. And this was the long way, which ended into what Chris has told us. So thank you very much, Antoine, for that. Pascal, of course, what you do goes deep to my heart, because single photons, we did that with Philippe. It was the PhD thesis of Philippe, and you know, entangled photon, single photon, as I said, is my first love. And so when Pascal comes and says, Alain, I have a soul for single photon, would you like to be in my advisory board, etc.? How could I refuse? Okay, so I did not refuse, okay? Bruno, another student, he mentioned it, but I have to say it clearly. A colleague here, Jacques Sabater, came and told me, you know, Alain, there is an outstanding student in the first year of Suboptique. Maybe you should try to attract him. So I went to Bruno and told him, look, Bruno, it seems that you have a lot of free time because he was studying so fast that he had a lot of free time. Why would you not come to the lab and play with whatever you learn? You know, it's fun to play in the lab. And he came, and it's how we have spent all this time together. Bruno has also been the one who has shown me that innovation, starting a startup company based on some fundamental ideas, is not blah, blah, blah. He showed me that it can be a real apparatus. And honestly, the money I gave him at the beginning, I thought I would never get my money back. I have, you know. When he sold his company, I got my money back with a multiplying factor, okay? So this is amazing. Of course, the important point, as he said, is not the money. The important point is that he has demonstrated that, yes, you can build a machine which goes on the field, which goes on the volcano. What else? Is it finished already? OK. Qui j'ai oublié? Granger? Je t'ai oublié, Philippe. Philippe. How can I forget Philippe? Well, Philippe, Philippe is somebody that I met probably, well, at École Normale, but also we were participating into a group, a circle of physicists who were discussing philosophical books and historical books about physics. And I must say that it was more fun to study history than epistemology. Anyway, this is where I found Philippe. I told him I was doing this experiment on Bell's inequality. He agreed to come. And then Philippe, it was in 80 or 81, Philippe? I had already several invitations. So I would go and travel. And the first time when I went somewhere and traveled and came back to the lab, and you know, it's a lab where it's dark. So you have to know where are the knobs. And when I came back, the knobs were not at the same place. Philippe had changed a lot of things in the experiment, and then I was relying totally on him to run the experiment. But of course, he was fantastic, so I could fully rely on him. And I must say that Philippe, I am really impressed by all you have done during your scientific life. You know quantum optics much better than me, but you are an outstanding teacher. Each time I see something which surprises me in the literature, I give a call to Philippe. Philippe, can you explain me that? He says, yes, and I go to his office, and he gives me a very clear explanation. So, Philippe, thank you for this long relationship that we had. Am I finished now? Yes, probably. So now, I would like to open again the other computer because I want to show some images. Est-ce que ça va marcher si j'ouvre directement? Ou il y a un mot de passe? Non, ça marche. Oui, mais moi je l'ai ici. Alors, je ne sais pas ce qu'il faut faire, mais il faut que quelqu'un fasse quelque chose. Mais il n'y a personne qui est capable de faire quelque chose. Alors que j'ai les images ici. Qu'est-ce qu'il faut faire pour que ce soit sur l'écran? Oui, d'accord, mais allez, on va aller à la fin. Bon. On va aller à la fin.
Allez, vous pouvez aller comme ça directement. Ça va rater.
Non, mais ça va, je vais faire passer rapidement, ça va être efficace.
Il
ne faut pas tout montrer.
Non, ça ne montre pas.
Ah bon. Voilà, donc j'avais fait une série de remerciements. Non, mais vous allez voir, attendez, soyez pas impatients. Et maintenant, après avoir... alors, j'espère que... Comment je le mets plein écran? Comme ça. Non, ça a recommencé au début. C'est insupportable. Allez, hop, on va y aller comme ça. Tac, 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 tac. Il faut être pragmatique dans la vie. Voilà, j'en étais là. Et hop, et voilà. Et donc, après avoir raconté, parlé de tout ce qui a été fait, bien sûr, il n'y a pas seulement cette expérience, mais effectivement, cette expérience... Oh, sorry for that. After talking all these various things which have been done since 1982 experiment, of course, I have to admit that the 1982 experiment was very important in my life. And so my thesis was defended at Institut d'Optique exactly 40 years ago. It was in February 83. Maréchal was chair of the committee. John Bell was there, Claude Cohen-Tanucci, Bernard Despagna, Christian Imbert, and Frank Laloué. And of course, when I compare that, there is 40 years between the thesis and between our meeting in Stockholm with Philippe and Jean. It was wonderful. But Annie has found a few days ago all photographies, bad style, old style, you know, no-numeric apparatus, etc., of the day of the defense. And I think there are some interesting things to see. You know the guy here? Well, he has a mustache. This is John Bell, and this is Christian Imbert. As I said, he was the one who allowed me to do this experiment. Here, another photo. And the reason why I keep this photo is that here we know that this is Claude Cohen-Tanucci, right? But unfortunately, we don't see better than that. You know, it's old photo, they are bad quality, and there is not much. Okay. Now, André Maréchal who is talking, okay, he was a chair. Bernard Despagna, here. Bernard Despagna was important for me. Claude Cohen-Tanucci, here. And I don't know why, but Frank Laloué is never on this photo. Maybe he was hiding somewhere. Why do I have that one? Who do we? Yes, that one. Who is the man here? Serge. Who is the man here? Alfred Kassler. Alfred Kassler came and attended the thesis sitting in the front row, probably under the influence of Claude, but I was very happy to have Alfred Kassler sitting in the front row. Okay. Now, in the evening, there was at my home a party with, as usual, foie gras, sauterne, etc., etc. And do you recognize the guy here? Philippe, you recognize the guy here? This was Philippe Grangier. Can you believe it? Attends, Jean. Jean, tu y étais aussi à cette soirée? À ton avis, c'est qui là, le gars? Et puis, pour ceux qui la connaissent, ça, c'est Annie. Bon. Merci beaucoup à tous. Et après, vous pouvez applaudir. Et après, j'ai encore quelque chose à dire. Voilà. En témoignage du rôle extraordinaire que l'Institut d'Optique a joué dans toute cette aventure, comme je l'ai dit, le fait que... Est-ce que je vais arriver à le trouver? Yes. As a testimony of the fact that Institut d'Optique played a big role, I have brought with me, but I don't find it at the moment, somebody stole it. I brought with me the Nobel medal, and I will, not the real one, a replica. But you know, when you receive the Nobel Prize, they give you the medal, which is solid gold, okay? And this one is in a safe box. But you are allowed to ask at the same moment, they will printing simultaneously 2 other replica, which are plated gold, and they look exactly the same, I can tell you. And I wanted, Rémi, to give one of these replica to the Institut d'Optique to show how much I owe to Institut d'Optique. La voilà. La voilà, Rémi. Voilà. Tu es jeune. Voilà, la médaille. Donc tu feras attention, il faudra que tu trouves quand même une armoire. D'abord, il faudra dire aux gens que ce n'est pas de l'or massif, comme ça, il y aura moins de tentations. In English. You will have to tell people that it is not massive gold, but it is only plated gold. Maybe people are not going to break the windows, but you have probably to have a safe window for putting that in it. Okay?
So thank you so much, Alain. Yeah, I think this is the best way you could conclude this fantastic day. So I know what you owe to Institut Optique, but we all know what you've done for Institut Optique and what you're still doing to promote the fantastic place and the fantastic model we have. So we all thank you very, very much for that. Maybe it's time to. And this medal is probably something that now enters the history of Institut Optique. So I think that's a great symbol. I don't know if you want to add something before I really conclude the day.
Of course I want to add something. No, I have a microphone. No, this day has been unbelievably friendly, moving. Do you say moving pour émouvant, Bill? Yes, moving for me. You know, it's well beyond what I was expecting. And don't repeat it too loudly, but of course, Stockholm is fantastic, but nothing like the friendship and the friendliness that I feel here. And for me, it has been a fantastic day. And I want to thank all the people who have organized that day. I know that they have done a lot of work. Thank you very much to all the people who organized, and thank you to all the people who came for making this day a wonderful, friendly day. Thank you.
I don't think I have so much to add, but I just wanted to say that we designed this day the way you wanted it to be, okay, at the same time prestigious and a great scientific day and convivial. So I had the feeling that we succeeded because I had very, very good feedback during the day. So we all enjoyed the day. Alain, I hope you enjoyed it as well, of course. I really would like to thank all the speakers who played this game, to being with us today and to play the game, to be in the spirit of the day. I think that's also something that really means a lot to you, Alain.
Yes, absolutely, definitely, as they say.
So this is the end, and I really thank you in the name of Institut Optique for attending. And before we really stop, I just want to ask the speakers and the chairs not to escape too fast, because we want to do a picture all together right in front of the window outside. Thank you very much, and have a nice end of the day.
So you will see that it's quite big. So oui, viens là. So I didn't prepare too much to say, but I think the main message is everyone is here and so happy to have you here in the lab. Je sais pas si entre différentes générations.
Le photographe est fini son travail.
So I don't know if you want to say something.
Merci. Cher Alain, dear Alain, so there is a small surprise before we go for lunch. The origin of the surprise is the following. So this day is a tribute to your research activities and the Nobel Prize that you received last year. But when we discussed the program of this day with the scientific committee, so with Rémi Carminati, Jean Dalibard, and Philippe Grangier, we also thought about your strong commitment to teaching and to the students. So you've been lecturing in many different places. First of all, at Institut d'Optique for many years, and you're still teaching. But also at VNS in Paris, at VNS Cachan, now NS Paris-Saclay, and École Polytechnique. And so we thought that there should be something which is mentioning your commitment to teaching. And so we discussed with Clémentine Bouillet, and we came to the idea that what we could do is contact a former PhD of the group, Hugo Caïla, who is now a video maker, and that we will, let's say, collaborate to have him realizing a short video. So this is a small gift from the Institute.
Ce que j'appelle mes enfants scientifiques, c'est ceux qui ont fait la thèse avec moi ou qui ont suivi mes cours. Et puis les petits-enfants, c'est ceux qui ont fait les thèses avec mes enfants. Donc j'en ai beaucoup finalement.
Oui, donc j'ai eu Alain en cours lorsque j'étais en première année à l'École normale supérieure à Paris. Et donc, en fait, il faisait une option sur l'optique et les lasers au deuxième semestre de la première année.
J'ai rencontré Alain en tant que professeur en cours de laser et d'optique quantique à l'École Polytechnique. Donc, 2 cours, 2 années d'affilée.
J'ai eu Alain Aspect en cours, donc à l'Institut d'Optique en 2e année. Donc c'était un cours qui s'appelait Interaction, rayonnement, matière.
Alain Aspect était mon enseignant quand j'étais à Cachan. Il était très apprécié comme enseignant qui nous préparait à la grègue.
Ça c'était un très bon prof, oui, c'est le moins qu'on puisse dire. Il était même célèbre dans l'école. Il faut rendre à César ce qui est à César. Il a un talent énorme, considérable pour expliquer les choses, pour convaincre les gens.
Do we really need to quantize light? Until the 1970s, the answer was not 100% yes. Almost all known phenomena of optics could be described in the framework of classical electromagnetism without any reference to the notion of photon. But it is not the end of the story. We need to quantize light if we want to understand modern optics. But why should you want to study quantization of light?
Je me souviens que c'était quelqu'un de très très captivant, donc quelqu'un qui récite pas son cours, mais qui nous raconte une histoire. Donc en fait, on l'écoute un peu avec des étoiles plein les yeux et ça marque.
Alain insistait énormément sur le fait que ça n'a pas à être facile. La physique, il faut se concentrer, il faut passer du temps, et que l'enseignement, enfin la salle de cours, ça devenait un endroit où on se faisait des images.
À Polytechnique, on a l'habitude d'enseignement assez mathématisé, assez formel. Et lui, une chose que j'ai bien aimée, c'est qu'il insistait beaucoup plus sur les aspects liés à l'intuition physique.
Les notions qui s'enchaînent, les réactions, on les retient mieux s'il y a quelqu'un qui a trouvé une bonne image pour ces notions-là, quoi.
À quoi ça sert les images? Ça sert à avoir des intuitions. En tant que physicien, c'est à vous de choisir l'image que vous voulez. Bricolez-vous votre propre image. L'essentiel, c'est qu'on fasse tous, que vous appreniez le formalisme et qu'on fasse tous les mêmes calculs.
Bon, moi je pense que c'est vrai de tous les profs remarquables que j'ai eus. En fait, on voit que c'est des gens absolument passionnés par ce qu'ils racontent. Et en fait, Ils sont absolument pas blasés, même si c'est des choses qu'ils ont racontées déjà à 10, 20, 100 fois.
Donc ça, c'est vrai qu'un cours d'Alain, voilà, il y a les mains, il y a le corps, il y a la voix, il y a tout ça au service d'un contenu qui est difficile d'accès, qui est difficile. Alors, j'ai pas eu Alain comme enseignant de travaux pratiques. Je sais qu'Alain s'est occupé de l'agrégation pendant un certain temps aussi. Mais il y a quelque chose qui ressort énormément dans ses cours, même si c'est pas dans le cœur des matières que j'ai pu aborder lorsque j'étais étudiant en face de lui, c'est la partie technique. Toute l'histoire de comment on est passé des expériences historiques d'Alain aux expériences de travaux pratiques, c'est ça. C'est une succession de questions techniques.
Et quand j'ai vu ce sujet-là, j'ai vu que c'était les inégalités de Bell pour les étudiants. Je suis monté voir Alain Speck, qui était toujours dans la maison. Je lui ai dit, tiens, il y a des gens qui ont monté ça pour des étudiants. Qu'est-ce que t'en penses? Alors, immédiatement, évidemment, il a été plus qu'enthousiaste. Il a dit, vas-y, tu commences, je te trouve l'argent tout de suite, il n'y a pas de problème, on fait la manip.
Je dis, vous savez, elles étaient dures, les expériences. Mais aujourd'hui, les étudiants de suboptique, 5 jours par semaine et 30 semaines par an, ils testent les inégalités de Bell. Alors donc, je fais un peu de pub pour ça, voilà. Bon, sur ce, si vous le souhaitez, vous pouvez applaudir. Alors, c'est une vraie surprise. Écoute, c'est magnifique, Hugo, et j'en profite pour dire à tout le monde que c'est un récidiviste. Avant de faire ça, il a fait une série de petites vidéos sur les inégalités de Bell que je cite à chacune de mes conférences, et je vous encourage. Pour le trouver, il faut aller sur YouTube et taper quoi?
Photon jumeau, c'est le nom de la chaîne YouTube. Voilà.
Voilà, donc Hugo, qui a été par ailleurs un étudiant tout à fait important dans le groupe, n'est-ce pas, Vincent, qui a beaucoup contribué... Hein? David. Excusez-moi, je suis fatigué. Qui a contribué à des résultats importants du groupe. Et donc, maintenant, il fait des vidéos. Je ne sais pas si un jour tu reviendras à la physique. Tu fais un peu de physique au travers de tes vidéos. Voilà. Merci beaucoup. Merci à tous pour avoir manigancé cette surprise. Merci à tous les orateurs de ce matin, parce que je ne vais pas les passer en série, là, pas maintenant, peut-être ce soir, on verra dans la conclusion. Mais en tout cas, merci à tous. C'est vraiment merveilleux pour moi.
Bon. Tiens, Chris, tu me passes mon sac, s'il te plaît?
Bon. Merci beaucoup à tous. Et après, vous pouvez applaudir. Et après, j'ai encore quelque chose à dire. Voilà, en témoignage du rôle extraordinaire que l'Institut d'optique a joué dans toute cette aventure, comme je l'ai dit, le fait que... Est-ce que je vais arriver à le trouver? Ah, yes. As a testimony of the fact that Institut d'optique played a big role, I've brought with me, but I don't find it at the moment, somebody stole it. I brought with me the Nobel medal, and I will, not the real one, a replica. But you know, when you receive the Nobel Prize, they give you the medal, which is solid gold, okay? And this one is in a safe box. But you are allowed to ask at the same moment, they will printing simultaneously 2 other replica, which are plated gold, and they look exactly the same, I can tell you. And I wanted, Rémi, to give one of these replica to the Institut d'optique to show how much I owe to Institut d'optique. La voilà. La voilà, Rémi. Voilà, tu es jeune. Voilà, la médaille, dont tu feras attention, il faudra que tu trouves quand même une armoire. D'abord, il faudra dire aux gens que ce n'est pas de l'or massif, comme ça, il y aura moins de tentations. In English. You will have to tell people that it is not massive gold, but it is only plated gold. Maybe people are not going to break the windows, but you are probably to have a safe window for putting that in it, okay?
So thank you so much, Alain. Yeah, I think this is the best way you could conclude this fantastic day. So I know what you owe to Institut d'optique, but we all know what you've done for Institut d'optique and what you're still doing to promote the fantastic place and the fantastic model we have. So we all thank you very, very much for that. Maybe it's time to... And this medal is probably something that now enters the history of Institut d'optique. So I think that's a great symbol. I don't know if you want to add something before I really conclude the day.
Of course I want to add something. No, I have a microphone. No, this day has been unbelievably friendly, moving. Do you say moving pour émouvant, Bill? Yes, moving for me. You know, it's well beyond what I was expecting. And don't repeat it too loudly, but of course, Stockholm is fantastic, but nothing like the friendship and the friendliness that I feel here. And for me, it has been a fantastic day. And I want to thank all the people who have organized that day. I know that they have done a lot of work. Thank you very much to all the people who organized, and thank you to all the people who came for making this day a wonderful, friendly day. Thank you.
I don't think I have so much to add, but I just wanted to say that we designed this day the way you wanted it to be, okay, at the same time prestigious and a great scientific day and convivial. So I had the feeling that we succeeded because I had very, very good feedback during the day. So we all enjoyed the day. Alain, I hope you enjoyed it as well, of course. I really would like to thank all the speakers who played this game, to being with us today and to play the game, to be in the spirit of the day. I think that's also something that really means a lot to you, Alain.
Yes, absolutely, definitely, as they say.
So this is the end, and I really thank you in the name of Institut d'optique for attending. And before we really stop, I just want to ask the speakers and the chairs not to escape too fast, because we want to do a picture all together right in front of the window outside. Thank you very much, and have a nice end of the day.